Hi everyone. So today we will start a new topic which is paging. So paging is one of the less understood topic and paging and multi-level paging. So both are I'm calling the same thing. And people means like gate aspirant consider this topic very hard topic. And gate also ask in every 1 2 year gate also ask at least one question from this topic. So from gate point of view, yes, I can say it is very important topic. Also it is very interesting topic also. By the way, this topic is more about just aptitude. I mean, you will just get to learn this topic and then you just need to apply your aptitude. Okay, just a little bit of calculation and that's all. Okay, not very much heavy computer science knowledge you need. It is basic level of aptitude. Let's just get started with this topic. So paging is, by the way, not a new idea. Paging is basically, this idea I can say can be treated like it has been borrowed from your usual, page of a book which is having some page number, and also it has the index. So basically, so let's suppose this is the paging introduction. Okay, so the index will say that okay, chapter 18, which is paging introduction, is at this page number, right? So it is the same kind of idea where we will be maintaining some kind of index table, and here we call it page table. Okay, that's the only difference. So basically we will maintaining some accounting we will be doing for some memory blocks. That's all. Okay, that is what paging does. Let's just understand this bit more carefully and with the real world example, that why we need paging and so on. Okay, so suppose you write a C program. Suppose you're writing some C program. Let's suppose this is your C program. What happens when you run this C program? Okay, what happens when you click on the run for the C program? So when you click on the run, so once you start running this, then you notice that this program is converted to the process, something called as process. See, let me go little step by step. Although these things are I have covered in previous lectures, but still let me just go little step by step. That once you have this program, then there are different phases, right? One of the phase is called compilation phase, or first you compile this, then you will get some a dot out or something. Okay, let's suppose this is a dot out, and then we run this. Okay, then we run this, right? Now when we compile, then it will get converted to assembly and then to the binary, right? So basically, you might have seen in some assembly code that we write move, R1, let's suppose some address 1000 or something, right? I mean, from this location move to R1 or something like this, right? So we generally write assembly codes like this. Basically, we all I mean to say that we have some address here. Okay, we have some address here. I'm just quickly telling you, okay, the need of the paging here in terms of the assembly and in terms of the compile and run, and obviously all about the paging we will study. But since this I have already covered in one of the YouTube video, if you want, you can watch that YouTube video. Let me just tell you. If you search on the YouTube, you will get to know. You will get the link of this video. So the video name is the journey of a program, the big picture, compiler, linker, assembler, loader. Okay, so just I will say must watch this video. This is very nice video. Okay, just must watch this video. And uh, and in fact we have received many comments, okay, under this video, like some see one of the comment by Suman. So this comment got 40 likes and so on. Okay, so there are many other comments we have got, right? So there are many comments we have got. So basically you can see that this video has been very good. So just watch this video. It is really a nice video. Okay, so coming to this particular thing, that see, all of this I explained in that video that I just talked about, but still I will quickly go through about it. Okay, so suppose we have some assembly which is basically the part of compilation phase. Now in this assembly you have, let's suppose, some address 1000. Okay, now here I am writing 1000 of address of what? Address of some memory, right? This is address of obviously memory. Okay, address of memory. But the problem here is that, problem with us is that for the compiler, that whenever we compile, at that time we need to generate this assembly and all, right? Whenever we compile, we get some a dot out, and after some time, maybe you can say after 1 minute, after 2 minutes, or after maybe 1 year or 2 year, doesn't I mean it depends on you. But after some time we are going to run this, right? And the amount of time is not very fixed, and in the sense that you never know that whenever you are going to run this, at that time what is going in the memory, right? In the main memory, what is going to be there. So you don't know that this particular a dot out will get loaded where in the memory. You never know, right? So how you can write 1,000? This is the challenge. Since you don't know that where this code is going to sit in the main memory, that is why this challenge is with you, that how to write this address, because you never know that this is going to sit where, right? So basically, to overcome this, we place some abstraction. The name of the abstraction is logical memory. So basically, we say that let's not worry about the main memory at the compile time. Okay. So we say that okay, this program is going to get something called as memory. Okay, I mean this is exactly same as the physical memory. I mean the layout is same and everything is same, but we are calling it logical memory, which means it is very much independent of the physical memory, in the sense that it could be lesser, it could be greater, it could be equal size of the physical memory. It does not depend on the physical memory. And then we say that okay, let's suppose the program starts from the very beginning, and then it basically can use the whole logical memory. So basically, what I'm claiming here is that each program is having its own logical memory, which is starting, let's suppose, from zero, and depending on the size, let's suppose it is 2 power 32. Okay. So the claim here is that each program has its own logical memory. This is the claim. Okay. I mean this is the idea, and this idea is called logical memory idea, and this idea has actually changed the entire computer science. Okay. The whole operating system, whole running of the program, everything, this simple idea has changed everything in computer science. This is very powerful idea. It is saying that every program is having its own logical memory, which means whenever you have another program, assume that there is another logical memory which is there. So whenever you are generating this 1,000, okay, you don't need to worry about the physical memory, you don't need to worry about the other programs. You only think that you are the king and this is your land. Okay, you are the king of this land, which means you own this complete memory, and you assume your program is going to be shifted here, okay, starting from zero, and then you can use this whole memory as per your own choice. And this is basically, you can say, logical address, kind of logical address. Okay, this is what logical address is. Now obviously, ultimately, this all of this program has to be going to the physical memory, and we need the physical address, which is done by the operating system, which we will study actually. But for the CPU, it has to execute the code line by line, and in the code we are writing the logical address. Okay. So I might sometimes say one line. The line is that CPU generates logical address. Generates logical address. What does this line mean? It means to say that CPU basically read your a dot out, and this a dot out has the logical addresses. Like for example, load load from some memory location. Let's suppose, uh, I mean I don't know. Okay, 1,000 comma 2,000. Okay, it depends on the syntax, but yeah. So load from this memory location to this memory location, or maybe R1 or something like this, right? So store, okay, store, load, store. So these all are these logical addresses are there. Okay, so this is also logical address. So basically, CPU is going to read your a dot out, and in a dot out you have your logical address. Why this logical address is needed? Why I can't directly write the physical address? Because I don't know where it will be loaded in the physical memory at the time of running. Because I may run this after 2 years or after 2 minutes. I don't know what is the situation of physical memory, how many programs are there, and I don't have to know actually. Okay. So that is why we never write the physical addresses here, and we don't have to do this. We don't need to know the physical addresses actually. As a programmer, you can you as a programmer you generally write the code, but as a compiler also I don't have to worry about the physical address. The compiler also just write the logical address. And the powerful idea behind this is that assume that you have, the memory this program is going to use is this, okay, which is the logical memory. Now the rest job is up to operating system, that how to convert this logical address into the physical address. But yeah, but as a compiler I am very much independent and very much tension free, that okay, I can basically run my program using the logical address or using the logical memory. I hope that is fine to everyone. So now you might little bit know that how does the logical memory look like. So basically logical memory, or we also call it virtual memory, it has few sections like code section, or we generally also call it static section. Okay, static section, and then heap, and then you have stack, something like this, right? Now these are the two areas, heap and stack, which grow opposite to each other. Okay, so more detail you can watch in this lecture, but I'm just telling you little overview that okay, they grow opposite to each other. And and this is, let's suppose, 2 power 32 bytes of memory. Okay, so 2 power 32 bytes of memory. Then generally my code, see, this code is basically going to take, let's suppose, few bytes only. I mean, not even more than more than you know I can say, I mean, how much it will take, right? Maybe 100 bytes. Okay, I mean, this is 2 power 32 bytes, right, which is basically almost 4 GB, right? This is 4 GB of logical memory you have, but this is just, your code is just 100 bytes. Let's suppose this code will sit here. Okay, and whatever you do, you just need 4 bytes here. So heap and stack, it will all together, it will not be exceeding basically more than 500 bytes. So what I mean to say that in most of the cases this area is basically empty. This is empty in most of the cases in the entire lifetime of the program. Okay, I mean, generally stack and heap doesn't take too much, so this area is mostly empty. So I can say 99.9% of the area is empty most of the time. I mean, of the logical memory, obviously. Okay, so I hope I'm not going too fast. What I mean to say that you have code and you want to run this code, you assume that you have a logical memory. We also call it virtual memory. Okay, you can technically take 2 power 32 bytes of this logical memory, but practically we generally take out of 4 GB we generally take at most, in MBs, at most in MBs. Okay, if it is very high level of program, some game or something is like that, which is too long program or requires too much of memory, it might take some GB, but it is not to till the 4 GB. I mean, yes, there are obviously maybe even 8 GB programs or like that, but I'm saying in general, right? So in most of the programs, like, it is 99.9% area is completely empty. But that's fine. Like, for every program we say that okay, this much memory is available to you, right? So now how to actually run, which means that this is the logical abstraction that I have. I mean, logical viewpoint is okay, but ultimately it has to go to the physical memory. See, this is your virtual memory, but ultimately it has to fit into the physical memory, isn't it? So tell me, suppose this is 4 GB. Okay, this is 8 GB. Can you directly fit this somewhere here? Let's suppose from here to here, program 1. Can you directly fit? Can we directly fit? Then answer is yes. If it is 8 GB, then probably yes. Yeah, right. I mean, no one is going to stop us if it is 8 GB. If the area is also available to me, then probably yes, right? Then in this case, yes. In this case, but suppose this is 4 GB. This is also 4 GB. Then can you fit? Can we load or fit, whatever you want to say now? Then maybe let's suppose I'm here also, I'm saying yes. Okay, yes, in this case. But suppose, consider a case. uh, so here, consider a case where this is, let's suppose, 4 this is suppose 4 GB, but this is, let's suppose, lesser than 4 GB, which is suppose 2 GB. Okay, suppose 2 GB. Can we fit now? Can we fit now? Then answer is no, right? Answer is no. Basically, if it is lesser, then obviously we can't fit. But if it is greater, okay, if it is greater or equal, then probably we can fit. But still, do we really want to fit directly? I mean, if we fit directly, then at most one or two program may run. See the problem, can you spot the problem in fitting the directly, even if you can fit? The problem is the empty space, right? The empty space is a bigger problem here. See, even if we fit directly, then also this empty space is basically going to take too much of the space unnecessarily, and here this empty space, and obviously in between a program we don't fit another program or like that, right? So empty space is basically one of the major problem here. Now, instead of fitting it directly, what we will do, we will just divide this, okay, into few chunks, and I will fill, obviously I will fit the loaded or the filled chunks, and obviously whatever is empty, I don't have to fit it, right? I don't have to fit it. So this is just very simple idea that we can implement. And obviously now the complexion will start, because since we are not directly fitting, we are first dividing it and then fitting. Now little bit of complexion will start, or little bit of complexity will start, and which is addressed by paging. Very simple idea. So the idea is very simple. What we will do, we will divide. See, earlier it was not divided. Now I will divide this, okay, into some chunks. Okay, divide into chunks. So let's just call divide into some piece of block. Okay, let's just call this piece of block, this has got very interesting name, this is called page. Okay, so we call it page 0, page 1, page 2, page 3, like that, right? Okay, we will call them pages. These are the pages. And now we can fit, or we can load this page anywhere, this page anywhere like that, right? Now we can load these pages anywhere as per your wish. But to make it little more structured, what we will do, we will also divide this physical memory. Currently this physical memory, I'm not dividing, but we will also divide this physical memory of equal size, which means if this page is of 1 KB, I will divide, if this each of this block is of 1 KB, I will divide this also into 1 KB, 1 KB each. Okay, so we call these piece of block as page, and here we call them frames. It's just like a photo frame. In the photo frame, you fit the photo. Similarly, in this frame, you are going to fit this page. I mean, not one-to-one mapping like this. It can go anywhere. This can go anywhere like that, right? So is the idea a little bit clear to everyone that what we want to do? Basically, we want to run our program, right? In order to run our program, we say that we at the compile time we do not know about the physical addresses, and we cannot know about the physical addresses. That is why we have to write the logical addresses, and all the game is of logical address. So basically at the compile time, to make it easy compilation, I said that or not just easy, to make it possible actually. Okay, earlier there was, when there was no concept of logical memory or virtual memory, it was very hard to compile and run, and actually you have to directly run. There is no two phases like compile and then you can't run it later, because you at the same time you have to know that okay, what is the situation of physical memory and all. It was too complex. But later on, with the very simple idea, the computer science has changed a lot. The simple idea is that we can introduce logical address in between, and now we have our whole logical memory. Logically you use this memory as much as you want. Okay, even till 2 power 32, I will tell you in detail, that you will get to know that how we are using it till 2 power 32. You can use anything. And now we can divide, and we obviously don't have to fit it directly. We can divide this into few small blocks, and we are calling them pages. And then we also at the same time divide physical memory into small blocks, we call them frames. And now any of this page can go into any of the frame, right? Now interestingly, you might remember that this is a heap and this is a stack. Now whenever any of this this logically, let's suppose this is required. Okay, whenever this is required, You don't have to worry, you just fit it. Okay, currently it is empty, then you are not fitting. Whenever the heap expand, you just fill it and fit it. Okay, similarly here, the moment it is required, you just fill it with whatever data. Okay, then fit it, just load into the main memory. Okay, the idea is very very simple here, and now the flexibility is too much. Okay, you can, this is ultra flexible, you can place any page in any of this frame, right? And we also have to obviously do the accounting. Okay, and this accounting has to be done by, accounting means this is, let's suppose, page number 0. I will generally we start with the indexing with the 0. This is page number 1, page number 2, page number 3. So page number 0 is, let's suppose, going to the frame number 5 or 6 or whatever, right? Let's suppose this is frame number 0, frame number 1, 2, 3, 4, 5, 6. So the in the accounting, okay, you will say that, okay, the page number 0, here you will write the page, here you will write frame. You will say the page number 0 has mapped to frame number 6, page number 1 has mapped to, something. If it is not mapped to something, you will just say it is not mapped. So we generally write invalid means it has not mapped. Let's suppose it has not mapped, you are not loading it to main memory for some reason, you can write invalid. Or let's suppose page number 2 has mapped to, let's suppose, frame number 0, and so on. Okay, and then it will be strictly increasing, like page number 0, 1, 2, 3, 4, like that, right? I mean, in fact, you don't have to store this index, because this is by default 0, 1, 2, 3, 4, 5. I mean, you can just store this frame numbers only in an array. Okay. I mean, the accounting you can do in an array, because in array, you don't have to obviously store the indices. I hope you're getting my point. Okay. So basically, let's suppose there are, let's suppose, 2 power 2 power 32 bytes of the memory is there, and let's suppose each page is having, let's suppose, 2 power 2 bytes. Then there will be 2 power 30 pages, right? There will be 2 power 30 pages if each page is of 2 power 2 bytes page size. See, initially I told you it is aptitude. Actually, it is aptitude. You can just divide these two numbers. This is the whole memory, right? 2 power 32 bytes. And this is size of one page. So how many pages will be there? 2 power 30, right? 2 power 30 pages will be there. So sorry about my handwriting. So this is 2 power 30. Okay. So how many entries, or how big the array will be? 2 power 30. Okay, 2 power 30 entries in the array, or in the page table, basically. Okay, 2 power 30, you can say, at the same time you can write the 2 power 30 entries in the page table will be there. 2 power 30 entries in page table. Okay. So I hope you are liking this idea, right? It has provided whole computer science a very good way to execute your programs. See, uh, logical memory is very, I mean, logical memory and paging are not very directly related, in the sense that logical memory concept is till this point only, which was some revolution in the computer science. Logical memory concept is till this point, that we have the logical, our own logical memory. Now how to fit this logical memory, okay, how to fit logical memory into this physical memory, that either we need to divide this into pages, or we can directly fit, or maybe you can divide this into unequal size or something, which is also called segment. This is another concept. So basically, paging is one of the way to implement the idea of logical memory, in the sense logical memory is this. Now how to fit into this physical memory, there could be many ways. One of the ways is paging. Okay, another way is also called segmentation, something like this, right? But I hope you got the paging idea, because currently we are studying paging, and paging is only important. Segmentation, they have just asked one or two question in last 45 years or 40 years, so segmentation is not important at all. So basically, for the paging, you just understand, we are going to divide this logical memory, we are going to divide this physical memory of equal size, and then we can fit any page anywhere. Okay. Now, interestingly, one more thing which is little optional at this point, okay, and I don't want to, make it complicated, but still, let me just reveal you some suspense about the physical memory. That physical memory is something which is, the supreme. I mean, ultimately, in reality, it's the physical memory is only there. I mean, virtual memory is not there, right? In reality, So physical memory is supreme, and in the physical memory we can store pages. Yes, we can store pages. Can we store some integer apart from the page? I mean, let's not worry about the pages and all. Apart from the page directly, can we store some integer? Yes, we can some store some integer. Can I store, anything like, can I store something else? Can I store something, some operating system code? Can I store OS code? Yes, I have to store OS code. So basically in the physical memory, it's not only the pages are going to get stored. There are multiple things that are going to get stored in the physical memory. So in reality, the physical memory is basically, get divided based on what you want to store. For example, if you want to store a page, we say that okay, we are dividing the physical memory each into the page size. I mean, the slots will be of the page size. If you want to store some integer, okay, then we say that okay, the physical memory, I will just tell you a little later, but currently I'm just revealing one suspense. I will say that okay, physical memory is divided into, let's suppose this integer is 4 bytes. Okay, physical memory is divided into 4 bytes of blocks. Okay, each of 4 bytes, something like this. And then in one of the block, one integer will sit. It's not like that in the whole physical memory I want to fit integers. No, even if I just have to store one integer, just a single integer, then also I assume that the physical memory is divided into integers block, and in one of the block it will go and sit. Basically, basically the address at which this integer will get stored, it will be the multiple of 4. Okay, it will be multiple of 4. So basically I will divide into 4 each of part 4. So it's not like that the address is starting from 3, or the address is basically, starting from 2 or something like this, or from 7 or something like this. It will be multiple of 4. Whenever we store integer, the address will be multiple of 4 if it is a 4 bytes in the physical memory I'm talking about. So anyway, let's not worry about it. The only thing I wanted to convey, that physical memory is supreme, and whatever we fit into the physical memory, based on that, at that, just sake of understanding, okay, based on that we divide the physical memory into that size only. Suppose I want to store the page, I will divide the physical memory into pages. It's not that I have to fit all physical memory into pages. No, even if I have to just store 2 pages, 3 pages, 5 pages, only one page, I will assume that physical memory has been divided into pages, and I will just ask it to, go into one of the frame or one of the slot. And then now let's suppose after this page I want to store some integer, I will assume that again it is divided into the size of 4, something like this. Okay, so don't worry if you have not understood what I have just said. It was just optional discussion. Okay, just to make it clear that physical memory is basically supreme. It's not that it's permanently divided. No, just a logical point of view. Just for the sake of understanding, we say that okay, we are dividing it. But still, see, even though I told you some suspense, still I urge you and I request you. I will say it is mandatory. You assume that logical memory has been divided into pages and physical memory has been divided into frames permanently and once for all. Okay, just assume it has been divided into frames. Otherwise, you might get keep on confusing. Okay, assume that physical memory has been divided into frames and logical memory has been divided into pages, and that's all. That is all needed for the paging discussion. Okay, so now the next thing we have to do is accounting, which means that we have to basically see that okay, page number 0 is in which frame, page number 1, page number 2, page number 3, page number 4, till page number whatever the page numbers are, 2 power 30, right? So till this page number is in which frame, so I will be just keep on storing. Okay, this is in which frame. If some page numbers in the between, let's suppose these are many page numbers in the between, if they are not loaded anywhere, I will say it is invalid. Invalid means it is not loaded anywhere. Invalid. Okay, see, it's very simple. It's just like I want to store something into the physical memory. I am just keeping it accounting, and I'm this table is called page table. Okay, I'm just having accounting here. Then this table is called page table. Very simple idea. This is the whole idea of paging. Logically, the idea is clear. The idea and implementation part is clear. Now we just have to understand this with respect to the aptitude part. Okay, that how to like store and little bit part we will understand. But this is, I can say, conceptually this is the end of paging. I mean, this is all we have to understand in the paging. That's all paging is doing, right? But still for the numerical perspective and for the for understanding this paging, obviously we have to spend a lot more time in this, right? So I hope this is clear to everyone. Now the size of page 0 and size of page 1, size of page 2, all these pages are same size. And page 0 size and frame 0 size, page 0 size, frame 1 size, I mean all of these sizes are same. Okay, these are kind of slots, you can say these are the slots or the frames, and these are the pages. You can load it anywhere and it will exactly fit. It will exactly fit. Understood? Okay. So by the way, this whole logical memory we have, right? We have the concept of logical memory. We also call it logical address space. Okay. So for example, we have the virtual memory or the logical memory. Suppose this is of 4 GB, right? 4 GB. Similarly, there is a physical memory of 4 GB or something. Now there is a term called address space or logical address space or physical address space. Let me just tell you, since I will be using this term again and again. Space means some space, right? I mean, this is some space, this is some space, like that, right? So if I say address space, this is a space in where memory. So this is a space. I mean, need not to be the empty space. It could be the filled one also. I mean, but it is some space in memory. Okay. So basically logical address space means this whole space, this whole memory. Logical memory and logical address space both are the same thing. Okay. Address space means like this is like my space. Okay. My address space, like that, right? Similarly, if it is physical memory, I will say this is a physical address space. Okay. Just like a terms which are coined here and there. Otherwise there is nothing more to know here. Okay. So I will be having page number, frame numbers like this, right? A system uses paging with a page size of 4 KB. If the logical space contains 2 power 32 bytes, how many pages are there? So they are saying that page size is 4 KB. By the way, KB means K means 2 power 10. So basically, let me just tell you that whenever I say 1K, it is basically 1 kilo, or in terms of computer science, it is 2 power 10, right? Whenever I say 1 mega, it is, I mean, generally we call it 10 s power 3 in kilo, and this is like million, which is 10 s power 6. In computer science, this is 10 2 power 20. 1 giga, okay, let's suppose this is bytes. So these are the bytes only. Giga means 2 power 30, okay. So this is a small terminology that we will remember. Here it is 10 s power 9. I mean, in the sense that these are not exactly equal, but the values are almost equal. For example, this is 1024, 2 power 10 is 1024, this is 1000, right? Anyway, you don't worry about the later numbers which in 10 s power. For us, we just need to know 2 powers, right? So 2 power 10 is K, 2 power 20 is mega, 2 power 30 is GB, giga. Okay. So now page size is given like this, which is 2 power 12, 2 power 12 bytes. Logical address space is 2 power 32 bytes. How many pages are there? So logical address space is given as 2 power 32 bytes. The number of pages will be the whole logical address space divided by one page size. It will be 2 power 20, right? 2 power 20 will be number of pages. So D is the correct answer. This is very easy question. I hope you understood this. Now let's do the next question. So the next question says that a process has a logical address space of 8 pages. So which means the logical address space has 8 pages here, right? So these are the 8 pages. Now they are saying that physical address space or the physical memory only has 5 pages. So here you have only 5 pages, right? These are, let's suppose, 5 pages. How many pages or 5 frames? You can say 5 frames here, okay? Here the terminology is like frames. Okay, so how many pages at maximum can be in memory? Memory means like can be in memory means like it must be physical memory. Okay, the physical address space. This is logical address space. So how many pages at maximum can be in memory at the same time? So I think 5, right? It cannot be more than 5. So 5 is the correct answer. Easy question. Now let's just move to the next question. So which of the following statement about the logical and physical memory is true? Logical memory is always smaller. Logical memory is always larger. Can be larger. Yes, it can be larger. Both are always equal. No. So whatever is having always term, these are false. Okay, false, false, and false. Can be larger, can be smaller, can be like these both are independent of each other. If the logical address space is 1024 bytes and each page is 16 bytes, then how many pages are there in total? So they are saying that you are having 2 power 10 bytes of your logical address space. So this is your logical address space and each page is 16 bytes. So page size is 16 bytes. Now, how many pages will be there? So it is 2 power 4. So you can just divide 2 power 10 divided by 2 power 4, which is 2 power 6 pages. These are the number of pages. So which is 64, right? 64 pages will be there. Again, this is easy question. So each page is 16 bytes. And if it is 1024, then 2 power 6, which is 64 pages will be there. Okay, for example, this is page 0, this is page 1, like that. This is page 63. And each page is having 16 bytes, right? So 16 means like here 0 to 15, then 16 to 31, something like this, right? Okay. Now let's go to the next question. Now they are saying in the previous question context only this question has been asked. They are saying that byte number 17 belong to which page? See here, this is byte number 17, right? I mean, or the address 17. This belong to which page? Very clearly it is belong to page 1. So basically you can say 0 to 15 belongs to page 0. Okay, and then 16 to 31 belongs to page 1 and so on, right? So someone asks you byte number 17 or address 17. Okay, this 17 belongs to which page? So you can divide by the 16. Okay, 16 because 16 is page size. So you can say that if you divide, then you can just take the integer part. Okay, 1. So here I'm just taking the integer part. So you will get to know the page number based on the logical address or based on the byte number that you are interested in. So this is logical address. So I can say this logical address is in which page? This is the page number, right? Is in the first page. I mean first in the sense like if indexing is start from 0. And we always start indexing from 0. So I can say that 17 is page number 1. And similarly, if I have to find out, let's suppose, so by the way, for this question, answer is 1. Okay. But similarly, if I have to find out that where is 18, so 18 logical addresses or logical address will be also in the page number 1, right? 18 is also page number 1. In fact, if you divide 16, so let me just, copy this diagram to the next page. So if you have, let's suppose, logical address 16, and if someone asks you, where is this 16 present? So logical address 16 is actually in page number 1. So you can very easily see 16 divided by page size is also 16. So it is, so basically this is logical address. And this is page size. So that's how the division is happening. And 1, here it is integer part, which is the page number. Okay, that's how we get the page number. So if I just ask you, where does this logical address 16 present? You will say it is in page number 1. Where does this logical address 31 is present? You will say again it is 1 point something, right? 1 point something. So basically the integer part is 1 only. 1 only. So you will say 31 is also in page number 1. Okay. Similarly, where does this logical address 0 is present? Logical address 0 is in page number 0. Logical address 1 is in page number 0, because 1 divided by 16 will be 0 only. Until unless it is 16, it will be 0, right? Till 15, it will be giving you 0. Okay. So it is very clear that if you want any logical address, so suppose if you want 1023 or 1022 or whatever, right? So 1023 is present where? If you divide by 16, which is page size, then you will get 63 point something. So basically this 63 is integer part. Okay. So you can say it is 1023 is in page number 63. Okay. 1023 is in page number 63. I hope you understood. This is very easy to understand. So, so let's just solve this question. They are saying 130 byte number 130 or logical address 130 is present in which page? So you can do 130 divided by 16. This is again in the previous question context. Okay, so you will be getting I think 8 point something. So it is 8 point something you will be getting. So basically page number is 8. Page number is 8. Okay, so if you do 130 divided by 16, you will be getting 8.125. 8.125. So integer part is 8. And similarly, if you do 16 multiplied by 8, then you will be getting 128, right? So 128. So basically, you can say that it is in page number 8. So by the way, what does this mean? That page number 0 is here, page number 1 is here. So if it is in page number 8, then how many pages are above it? Can you tell me how many pages are above it? See, if it is in page number 1, then one page is above it, right? If it is in page number 0, then 0 page is above it. Okay, I'm just asking above. If it is page number 8, since the indexing is start from 0 to 7, so 8 pages are above it. 8 pages are above it. Okay, now there is no indexing and all. I'm just saying number. Okay, this is the number 8. Okay, 8 pages. Like counting. I'm just counting. Okay, 8 pages are above it, right? And each page has actually 16 bytes. So 16 into 8, which is 128. So 128 bytes are above this page. And 130, this is 129 byte, and this is 130 byte. I mean, if you're indexing, the byte number is also actually starting from 0. So basically, this is 128, byte number 128, 129, and then this is byte number 130. Okay. So basically what I mean to say that you can easily logically also see that, okay, till, see, if 8 pages are above it, then till byte number or 128 bytes are above it. 128 bytes means byte number 0 to byte number 127 are above it. Byte number 128. Okay, if I just ask you what is the page number for byte number 128, you will say it is 8 only. Byte number 128 is here. Byte number 129 is also here. Okay. Byte number 129 is also here. Byte number 130 is also here. Okay. All of these three, and in fact, there are 16 bytes here. Right. So 128, if I just, add 15 here, you will be getting, so 143. Okay. So byte number 128 till 143 are here. Till 143. Is this fine to everyone? And then byte number 144 will be in the next page, which is page number 9. So if I just ask you why 144 divided by 16, then you will be getting 9, right? Because the integer part is 9. 144 is in the next page, which is 9. So you just do one thing. You just have this calculation, very clear with you, which means they just take pen and paper and just see if it is making sense for you or not. So basically we are able to say that, okay, these many pages are above it, which means that that you can multiply with the page size, which means 16 into 8, 128 bytes are above it, and which means this is 128, 129, and this is 130 byte, and 1/3 byte number 130. Okay. So I hope little bit it is clear. So now let's just see more examples. I hope it will be clear more. But one thing you might have noticed here. See, this is page number 0, this is page number 1, and similarly till page number 7 I have, right? And then there is a page number 8. Okay, this is page number 8. Here, this is 128, byte number 128. It is in page number 8. Byte number 129 is also in page number 8. And then byte number 130, it is also in page number 8, right? This is also in page number 8. Now, if you divide this 130, if I want to know the page number, then I told you very simple formula. You can just do like this, and which means you can just take the integer part. And then you will be getting the page number. But suppose within this page, how much down I have to go, or in other words, how many bytes I have to skip to get this, right? How many bytes I have to skip? 2. So basically, how to get that number? I mean, mathematically, just like this division. See, what you do, you just take the mod, okay, which means remainder. This is quotient, okay, this is quotient. But if you take the remainder, you will getting 2, okay. This is the remainder. So this is also called as offset. This is also called as offset. Offset means how many bytes I need to skip within that page. Once you reach to this page, so basically I know that this is in page number 8. But in page number 8, there are 16 bytes, right? There are like byte number 128, 129 till byte number 143. Till byte number 143. There are like 16 bytes here. Now I need to know that okay, how much down I have to go here. So basically you will get to know this by the offset or using the mod operation, which will give you the remainder. So which means let's suppose if I ask you, this is let's suppose page number 0, this is let's suppose page number 1. So page number 1 typically has from byte number 16. Okay, see, every page starting address must be multiple of 16. Okay, every page starting address must be multiple of 16. This is I mean, because the page size is basically 16, right? Until 31. So 16 till 31. Last address is not multiple of 16, but yeah, the next address will be 2. I mean, for the page number 2, this is basically 17. Okay, sorry, 32. This is 32, which means it is again multiple of 16. Okay, it is 0. So 0 is again multiple of 16. The starting address must be multiple of 16. Anyway, so what I'm saying here is that suppose you pick 17, okay, byte number 17 or logical address 17. Both are the same thing. Logical address 17 you pick. Okay. If I ask you where is this 17, then you will tell me the page number if you want to know. Okay. Page number. It is logical address that you have, right? Divide by page size. It is very natural, right? Very natural. So from here you will get to know the page number. So logical address is 17, page size is 16. So the integer part you need to take, right? So page number is 1. Now, if someone asks you, what is the offset? Offset means within the page, within that page, how much down you have to go. So if I just ask you, what is the offset? Offset you can find out using the mod operation. So this is the logical address. Mod page size, which means logical address is 17, mod page size is 16. So here also actually remainder is 1, which is fine. Okay, you will be getting 1, which means if you skip 1 byte, okay, if you skip just 1 byte, the next is 17. That's how you get the 17, right? So you just need to skip 1 byte to get the 17. Now suppose if I ask the same question about the 18, okay, about the 18, then what will you do? You will say, let me write here 18. So if you write 18 here, you will say it will be again 1. Okay, if you divide, then you will getting 1 as an integer part, which means page number is still 1. Now what offset is actually 2 here. Let's just see if we are getting 2 or not. So 18 mod 16. If you do the remainder part, you will getting 2. Okay, if you divide and if you take the remainder, it is 2 only, which means you need to skip 2 bytes to get this 18. Okay, that's what offset says. So ultimately what I'm saying, that any logical address, basically, okay, whatever it is, it will be basically some quotient which we are calling page number. Okay, if you divide by the page size, basically, if you divide by page size, then you can write like this. Okay, should I write quotient or page number? Let me write page number. Okay, page number into page size plus remainder, which is offset. I mean, mathematically it is like this. So you can say logical address. Given the logical address, I will always be interested into split into 2 parts. Split in the sense like take the meaning out of it. So first I will get to know the page number. Okay. Then I will do the mod operation and I will get to know the offset also. Okay. Within the page, how much bytes I need to go down. So for example, the page number, if I have to write the page number, this is logical address divided by page size. This is logical address mod page size, something like this, right? So I hope that is fine to everyone. Now what we will be doing? We will be doing few questions where it will be actually extremely clear that what do I mean to say. Okay, so we will be dividing the logical address into 2 parts: page number and offset. Let's just see. So now they are asking for the same question context, that for the byte number 130, by the way, page size here I'm saying 16 bytes. Okay, So for 130, what is the offset? So you will do mod operation, mod 16. Then you will be getting, if you divide, then it will be 8. 16 into 8 is 128. Okay, so remainder will be 2, which is offset, right? So 2 is offset. So I hope you are getting the meaning of offset. Meaning means, like, offset means that how much down we, or how much bytes we have to skip. Okay, so 2 bytes you have to skip to get this 130. So byte number 128 you have to skip, byte number 129 you have to skip. Understood? Now let's just solve this question. Logical address space is 1024 bytes, page size is 8 bytes, logical address is 905. Okay, so they're saying 905. I mean, this, I don't think you need to know this information, but that's fine. Okay, so they are asking you page number and page offset. So you just divide 905 by 8. Integer part you need to take. This is 1, again 1, and then 2, which means 3, right? Okay, 113. So you will be getting 113 as page number. What does this mean? It means that in page number 113, this address is present. Actually, in page number 113, there are many addresses present. Okay, so if you ask me that what is the first address in page number 113, then you can just multiply this by 8. Okay, so you will be getting 904. Okay, so in page number 113, the first address is 904, the next address must be 905. So offset must be 1. Let's just check it. Okay, so 905 mod 8. So let me write mod like this. Mod 8 will be 1. You can just check it. If you divide, then 8, and then it will be 1, 113, right? Yes. So 25 is there. I mean, you will be getting 1 as remainder. Okay, which is offset. So now you know completely about this aptitude, which means if someone asks you that, okay, anything they can ask you. For example, if it is page number 10, suppose this is page number 10. Now let's suppose they ask you how many pages are above it, and let's suppose they give you page size is again 16 bytes. How many pages above it? So what is your answer? Suppose they ask you how many bytes above it. Suppose they ask you what is the starting address. What is the starting address of this page? Okay, suppose they ask you what is the starting and the whole sequence, like address sequence, address range of this page, address range of this page. Okay, suppose they ask you anything about these settings, right? Then how to deal with these kind of things? You can say that, okay, how many pages are above it? 0 to 9, right? So always equal to page number. So if page number is 10, then how many pages are above it? 10 pages are above it. Okay, which means that 10 into 16, which means 160 bytes are above it. 160 bytes are above it. If someone asks you the sequence of bytes, you can say 0 to 159. Okay, 0 to 159 bytes are above it. Okay, anyway, what is the starting address? For the starting address, you just multiply by the page size, because it is always starting, always have to be multiple of 16 or multiple of page size. So you can say 160. Okay, 160 is starting address. And what is the last address? So you can just add 16, 160 plus 16, it will be 176. So you can say till 175, basically 160 till 175. I mean, this 176 will be for the next page. Okay, because you just have 16 bytes. So basically you can say this is the address range. Okay, is this clear to everyone that given a page, you know everything about it, right? Now suppose someone says that within this page, okay, there is some address. Okay, so let's suppose there is some MCQ that someone asks you that which of the following, suppose someone asks you that which of the following is your R addresses within this page, then you can tell, right? So let's suppose first option is 160, second option is 150, third option is 170, fourth option is 176. Then you strictly know it is from 160 to 175, right? We have just seen this. So 160 is answer, 170 is answer, but 176 is not the answer, right? So A and C are the answers. Suppose they ask the question something like this, that if the logical address is 170, then what is the offset? And in fact, let's suppose they ask you page number also. Actually, page number you already know, because 160 to 176 in page number 10. Still, let's just quickly solve this. So 170 divided by 16, you will be getting 10 point something, right? So that is why 10 is here. Now offset, basically you will be seeing that, okay, if you do the mod operation, then what should be the answer? So you can say 160, 161, right? So I think 10 might be the answer, right? So remainder will be 10, because 170 can be written as 10 into 16, 10 into 16 plus 10, right? So 10 is the remainder, 10 is the quotient. Okay, offset and page number both are for 170, both are 10. Is this fine to everyone? So what is the offset? Offset means how many bytes you have to skip to get this. Okay, so I hope that's this setup is clear to everyone. Now you might be seeing that we have to actually do this division and this mod operation, right? This seems to be little bit mathematical and little bit unnecessarily complicated. But fortunately, this is done very easily in the binary number system. And I will tell you how. Okay. In just few seconds or few minutes, I will tell you how. Okay. So by the way, I hope it is clear that page number, this is very important slide to understand that page number equal to logical address divided by page size, and offset is using the mod operation. Let's suppose they ask you something like this. Suppose that they say that logical address space is these many bytes and page size is 8 bytes. The page table is also given, which means some of the entries in the page table are given. Some of the entries obviously they have to skip because it is a long page table. Find the physical address corresponding to the logical address 905. See, for 905, we have just seen that 905 divided by what is the page size here is 8 bytes. Okay, integer part is 113. 905 divided by 8, sorry, mod 8, right? It was 1. Okay, we have just seen this. Yes. So basically we know page number, we know offset already, right? This is the logical address. Now they are going just one step ahead. They are saying logical address breakup is fine. Okay, you are breaking up into two parts, which is fine. Now can you tell me what is the physical address? See, corresponding to page number 113, what is the frame number? Frame number you can get to know from here, which is 10, right? So which means page number 113 is in the frame number 10. Now in the physical memory, they are just asking you that suppose this is frame number 0, frame number 1, like this. Suppose my page, okay, page number 113 in the logical address space, this is, let's suppose page number 113 is mapping to, okay, page number 10, frame number 10, right? Now they're asking you what is the physical address. See, for the physical address, one thing is very interesting is that offset doesn't get changed because you are shifting it as it is, right? So inside it, let's suppose you are earlier have to skip three addresses, 4 bytes, 5 bytes, something like this. Then also here also, once you shift this as it is, then also the offset will be same. So offset is same. You just have to count that how many bytes are above it plus offset, right? So basically, if it is in frame number 10, then you can say that 10 frames are above it. If 10 frames are above it, then how many bytes are above it? 10 into 8, which is 80 bytes are above it. And one we have to skip. So 81. Okay. So the physical address is 81. How? So how to find out the physical address? It is very important. It is basically you have the frame number, right? And then you have your frame size, which is exactly equal to page size plus offset. Offset you directly get from here. Frame number you get from this. Frame size you already know, this is page size. So 81 is the physical address. Which means according to this page table, if I fit this into the frame number 10, then the logical address 905. Okay. If I fit this page number 113 to frame number 10, then the logical address 905 get converted to physical address 81. And that is how using the page table you can also get the physical address. This is very easy, right? You just have to know the address of this byte. Offset you already know. You just need to know the how many bytes are above it. So using the frame number, you can know the how many bytes are above this page. So so I can say, see, if you have the logical address, you can split into page number and offset. Now there is some mapping, okay, which is called as page table. Using this page table, okay, using this mapping, you get the frame number. Now once you have this frame number, offset remains same, then using these two you get the physical address. How? You basically do one thing. Or let me write like this. Frame number into frame size, or the page size, actually both are same, okay? Frame size plus offset. Okay, this is your physical address. So offset you take from here and frame number you are getting from here. Okay, offset remain as it is. Is this fine to everyone? That given the logical address, how we are taking help of page table to get the physical address? Because you just need to know the frame number. Once you know the frame number, you have your physical address ready with you. Okay, so let's just let's just solve more questions. So basically the physical address is nothing but frame number into page size, or the frame size plus offset, right? So let's just solve more questions. Suppose they say that page size is 64 bytes and logical address is 810. Find the physical address. So first of all, from this logical address, which is 810, I will find the page number. What is the page number? Page number will be 810 divided by page size, which is 64. So integer part you have to take. So what do you think it will be? 810 divided by 64. It is 12 point something, right? 12. Okay. So this is the page number, and similarly you have to get the offset. So 64 into 12, it is say minus 810. Okay, this is 42. So offset you will get as 42, which is 810 mod 64. Okay, so first you divide this. Now to get the physical address, it is very easy. Using the page table, you can get the frame number first. So what is the frame number? The frame number for the 12, the frame number is 13. Okay, so the page table, they have given few entry of the page table. So from the 12, you can say it is 13. This is the frame number. This is important. Once you have the frame number, then 13 means there are 13 frames above it, which means 13 into frame size is basically 64. These many bytes above it, and then within the frame you have to skip 42. Okay. So 13 into 64 plus 42. If you do this, this is 874. So this is your physical address. Right? This is your physical address. Basically from 12 you are just going one down, which means you are just increasing 64 here. Okay, so if you add these two, I mean 810 plus 64, because earlier it was somewhere at 810. Now you the position is just one frame down, right? So which means from the earlier position. So anyway, so basically you can see that. Okay, now you are getting 874. So 8874 is your answer. Now let's suppose they are asking to convert, okay, this particular virtual address or this particular logical address to the physical address. The page size is 2 power 11 bytes, which means 2 into 2 power 10, which is 2 power 11. Okay, so what I need to do, I need to just convert this 2500 divided by 2 power 11 means 2048. 2048. So it will be 1 point something, right? It will be 1 point something. And then if I do the mod, means I just have to directly subtract here. 2, 9 minus 4, 5, and then 4, right? 452. This is 452. Now, what will be the frame number? It is 3. So the frame number is 3, which means 3 into, again, 3 into 2048 plus 452. Okay, this is your physical address. So if you do this, you will be getting 6596. Okay, very easy question, isn't it? So see, you don't have to remember anything. Okay, you just have to apply your brain that okay, this is logical address. Page number makes sense if you divide, because every page is in a multiple of page size. So if you divide by the page size, then you will be getting the page number. And offset also makes sense if you take the remainder. Right? Now, will you believe me that this exact, I mean, edit is this question only. I just write in the short form. This question is basically GATE 2024 question. And people were not able to solve this question because they were just remembering by hearting the formulas. And we solved these kind of questions way before than GATE has asked this question. I mean, we have been teaching this since the starting of the Go classes. Go classes started in 2021. We are teaching these concepts since 2021. These concepts mean like paging. Everyone is teaching paging, but people generally forget in the decimal format how to deal with these things with the first principle. Actually, we will deal with the binary, and people just remember the binary things. Okay, because that has been asking GATE also asked this decimal system kind of thing very first time, and only I can say only few people were able to solve this question. Those either have watched Go classes lectures, or they were already very much familiar with the first principles. Okay, so this question was asked in GATE 2024. But we have been teaching this decimal format. Like we generally start the paging from the decimal format only. In fact, to the proof, like I can say that the similar question, the decimal kind of question, we have asked in test series in 2022 or 23. I mean, before GATE, we have already asked these kind of questions in our test series. And no other test series had these kind of questions before GATE. Okay, before GATE 2024, but we already had these kind of questions, and GATE asked after the 1 year we have put this question. So maybe I can just show you some proof. Probably I will be having those screenshots. Yes. See, in January 2023, we asked this question, and this is the similar kind of question where I'm asking that in the decimal format. In the decimal format, this address is given, and we are asking to the physical address. And then I have commented also that we had included this question way back in 2023, and to my surprise, almost every student who attempted this test, I'm talking about the test, okay, at that time found it puzzling. I was surprised too because it was such a simple question. Later, I realized that students were not very familiar with the solving problems using the decimal notations. And now comes the pleasant surprise. GATE 2024 features a question based on the exact same decimal concept. Okay, so this was the link. The interesting part is that, to best of our knowledge, no one before GATE 2024 had focused on this type of question, and goclasses was the first to introduce such conceptual problems in its test series. Okay, so Gate has asked the same type of questions just a year later. Okay, so by the way, I hope you understood that how things are working with the very first principle. Now we will see things in binary because binary makes things very easy, and computer systems always prefer binary, right? I mean, our computer store everything in binary, and we don't have to even divide or take the mod, or which means reminder, in the binary. It's very easy. Okay, I mean, actually we have to do it, but we don't have to do it. Okay, so it's like that. I mean, it's automatically given. See, let me just give you a little bit of hint. Let's suppose if I ask you, okay, let's suppose this is the number. If I ask you that if you divide this number, okay, by 10, by 10 or by 100, or 10 is power, let's suppose 10 is power 2, 10 is power 3, or something, by 10, then what is the remainder? You can easily say, okay, 3. What is the quotient? This. I mean, this is directly served. If we have decimal number and we are dividing by 10, then this is directly served. Similarly, if we represent this in binary and if we divide by 2 power, then also it is directly served. So we will just see this. Okay, I hope you are getting my point, that decimal is the basic first principle, that how we should understand it. And later on, people realize that, okay, things are actually very easy in binary, and it is favorable to us also because computer systems are preferring binary. Okay. So let's just see this, that how to do it in binary. So let's have a small detour. Okay. So we will first understand small things, and then I will come back to the paging or the logical address, physical address, these kind of terminology. Let's have a basic division first. Suppose this is some number, okay, and suppose I want to divide this number by 10. I want to take the remainder. Then obviously 8 will be the remainder. Here, if I divide by 10 as power 2 or 100, then 38 will be the remainder, and similarly 538 is the remainder. That's very easy to call, right? Now suppose I do the same thing, okay, same number, same thing, everything is same, but instead of 10, I ask you 2, mod 2 power 2, mod 2 power 3. Then is this directly very easy? I mean, mod 2 is easy because you might say it is even number, so that is why it is easy. I mean, mod 2, you might say it is easy. But is this easy for 2 power 2 or 4? Is this easy for 2 power 3 also? Let's just check. Actually, things will become easy if I just represent this number into binary. Okay. So suppose I represent this in binary, and now I ask you the same question, mod 2 power 2, mod 2 power 3, right? Then it is actually very easy. See, earlier, in case of 10, this is the remainder and this is the quotient, right? Similarly, this is the quotient, this is the remainder, this is the quotient, this is the remainder, right? Now, if you represent in binary, and then if you ask 2 power, for example, 2 power 1, 2 power 2, 2 power 3, then this is the remainder for 2 power 1, this is the remainder for 2 power 2, this is the remainder for 2 power 3. This is the quotient for 2 power 3, and so on. Okay, this is the quotient for 2 power 3, something like this. So yes, reminder is very easy, 0, and then it is 1 0. I mean, these are obviously in binary. This number is binary, these are in binary. If you want, you can convert to the decimal. Okay, and then 0 1 0. In decimal, it is 2, it is 2, it is 0, right? In decimal. So finding the remainder is actually very easy if you represent in binary and if they are asking for 2 power, right? See, in our case of paging, we have to divide by the page size, and page size is always in 2 power. It will be 2 power p. Okay, it will be always in 2 power. So I will tell you. Okay, it will always be in 2 power, and given the address will be always in binary, and then you can easily say that, okay, this is the quotient, which means this is the page number and this is the page offset. Okay, so this is the reminder, and if I just ask you the quotient, whatever the quotient, the remaining part is actually quotient. Okay, so here this is the quotient, right? And in this case this is the quotient, like that, right? So remaining part is quotient. So I hope that is fine to everyone. So last 4 bit is the remainder if you divide by 2 power 4. Left part, so basically this left part is quotient and right part is remainder. So this is quotient and this is remainder. This is very easy, right? That's all I wanted to convey. So basically in case of decimal, if you divide by the 10's power, then it is easy. But in case of, if the number is in binary, okay, see, like currently I am writing like this, but assume that you have already number in the binary, right? If you have to represent in the binary, then the whole purpose is lost, right? I mean, instead of doing that, you can directly do 7538 mod 8, right? 7538 mod 8, it might be little easier, mod 8. Okay, instead of converting to the binary, you can directly do mod 8. Probably it will be easier. But suppose you already have the binary version, then in this case, if you divide by 2 raised power, then it is actually very easy. So for example, suppose you have some number 0 1 0 1 0 0 0 0 1 0 1 0 0 0 1 1. Okay, suppose this is the number which is represented in binary. Now if you divide this number by 2 raised power p, then you can say, let's suppose these are the p bits, then you can say this is the offset, or this is the remainder actually. Okay, currently let me just call it remainder, and this is the quotient. Okay, so like the similar thing I already told you. So this is the quotient and this is the remainder. So this is the quotient, this is the remainder. I hope that is fine to everyone. Okay, these are the p bits. Now, can you relate it with the logical address? Suppose the logical address in binary is given to you. Okay, suppose this is the logical address, right? Then what will you do? If the page size is 2 power p, then you will say that okay, this is the offset, which are the least significant p bits. This is the offset, and this is the page number. Okay, because the quotient is page number, right? Okay, so whatever size they give you, let's suppose they say that logical address space is 2 power k bytes or something. Okay, logical address space is, let's suppose, 2 power k bytes, or generally they say k bits. Okay, k bits, which means in terms of byte, you can tell that okay, if it is needing k bits to represent, then in terms of bytes it will be 2 power k bytes. Okay, if the system is byte addressable. So basically, if it is k bits, then total is k bits. Logical address space total is k bits. Out of that, p bits will be used for the offset, and remaining bits will be used for the page number. By the way, in the binary, if I just ask you, let's suppose 101, okay, some number. Can you tell me, by looking at this number, this is in binary, okay, in binary. Can you tell me, looking at this number, is this divisible by 2? Is it divisible by 2? Then you can say yes, because the remainder is 0. If you divide, then the remainder is 0. So yes, right? Is it divisible by 2 raised power 2? Yes, because here also the remainder is 0, right? So yes, this number is also divisible by 2 raised power 2. Is it divisible by 2 raised power 3? Then also yes, right? Because this is also 0. So yes, right? Now, is this divisible by 2 raised power 4? Then no. Why? Because this is not 0, right? This is not 0. So no. So basically, you can also tell whether this number is divisible by some 2 raised power 2 raised power 1, 2 raised power 2, like this, right? If the number is in binary. Very easy. If you give this number in the decimal, then probably there are some other methods. Okay, some other divisibility rules or something. But in binary, if you ask 2 raised power, it's extremely easy. Okay, just like in decimal, if the number is given and they ask you 10 is power. So binary makes things very easy, right? If the divisor, okay, of this number is in 2 power. So you can understand like this, that we are right shifting. If we are dividing, then we are right shifting, then this part get truncated, which is the remainder. Okay. And the quotient is basically how many times we are dividing. This is the quotient. It's like right shifting. Okay, anyway, so don't worry about it. So basically what I'm saying, that if you have any number, and if they ask you what will the remainder if you divide by 2 power 4, then these are the 4 bits. This is the remainder, this is the quotient. Okay, this is the remainder, this is the quotient. I hope that is fine to everyone. That's very easy, right? Quotient and remainder. And they ask you in the decimal, then you can convert to the decimal, but in the binary it is extremely easy to tell the quotient and remainder. For example, if you divide by 2, this is in binary is this. So this is the remainder, 2 power 2, then this is the remainder, which is actually 10, which is equal to 10 in binary. And then 2 in the decimal. So the conclusion is that if you divide by 2 power p, last p bits are the remainder, and the remaining bits, okay, remaining left bits are the quotient. This is true for any integer n in binary. Okay, if you have any integer n, if you represent it in binary, last p bits are remainder if you divide by 2 power p. That's very easy. So let's see this question. If a number n is divided by 2 power p, what happens to the bits? So answer is actually given. Lower p bits from form a remainder, remaining form a quotient. Okay, that's easy question. That's why I have already written the answer. So A is the answer. So this is just end of detour. Very easy detour. I hope you understood, right? Now let's solve this question. Suppose they say a computer system has uses 16-bit logical address and the page size is this. Logical address is basically this. Okay, for some particular logical address, which is this, which is of 16 bits actually, like 1 2 3 4 4 into 4, 16 bits logical address I have. One of the logical address is given to you. Now they're asking page number and offset. Earlier we used to have this, and then we used to deal with these messy calculation, right? But suppose you directly have in binary, can you tell me page number and offset? So offset will be last 12 bits, because if you're dividing by 2 power 12, then the remainder will be last 12 bits with offset, and then the page number will be, this is the offset, and this is the page number. So 4 bits are the page number. Okay, page number. So you can say 4 bits are the page number, the number of pages will be 2 power 4, which is 16. You can easily see that why, because 16 bit logical address means, like if you're representing 16 bits, then 2 power 16 bytes of logical address will be there. Actually you don't have to convert from here to here, because now we will be dealing with the binary, but just for telling you, this is the size of logical address, right? 2 power 16 bytes. So 2 power 16 bytes is the size of logical address. And page size is 2 power 2 into 2 power 10, right, which is actually 2 power 12 bytes. They have already written this. Okay, 2 power 12. So again 2 power 4 number of pages. So you can find number of pages from here also, and from here also you can find how page number has only 4 bits. Okay, that's how you can find out. See, let me just tell you what it is happening. 16-bit logical address is given, so you will first make a box of 16-bit. You will say that, okay, suppose this is 16-bit, and then you will divide this box into 2 parts. Okay, so that's how we will be solving all the questions. I'm talking about currently logical address. You can do same for the physical address. Okay, depending on the page size. I mean, here also we will use the page size. So here the offset, this is the offset, which is 12 bits, because page size is 2 power 12. Okay, so this is the page size. Based on the page size, I can easily find out the offset. Offset, last 12 bits will be offset, right? And this is the page number. Starting 4 bits will be the page number, which means 2 power 4 pages could exist. And if let's suppose offset is 12 bits, which means the page size must be 2 power 12. Okay, vice versa, it is always vice versa, which means if I can represent offset using 12 bits, means like page size must be 2 power 12, because offset means how much down I can go, right? How much down I can go. So if these are represented by 12 bits, which means 2 power 12 possibilities I must be having to go down. So 2 power 12 must be the page size. Okay. Now similarly for the physical address, you can say for the physical address, logical address is given to you, right? So the offset will remain same. So you will directly copy this offset. This is like copy paste. Okay. You whatever, I mean, they will give you some logical address. For example, this is the logical address. So for this logical address, you will just copy the last 12 bits, right? Last 12 bits will get or it is copied in this case. Okay. So till this point, you will as it is copy. So just a second. Yeah, till this point you will as it is copy here, right? But you will not copy this. You will not copy this. This is the page number, but you need the frame number. Okay, so you will not copy this. So what will you do? You will use a page table, right? So whatever is the page number, currently the page number is 3, right? 0010. Okay, you will use the page table and you will get the frame number. And from here you will get the frame number that you will directly put. And that's how very easily by the concatenation you are getting the physical address directly. See, earlier if you remember, to get the physical address we have to do little bit of multiplication. Okay, see, earlier if you remember, we have to do little bit of multiplication, which is something like this. Let me show you. See this, right? To get the physical address you have to add offset and then the frame size or the page size into the frame number or something, right? But here in the binary, I mean, the things are exactly same. Okay, there is no difference, right? I mean, if you just think in terms of the binary, you will be getting the same thing, and similarly vice versa. Like things are same, but it is just that things are easy in binary. Okay, here also indirectly what you are doing, frame number you are having, right, into multiplied by this 2 power, I mean, how many bits are these, because it's like a shifting on the left, right? So if you are shifting on the left and then you will be multiplying, I mean, if you convert that to decimal, then frame number into 2 power 12 plus this number which is offset, right, plus this number which is offset, because frame number into 2 power 12 will be basically frame number and then all zeros, right? I mean 12 zeros basically, which is left shift, and then plus, then you have to add this, right, offset. So basically earlier I was doing something like this, multiplication and then plus and all, but here it is very simple concatenation. Okay, so for physical address also you can divide into offset and frame number. Offset you can directly copy, but frame number you have to get from the page table. That's how you will be getting the physical address. I hope that is a little bit fine. So basically for this, if the okay, they are asking the page number and offset. For this is the page number and this is the offset, right? Very very easy. Why that is the case? Because page size is 2 power 12. Since it is given in binary, that's why 12 bits offset. This is page number. Very easy. Okay, so let's just see more questions. Suppose this is the next question. Suppose they say page size is now 2 power 10, page number and frame offset. So this is 2 power 10. So page number, so this is offset and this is the page number, right? Page number is 3 and offset in decimal you can find out, but there is no need. So basically I can say this is offset and this is page number. Okay, so for this question this is the answer. So to sum up all the things, I can say that if logical address is n bits, okay, and page size is, let's suppose, 2 power k or 2 power p bytes, right? In that case, there will be, let's suppose if it is 2 power k, then k bits will be page offset and remaining bits will be page number. Okay. So you can split. This is called split of logical address. This is called splitting logical address. So split of logical. We will see the questions, but currently I'm just telling you, okay, here, that we have already seen the questions, but we will see more questions. So this is the split of logical address, and this is the very important slide. Okay, generally I don't write this line, but when I write, I mean it. Okay, so this is very important slide in whole paging. You should be know, you have to know that how to split the logical address, okay, or the physical address. I mean, if it is a instead of logical, if I say physical, then nothing will change. If I say physical, then instead of page, I will say frame. Okay, that's the only thing. And frame number we generally get from the page table. This is the very important slide. So if you see this particular diagram, that's the job of something called as MMU, okay, memory management unit. That is a part of operating system. So you can say this is a job of operating system. So basically what it does, CPU is generating logical address. This is the logical address. This is getting divided based on the page size, okay, into two parts. Then offset is directly being copied, and this virtual page number or logical page number is getting converted to physical page number or the frame number. PPN means physical page number. This is a virtual page number. Okay, so it is basically getting converted to page number, and then you are going to have your offset. Okay, and this thing ultimately is your physical address, and you finally get using the physical address, you finally get basically the particular byte that you are interested in, which means first you will go to the page number. This is the page number, or sorry, the frame number. You will go to the frame number, and within the frame, how much down you need to go, it will be told by the offset. Okay, so I hope that is fine. This diagram is fine to everyone. Even if it is not fine, don't worry, because this is going to be clear in next few slides using the questions. We will just clear it using the questions. Okay, but I hope you're getting my point that logical address has to be split into two parts. Using the page number, you get the frame number, and you just append the frame number and the offset. You directly have the physical address. Don't have to do all the division, all the multiplication, anything, right? Very easy. Just replace here the frame number, you have your physical address. Okay, so let's solve this question. What this question is saying, suppose the logical address is this, I mean, this is basically logical address is space. Okay, this means space. Okay, again, this is also means space. So logical address space is, let's suppose, 256 kb, which is 2 power 8 is 256 into 2 power 10 is k bytes, right? These are bytes. So which is 2 power 18 bytes, which means it must be 18-bit long. And what about the physical address? Physical address is basically 2 power 6 into 2 power 10, which is 2 power 16 bytes, which is basically 16-bit long, right? So logical address is 18-bit long. So you can say logical address here 18-bit, right? Now since page size is given as 2 power 2 into 2 power 10, which is 2 power 12 bytes. So you can say that 12, okay, from here 12 bits are used for the offset. So these are the 12 bits which we will be using for the offset, right? And these are the 6 bits which are for the page number. And since 6 bits are used for the page number, so you can tell the number of pages. How many? 2 power 6, very easy. Number of bits in page offset, number of bits here is 12. Number of frames, number of frames you have to tell using the physical address. There is no other way. So just split the physical address also. I mean, the offset will be anyway 12 bits offset. Okay, since the total is 2 power 16, this is 16, so remaining is 4. So frame number is having 4 bits, which means 2 power 4. 2 power 4 are the number of frames. Okay, now let's see the last question, which is little more interesting. What they are saying, if each page table entry size is 2 power p bytes, then size of the page table. So basically they are saying that see, the page table is generally, so this is very first question related to the page table, so that is why you might be finding it little tough, but don't worry, you will get to understand in this video itself. Okay, so basically page table have all the entries for the pages, like page number 0 is in which frame, so these are all the frame numbers. So anyway, basically the number of entries basically same as number of pages, right? Number of pages, this is same as number of pages. So how many pages you have, by the way? You have 2 power 6 pages, so 2 power 6 entries you have, and then they are saying that each entry size is 2 power p. Okay, so basically you have 2 power p plus 6 size of page table. They are asking size of page table. This is the common question that we will be asking again and again. Okay, because actually size of page table leads to the multi-level paging. We will see how, right? I mean, I will motivate multi-level paging, but for now let's just see the single level paging. So basically here in the page table there are number of entries are basically same as number of pages, and each entry size will also be given to you, and based on that you can find out the size of page table. You just multiply both, you will be getting size of page table. See, again it is just an aptitude, right? So let's solve more questions, probably you will be more clear. So let's just take this question. What they're saying, a 20-bit logical address system has a page size of 4 KB. If a page number is this, construct a logical address whose offset is this. So they are giving the offset, okay, and then they are giving the page number, right? They are just asking you to find out the logical address. I think that's easy, right? You just need to concatenate these two. Okay, so just take this, right, and just take this. Just concatenate these two, and this is your answer, isn't it? So the answer is very easy. So this is your answer, which is the logical address, right? I mean, the same question but in the reverse. Let's see this question. A system uses this. Okay, if a logical address is currently this, what will the next logical address that lies exactly at the beginning of the next page? This is little interesting question. So what they are saying, that some logical address they are giving you. Okay, they are saying what is the next logical address. See, next obviously plus 1, right? And plus 1 means this will be 0 0 0 0 0 and 1 will be here. This is the next logical address. uh, but uh, but they are not interested in the next, which is like numerically next. Okay, they are saying the next which is lying exactly at the beginning of the next page. So by the way, what is the offset here? See, what is the offset here and what is the page number? If page size is 1 KB, you can say 2 power 10, right? So 10. So I can say this, right? This is the offset, right? So 0 1 1 0 and then 1 1. This is your page number, I can say. Remaining is your offset, which is 0 0 1 1 1 1 1 1 1 1. Okay. Anyway, this is your offset. 8 bits, right? Sorry, 10 bits. And 6 bits is your page number. So this is your page number. This is your offset. So now tell me, what will happen? See, in this page, within this page, there are many, there are, you can say, many, bytes. So how many bytes are there? Depending on the offset. So offset is 2 power 10 bits. So 2 power 10 bytes are there. How? So you can range. See, you can say that, okay, 0 1 1 0 1 1, right? So this is your page number. Within this page, okay, you can range all the zeros. So you can take all the zeros. All the zeros till all the ones, right? Till all the ones. So this is 0 0 0 0 1, like this, right? So you can say these many bytes are there within this page. Now don't worry about the offset. They're asking you the next, for the next page, what is the beginning address? Okay. So beginning address must be having offset 0, and the page number will be the next page number. So it's very easy question. So what you need to do, you can just increment the page number. Don't worry about the offset for now. You can just increment the page number, which means just plus 1. If you do the plus 1, then you will be getting what? You will getting, this is basically 3, you will getting 4, so which means that 0 1 1 1 0 0. This is the next page number, right? This is next page number. And what should be the offset? The first address must be having, it must be divisible by the page size, or anyway the offset must be 0, okay, for the first address. So this is your answer. Have you understood this question? If you have understood this question, then you actually got to understood, you got to know all the meaning, that what is happening, what is not happening. I mean, all this binary and all. You actually felt it. Okay. Which means that you completely understood if you understood this question. See, see, whatever is the logical address given to you. Let's suppose 10100111. Okay. And then let's suppose 101100. Okay. Whatever is the logical address given to you. First find out what is the offset. Let's suppose this is offset. Okay. This offset is actually only limited to that particular page. In the sense that if they ask you the next page, then in that case you just increment this number, right? You just increment this number. Offset doesn't matter. In this page there are many possibilities of offset. You can write any number here, doesn't matter. Let's suppose they ask you, tell me any address which belongs to the next page. Okay, so let's suppose the question is, tell me any address which belong to next page. Then you can say fill your number here, I mean any number. Okay, any so basically this is 1 2 3 4 5 6 7 8 9. Okay, so any 9-bit number you can write. Okay, so this is the next address. Okay, any address of I mean any address which belong to the next page. So I hope you are getting the point. See, this thing should be, very much easy for you, because generally students find these things very difficult. Gate has not asked much of this. Okay, Gate, I'm not saying that Gate has asked much of this. Okay, tell me the next address and all. But sometimes they give you addresses. Generally they don't write binary, because binary is too long to write, so that's why they prefer to write in hexadecimal. So sometimes they will give you some addresses, then it will be too much panic for you, okay, if you don't understand this basic. So the basic thing is that you just find out the page number, and don't worry about the offset can keep on changing. Okay, just increment the page number, right? So I hope you understood this, right? So basically, given the logical address, you should be very comfortable that okay, this is the page number, this is the offset. This offset may range from 000 to all the ones, then but the page number will be same. Okay, what is the first address on this page? The first address will be all 0. What is the last address in this page? Last address in this page will be all the ones. Okay, and everything is in this page only. I hope you understood. So now let's just solve this question. A computer system has 32 bits of logical address space and page size of 4 KB. 4 KB means 2 power 10, 2 power 2 into 2 power 10, which is 2 power 12 bytes. Find the required bits for the offset. Offset will take 12 bytes, 12 bits, right? If page size is 2 power 12 bytes, so I can say this will be the division. This is 12 bits offset. And out of this 32, remaining 20 will be your page number. This is 20 bits. Okay. Now let's see this question. The similar kind of question they're asking. So this is 2 power 6 into 2 power 10, which is 2 power 16. So 16 bit logical address you have here. And then they are saying this is 2 power 11, 2 power 11 bytes. So basically 11 bits will be your offset. And remaining 5 will be your page number. So how many pages will be here? 2 power 5, right? Offset 11 bits, remaining 5 will be your page number. And how many pages? 2 power 5 pages. In any page, let's suppose this is one of the page. Okay, so there will be all the zeros to all the ones. There will be many bytes could be there in this page. So as I told you, this is very, very important slide. So I hope now you understood that given the page number, we can easily find out the using the page table, we can find out the frame number, and that's how the things are being done in the operating system, right? Okay, question, generally they ask question related to this, that okay, divide this into two parts, or in multi-level paging, three parts, four parts, like this. Okay, that's very, very easy actually. So so basically, we technically call this as offset, but this is kind of, I mean, all of these numbers are actually offset only. Offset in the sense that offset tell me that how much down I need to go, right? This is the same, right? This is virtual page number, this is also telling me how much down I need to go, kind of this, right? I mean, this is also kind of offset. Okay, that how much down I need to go, this is the, technically we call this as offset, that okay, how much down I need to go. But here also, whatever is this number, this is telling me the page number, which means okay, one page number 0 1 2 3, like that, how much down I need to go, right? Kind of the offset. Okay, anyway, but technically this is offset. Okay, now let's see this question. In this question they are saying virtual to physical address we need to convert. Okay, and page size is given as 1024. So virtual address is this. If you tell me so basically 697 is there. If you tell me page number, then it will be 0. If you tell me offset, actually this is the decimal question, don't worry about the binary here, this is completely decimal question. This is 697. So page number 0 has been mapped to frame number 3. So basically 3 into, the answer will be 3 into frame size is basically 1024 plus 697. Okay, what is the answer here? Here the page number will be 1. Page number 1 has been mapped to the frame number 10. So this is again 10 into 1024 plus in this case offset will be 30. Here the page number is 1. Page number 1, again the page number is 1, which has been mapped to the frame number 10. So this is again 10 into 1024. Okay, plus the offset is anyway 0 here. Okay, plus 0. So these are the answers. Okay, again this is a decimal question, but the thing is that I hope you are comfortable both in the decimal and binary. They rarely ask related to decimal, but you should be actually very, very comfortable in the binary. Okay, now we will be solving more questions which are morely about the gate questions, and which will be mostly these questions are related to the binary only. Okay, and I hope till now the things are easy, and after these questions your confidence will be very high that okay, you know the things. Okay, let's solve this question. So this question has been asked in gate 2015. Let's see what this question is asking. So they are saying consider a system with byte addressable memory with 32-bit logical address. So let me write here, your logical address space is 32-bit, which means you will be having 32-bit of logical address, right? Now 4 KB page size means, like if page size is 4 KB, which means 4 KB, which means 2 rows power 12 bytes, right? So which means offset will be, you can say 12. So 12 is offset, and page number will be taking 20 bits, right? So number of pages will be, you can say 2 power 20. The size of page table in system. So they are asking size of page table. So see, in this case, you need to know how many entries will be there in the page table, right? So let me just tell you that how many entries will be there in the page table. It will be actually equal to number of pages, right? So I can say that number of entries in page table is equal to number of pages, right? And how many number of pages are there? 2 power 20, right? So you will get 2 power 20 entries. So basically you will get 2 power 20 entries, right? And each entry so they are saying page table entry of 4 byte each, right? And each entry is of 4 byte, right? This is like page table entry size. Okay, So that is why this is the whole thing is page table size. So let me just tell you that the page table size will be page table size equal to number of entries in it and into size of each entry, these many bytes, right? Because this is the size of each entry, so which is 2 to the power 22 bytes, or in other words, if you tell in MB, so you can say that this is 1 mega, so it is 4 MB, right? So it is 4 MB. Okay, so 4 must be the answer. Let's just see 4 is the answer. I hope you got this question. This is easy question, and I hope it is completely fine to everyone, right? Now let's move to the next question. So, by the way, in this question, there was nothing hard, nothing easy. Like, it was very usual kind of question. They're just asking the size of page table, which you can find out by the number of entries in the page table multiplied by size of each entry, right? Very easy. Just kind of aptitude kind of questions. Let's just see this question, which has been asked in GATE 2016. So, what they are saying? Consider a computer system with 40-bit virtual addressing. So now virtual address or logical address both are same. So virtual address, we are saying this is 40-bit. Okay, so now currently it is like 40-bit long. Now they are saying the page size of 16 kilobyte. So they are saying the page size is also given to you, which is 16 kilobytes, right? Which is same as 2 to the power 4 into 2 to the power 10, which is 2 to the power 14. So 14 you can say will be your offset. Okay, now remaining will be basically 26. Now what they are saying, computer system has one level paging per process. Each table entry requires 48 bits. Now they are given in the bits. The size of page table again they are asking. So number of pages will be 2 to the power 26. Similarly, number of page like entries will be this much, and each entry is of 48 bits, right? Let me just convert it to bytes. You can divide by 8 and it will be 6, right? So it will be 6 bytes. So you can say it is into 6, right? So in terms of megabytes, it is 2 to the power 20 into 2 to the power 6 into 6. So which is 64 into 6 MB, right? 64 into 6 MB, which is uh, 6 into 4 is 24, and then 6 into 6 36 and 38, right? So 384 MB. So 384 MB is the correct answer. I hope you understood. Again, this was the similar kind of question. Okay, great. So this is 384. Now let's just move to the next question. Okay, so let's now see some other page table entry information, which means that in page table entry, how does it look like? Like for example, you have a page table where you are storing, right, the frame numbers. So for example, you are storing the frame numbers. Are we storing something else also? So for example, suppose this is corresponding to page 0, this is corresponding to page 1, and so on, right? And so on. So this is corresponding to page 0, the frame number. So I'm writing the frame numbers here. Okay, so whatever is the frame number, I will be writing here corresponding to the page 1, page 2, and so on, right? Now along with the frame number, we also write few other information. Okay, like for example, valid bit, whether this particular entry is valid or not. Okay, which means whether this page is currently in the main memory or not in the main memory. I'm not going much in the detail here, but only thing I'm trying to tell here is that there are other things which are also getting stored apart from the frame number. I mean, the frame number is the main, which is taking the largest amount of space or the most number of bits. So for example, you are storing, let's suppose, frame number using 10 bits. I will come to this part. Okay, but suppose you are storing generally it is, let's suppose, using 20 bits, right? Then in that case, I mean, if you are storing using 20 bits, then there will be 3 4 or 5 bits or 6 bits for other things also. Okay, but the frame number is the dominant one, and then there are other things like valid bit, protection bit, dirty bit, and so on. So for example, this is the frame number, then valid, read write, present, reference, dirty. So these are the other information which is either 1 or 0. This is also present in the page table entry. Okay, so along with the frame number you are also storing something else also, right? I mean, which is basically the other information. Now suppose they ask you this question. So they are saying that in a virtual memory system, size of virtual address is 32 bit. Okay. So again, you have to split the virtual address. So let's suppose this is 32 bit. This is virtual address space, and similarly, let me write the physical address space, which is 30 bits. Okay. So here it is 30 bits. Okay. So this is 30 bits, and this is 32 bits. Now 4 KB is the size of page table. Sorry, size of each page table, and page size, right? Page size is 4 KB. So which means this is 2 power 2 into 2 power 10, which is 12. Okay. So 12 here you will be writing as an offset, page offset, and the frame offset, right? 12, which is page offset and frame offset. Here the remaining thing is basically you will be getting 18 here. Here you will be getting 20, right? So this is the page number. This is the frame number. Okay. Now let's see what they are asking. The main memory is byte addressable. Which of the following is the maximum number of bits that can be used for storing protection and other information in each page table entry? They are saying that page table entry size is 32 bits. Okay. So now let's just understand this bit more carefully. See. So let's just go to the next page, right? So basically here we are saying that page table entry size is 32 bits, right? 32 bit page table entry. Now what does this mean? It means that in the page table, the whole entry size, this whole entry, this is corresponding to page number 0. So here you have frame number and other things also, but the whole entry size is 32 bit, right? Now you see here that you are going to store the frame number and other things. Can you tell me that how many bits are required to store the frame number? This is very important. Okay, once you answer this question, the entire question will be answered. So the main question here to answer is that how many bits are required, to address any frame, or of required to store the frame number, something like this, right? To store frame number. See how many frames are there. 2 power 18 frames are there, or in other words, frame number is basically uniquely identified just using 18 bits, isn't it? Okay, so you just need 18 bits here. So you can say that frame number is uniquely identified using 18 bits. So here you can write that frame number is uniquely identified using 18 bits. So that is why using 18 bits you can store any frame number. So 18 bits are required for the frame number, for frame number, and remaining bits you can use for other purpose. So how many bits you can use for other purpose? 32 minus 18, it will be 14, right? So 14 bits you can use for the other purpose, let's just see the answer. So basically 14. Is this understood to everyone? So first we need to understand this, then I will just tell little more detail about these things. See, the whole point here is that how many bits you need for the frame number. Since there is like 18 bits only you need for the frame number, which is always determined by the physical address space. I mean, it depends on the physical address space, right? If it is too big, if it is, let's suppose, too big, then obviously you need more bits in the frame number. Okay. So basically what is happening here is that, see, this question is solved. Okay, this question has 14 answer and everything is solved, and you can solve any other gate question related to this concept. Actually, I'm covering all the gate questions which are related to paging concepts, right? But this question is solved, but I want to make sure that you understand this idea very clearly. Okay, see, what does this mean? This 18 and 12, what does this mean? Okay, let's just understand this very clearly. So here you have 18 bits for the frame number and 12 bits for the offset, frame offset, right? So tell me any frame number, how would it look like? I mean, it will be some 18 bits, maybe let's suppose 100, okay, some 18 bits, right? Something like this, right? Suppose something like this. Okay, these are, let's suppose, 18 bits. This is how any frame number will look like in binary, right? Any frame number will look like this, right? Now here, if you append all the zeros, this is the first address. So you can say if you append all the zeros, then this is the first address in that frame, right? So let me just write it here. All the zeros means if you append, okay, if you append, so let me write like this. Basically, this is the empty space, and if you fill this empty space with all the zeros, this is the first address in that frame, and if you have all the ones, then this is the last address in that frame, right? I hope this is clear to everyone. Now tell me, suppose you have your physical memory, okay? Suppose this is your frame, right? Suppose, for example, here you have just for the sake of simplicity, let's suppose you have four frames, okay? Maybe let me draw the four frames, one, two, three, four. Now you can see this is frame number 0, this is frame number 1, this is frame number 2, this is frame number 3, or in other words, in binary you can say this is, you can just give it a 0 0 0 1 1 0 1 1, right? And here it could be the entire story. I mean, you can have it, each frame could be as long as you want. So basically, let's suppose there are like 10 more zeros, okay? 10 more zeros means starting address, and 10 more ones means last address, something like this. It could be any story, right? Now, what I mean to say that you just need these two bits. So suppose if I just ask you, let's suppose 01 is your frame number, right? I mean, this is this frame number. And if I just append 10 zeros, which is the starting address, okay? Let's suppose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Which is the starting address in this frame. Now, is this also, can I also use this particular thing as a frame number, something like this? I mean, instead of just 01, what I mean to say that can I append all the zeros, and instead of saying that, okay, this is the frame number, I can say like, okay, this is the, I mean, instead of giving the frame number, can I give the first address in the frame number? Yes, I can give, and later on I can just ignore this, right? I mean, I can give, let's suppose, some other address in the frame number, and I can say that, okay, from here you can extract. See, what I mean to say that you can even have the 32-bit or whatever is the logical of whatever the physical address, right? This is 30. So you can have entire 30 bits as a frame number. I mean, you can have all the zeros, or you can have any address here. You can say, okay, from here you can find out the frame number. But that's not the best way. See, what I mean to say, I will be very clear, don't worry. Okay, I will be making myself very clear here. What I mean to say that if you have, okay, it doesn't matter how long your physical memory is. If you have four frames, you just need two bits, okay? So within that there could be many addresses. You don't have to give this whole thing, and you don't have to say this is the frame number, okay? For the frame number, this two bits are enough. Are you getting my point? So it depends on the physical memory and the size of the frame, right? Now let's suppose there's a physical memory. Now let's just consider very different case. Okay, suppose this is physical memory. Now in this memory, since it is a universe of, all, I mean, this is the only reality, right? I mean, logical memory is there, but this is the only real existential memory that we have, right? So suppose if I ask you that I want to store, let's suppose this is 30 bit or 32 bit, doesn't matter, okay? Let's just assume this is 30 bit. Suppose in this memory I want to store something. Okay, I mean, need not to be page table, something. Okay, just one of this. It's not like I have many such things. I have, let's suppose the problem statement is like this. I have just one of uh just one, you know, you can say a piece of block, which is piece of block, which is, let's suppose, 2 power 20 bytes. Okay, 2 power 20 bytes, or it could be any bytes, doesn't matter. Okay, suppose see, now it will be very interesting and I can, let me just warn you, it is like little bit optional discussion. We will come back to this in multi-level paging in one of the question, but currently I'm just taking it as little bit of the optional discussion. Suppose there is one chunk that I want to store. There is some block which is basically of 2 power 20 size. Okay, suppose this is 2 power 20 size block. I want to shoot. I have just one of this. I don't have many of this. I have just one of this. Okay, only and only one of this. And it's not a page table. It's not a process. It has nothing to do with the paging. Suppose it has nothing at all to do with the paging, because physical memory is the only existential memory, and here I can store. I mean, where like whatever I need in the main memory, I can load it to the main memory, right? Suppose I want to load or I want to store this into the main memory here. Suppose. Now, what will happen? Okay, so this is going to be very interesting. See, suppose I want to store this here. Now, what will happen? See, I can definitely store it anywhere, right? Now, but before storing this, I will assume. Okay, that's interesting. That before storing this, I will assume my main memory or the physical memory has been divided into this size, which is 2 power 20. So before storing this, assume main memory or the physical memory, both are the same thing, is divided into 2 power 20 size. So basically totally it is 30 bits. So you can either have, I mean, like this is 30, and so offset will be like 20. Okay, because the like block offset will be like 20. Okay, and then 10 bits are remaining, something like this. Okay, like either you can do like this or you can do like this. Okay, 2 power 30 is the total size and 2 power 20 is one of the size, so there will be 2 power 10 such blocks can exist, right? Such blocks. See, I have only one block. Okay, but there can be 2 power 10 such blocks may exist here, may exist. I'm not saying that I have 2 power 10. I'm just saying that there could be 2 power 10 such blocks may exist. Okay, now if someone asks me that that what is the, address of this block, like, so I will ultimately store it somewhere, right? But before storing this, I will just assume that my physical memory is divided into 2 power 20 size of blocks. Okay, 2 power 20 size of blocks, and I will store this as in one of the block. So so basically I can say, I will assume that physical memory or the main memory is divided into 2 power 20 size, right? Each block, and I will store my block or my piece of code into one such. So I think the block term might be confusing here. So what I was using the term, just one piece of block. Okay, my piece of block basically into one such block, right? Okay, so should I be calling it frame, one such frame? So my block, or let me just call it my block into one such frame, or like, I mean, this will be divided into 2 power 20 size each frame, or I mean, you don't get confused between blocks, right? I hope that's fine. So basically what I'm trying to say, that this is your main memory. It will be okay, assume that it has been divided into 2 power 20, I mean 2 power 20 such no, like each block size is, or each frame size is 2 power 20. Now I will load this into one of this. Okay, so how many such can exist? 2 power 10 can exist. 2 power 10. So if someone asks me that how many bits you required, okay, how many bits you required to address your block, then only 10 bits. Why? Because see here I told you that if there are like four frames or four such partitions are there, okay, if four such partitions are there, then you just need 2 bits. Doesn't matter how big the first partition, I mean how big each partition is. So basically, if 2 power 10 such partitions are there, okay, 2 power 10 partitions, I will assume that these many partitions has been done. Okay, if 2 power 10 such partitions are there, in that case, I will say that okay, uh, that this is like my block is going to lie in one of the partition, into one such, basically you can say partition. Okay, so I will assume that physical memory is divided into 2 power 20 size of partitions. Okay, let me use the word partition. Partition is a good word. Size of partitions, and I'm going to store in one such partition. Okay, so how many bits are required to address my piece of block? 10 bits, right? Because there could be 10, 2 power 10 partitions, and I will be storing in one such partition. Okay, see, in reality, physical memory is never divided into, I mean like there is no hard boundary or something like this, right? I mean I'm not going to divide it. It is just the abstraction. Okay, I just say that okay, if whatever I want to store, even if I want to store integer which is having 2 power 2 size, let's suppose, okay, which is like just a 4 bytes, I will assume that it has been divided into 4 bytes of chunk. Okay, 4 bytes of chunk, and this is going to sit into one of the partition. Whatever I want to store into the physical memory, I will assume that physical memory has been divided into that size. The reason is that because I want the starting address, okay, to be aligned with this size. I want that this starting address is divisible by the size whichever I'm storing. Okay, see here, you can say whatever is the offset, which is 20 bits are offset, right? So you can say 20 bits here, 20 bits are 0, I mean last 20 bits are 0. Here also last 20 bits are 0. Here also last 20 bits are 0. So basically everywhere last 20 bits are 0. Okay, and then this partition number, or you can call it frame number, will keep on changing. The frame number will keep on changing. So basically the point here is that physical memory get never in reality it never get divided, but whatever you want to store, just assume that your partition, okay, the physical memory whatever you have, assume this partition is based on whatever you want to store for the physical memory. Okay, even if you want to store integer, assume that it has been divided into 4 bytes each. See, if you study computer organization and architecture, COA, right, computer organization, there we have cache memory topic. Now we say that there are like lines and blocks, right? I mean we divide physical memory. Okay, so or the main memory, let me write physical memory into blocks. We say something like this, right? Into blocks. So CO is saying, I mean if you really believe that we are dividing, then aren't these two things are contradicting? That COA, cache memory topic, is saying that okay, we are dividing into blocks, but operating system paging topic is saying we are dividing into the frames, right? So we divide physical memory into frames, right? So which do you think is correct? Operating system point of view is correct, or COA point of view? I mean, are we dividing into the blocks or we are dividing into the frames? In reality, we are not dividing. I mean, we are not actually hard divide. It is like whatever you want to store, assume that it has been divided into that size. Okay, and then we store that in the physical memory. Now, if you want to understand it little bit more, then you can understand like this. That see, this is the physical memory, right? The good thing about the physical the computer system is that everything is in the 2 power. Okay, so suppose you want to store 2 power 20. Okay, then you assume that okay, 2 power 20 size, each is 2 power 20 size, right? Each is 2 power 20 size. So this is 2 power 20 size, this is 2 power 20 size, this is 2 power 20 size. Okay, Now, obviously, you are not going to fill the whole physical memory. Your required things will be getting in one of the partition, or maybe multiple partition, doesn't matter. So let's suppose this in this partition, this partition. I mean, you are not going to occupy the whole physical memory. Okay. Now, suppose, I mean, you may occupy. That's not an that's not an issue. But I'm trying to explain you something else. Now, suppose later on you want to store something of size 2 power 10. Okay, just forget about paging, forget about cache memory, everything. Just forget about it. I'm just saying that how it is working. Suppose sometime you want to store something of size 2 power 20. Then you say that okay, you're dividing in 2 power 20. Now, suppose you want to store of size 2 power 10, then you will say, okay, you are dividing into 2 power 10 size. Now, how these two are basically working together? See, the good thing is that both are in 2 power. So basically, if you divide in 2 power 10 size, right, then there will be I think 2 power 10 such partition in each this 2 power 20. So basically, what I mean to say that it will not be conflicting, or it will not be like this. See, what I mean to say that here it will not be the case that this 2 power 10 will be basically one of the 2 power 10 will be taking some part of this and some part of this. It will not be the case. I mean, basically, there are like 2 power 20 divided by 2 power 10, so it is not 2, it is not 4, it is 2 power 10. Okay, so basically you will be getting 2 power 10 such partitions. What I mean to say that you will be getting 2 power 10 such partitions right here in 2 power. So it is not like that some part of 2 power 10 is here and some part of 2 power 10 is here, and if you store it in it here, then how you are going to make sure that okay, this is going to fit in address aligned with the 2 power 20. So the good thing here is that this later on, whenever this 2 power 10 comes, it is not going to make things worse for this 2 power 20. Or suppose 2 power 22 comes later on, okay, I mean bigger than this, okay, suppose 2 power 22 comes, then it will take more than one block. Let's suppose 2 power 21 is coming, then it will take two blocks of 2 power 20. So it is also not the case that it is starting from here and it is basically like this, right? It is also not the case. So basically, if everything is in 2 power 20, then everything is working very smoothly without even you notice it. Okay, there won't be any problem in the address alignment. So address alignment is very important. Don't worry about all of this. What I'm trying to say here is that whatever you want to store in the physical memory, you assume that you are dividing the physical memory with respect to that size. Okay, and it will work like a charm. And this is how the reality works. Okay, so let me just write it, that whatever you want to store in physical memory, assume that physical memory also got divided into that size. Okay, this is like a I can say the most important rule, or this is how the things are working in reality. Okay, so this is how things are working in reality. So I hope you are getting my point, that what is happening here. Okay, so if there is a little bit issue, then don't worry. Okay, you will get to understand over the time. So but you just remember this, that whatever you want to store in the physical memory, assume that physical memory have been divided into that size. Okay, that's all. Now suppose coming back to this question, suppose you want to store um okay, so basically in the page table entry, we want to know the frame number, right? So frame number will be basically of 18 bits, because I just need 18 bits to uniquely identify the frame number. Even though if I have 30 bits, can I know the frame number? Yes, but 18 bits are enough, okay, to uniquely identify the frame number. Now suppose the frame size is something else, or I mean it will depend like how many bits I need. Suppose the frame size is, let's suppose 28 bits. Okay, frame size itself is taking 28 bits. Then how many such frames can exist? So there will be there will be basically two, right? Two. So you just need 0001, like there is just two bits are needed to uniquely identify the frame number. Okay. Cool. So now let's just solve this question. So this question is saying a computer system uses a single label paging scheme for the address translation. The virtual address space of the process consists of 1024 bytes. So basically, which means 2 power 10, right? So virtual address space 10 bits. Okay. Out of it, 9 bits. Okay, sorry. Out of it, page size is 8 bytes, which is 2 power 3, right? So basically 3 bits are offset, 7 bits are page number. And the physical address consists of 512 bytes, which means let me write the physical address also. So the physical address space is 9, and then 3 are taken for the offset, and the 6 bits are for the frame number. Physical address space. Now they are saying page table entry requires 2 bytes of storage. See, 6 bits you definitely need for the frame number. 2 bytes means like in terms of the bits, 16 bits, right? 16 bits. So remaining 10 bits you may use, or you may just nullify or whatever, right? I mean, you may use for the other information. That's fine. That's not an issue. But let's just see the question. They are saying find the range of possible values. So suppose this is the page table. In the page table, you store the frame numbers, right? You store the frame numbers. So these are the frame numbers. Point to the frame number. Okay. So these are the frame numbers. So they are asking what are the possible values of these AIs. So since there could be 2 power 6 frames, okay, which is 64 frames could be there. So the possible values could be 0 to 63. I mean, here in the page table, you will be writing, I mean, this page 0 is, let's suppose, getting loaded to frame number 62. Page 1 is getting loaded to some other frame, let's suppose frame number 0. Page 2 is not even getting loaded to anywhere. You can say it is invalid, right? Invalid, let's suppose. So basically, these entries, either it is invalid, or if it is valid, then it will be 0 to 63. Okay. So that's how you can solve this question. So what is the answer? A is answer, right? A is answer here. Have you understood? So they are just asking that what will the these numbers. They are not asking that how many bits. How many bits of these numbers will be there? 6 bits, right? 6 bits of these numbers. 6 bits of these numbers. 6 bits of these numbers, and the values could be 0 to 63. Very, very easy question. Okay. Now let's go to the next question. So they are saying consider a machine with 64 MB physical memory and 32 bit virtual address space. So they are saying this is 2 power 6 into 2 power 20, which is 2 power 26, right? Physical memory. So the physical memory, you can say physical address space is 26. Virtual address space is 32. If the page size is 4 KB, which means 12, right? Which means 12 here, 12 offset is 12, 20 is remaining here, and here you are remaining 14, right? Okay. What is the approximate size of the page table? Okay, this is interesting question. In the page table, how many entries will be there? First, you need to find out the number of entries in the page table, and then multiply it by the page table entry size. So the number of entries in page table, how much it will be? So how many entries will be there? Number of pages, right? Equal to number of pages, which are 2 power 20, right? And size of each entry, it actually has to be minimum 14 bits. I mean, you have to store the frame number and other things you can store, right? So it has to be minimum 14 bits. So this is like minimum, right? So basically you can multiply these two, right? If you multiply 2 power 20 into 14, they're asking approximate. So let's just assume like it is minimum 14, it could be 16, right? I mean, let's just assume if it is 16, just in nearest 2 power. So it is basically 2 power 24, or in terms of the MB, it is 16 MB. Okay. So it is 14, basically it is 14 So but you can say this is same as, I mean almost same as 2 power 20 into 16, which is 16 MB. This is page table size, right? Okay, I hope you understood. So actually in this question, I think this they should specify. I mean, it could be 24. Minimum it should be like this. I mean, it cannot be 8 MB, it cannot be 2 MB, but it could be 16. It could be 24 also. But what is the approximate size of the page table? It's better if they specify that the minimum approximate minimum size. Okay, something like this. Okay, it's better. Otherwise, the closest answer is 16 bits, 16 MB. But I hope you understood the point that in the page table entry we have the frame numbers, right? In the page table entry we have the frame numbers, and the frame numbers depend on number of frames. Okay, these many bits. How many bits we are going to use for the frame number? It depends on number of frames. Okay, this is the page table entry. Great. So yes, so answer is C. Just a second. 2 power 20. Okay, sorry. This is oh my god. I just made a you know blunder, I can say. So basically, it is in the bits, right? I mean, this is in the bits. So that's till this point it was fine. But since it is in the bits, now you have to convert into the bytes. So it is just 2 bytes. Okay, two in terms of the bytes. So basically, it is 2 MB. Yes, then I think this makes sense, like 2 MB. So basically, C is the answer, not A. Okay, C is the answer. That was interesting because the option A was 16 MB itself, right? But yeah, C is the answer. So let us now take one example of a process. Suppose that a page size is 4 KB and logical address space is basically of 32 bits. Okay, so this is your logical address space, which is of 32 bits. And from here you can say this is 2 power 12, right? 12 bytes. So 12 is basically offset and 20 is your page number, and this is your page offset. This is your logical address space. That's how it is getting divided. Okay, now page table entry is of 4 bytes. Now they're asking page table size, so you can say number of entries 2 power 20 into each is 2 power 2 bytes, so it is 2 power, or maybe you can say 4 MB. This is size of page table. Okay, very easy question, but why I'm doing this question at this point in time, you will get to understand. Now, just assume that you have 4 MB of the page table, and with this setup, right? Now let's just see. Suppose in reality, let's suppose you write some program which is suppose looking like this. Now this program will typically will load it into the physical memory, but before that you assume that there's a logical address space, and the program has its own logical address space, right? So you are going to store this code in the static area or something like this, right? I mean, ultimately this particular program, the stack will not grow more than 20 bytes, and heap will not grow more than, let's suppose, 4 bytes. Ultimately this program is going to end up almost 50 bytes only. Okay, almost 50 byte only. So you notice one thing here, that the program is just 50 bytes, but the page table, or the 35 bytes, doesn't matter, basically it is in bytes, right? But the page table size is 4 MB. So it means that index table index table is bigger, far bigger, right? Not just bigger. Actually the program is very small, still the page table is huge, right? Is far bigger than book itself. Don't you think so? Index table is far bigger than book itself. So basically, why it is happening, let me tell you. That see, you are going to have this logical address space, and then you know that most of these are never going to occupy, right? And then you will fill, or you will basically load these pages into the physical memory, which is fine. But how does the page table work? So that is how the page table will look like. So which means this entry, this the first entry, which is zeroth entry, it will tell you where is page 0, right? Where is page 0? Which means where is this page, right? Where is this page? Like this is page 0, this is page 1, page 2, page 3, like this, right? So this will tell you where is page 1, this will tell you where is page 2, this will tell you where is page 3, and so on. For example, this is some page, let's suppose page number 10. So there is some entry, let's suppose this is entry number 10. Okay, so this will tell you where is page 10. But since currently this particular page is not allocated, so I will say it is invalid, right? I will say it is invalid. Similarly, I will say that all of these pages are not allocated. So I will say all of these entries are invalid, right? So basically, since the entries are not allocated to, since the pages are not allocated to any frame, or there is no data here, so that is why I will say these all entries are invalid. Okay, so I hope you understood. Now these entries are too much. Okay, as I told you that page this particular process will not be using most of this area. So you can say these entries are basically, you can say 99.9% entries are invalid. Okay, most of the entries are invalid. So I hope you got the point, right? I mean, it may be 99%, or maybe 99.5%, but for most of the programs or most of the processes, most of the entries are invalid. Now, now I hope you got the setup, right? So page table size, I told you, is basically 4 MB, which is too big. And can we store? Yes, we can definitely store this page table. It's not an issue. But the thing is that you are storing something, okay, which is having too many invalids. I mean, let's suppose you want to store some array, okay, and I mean array or page table, whatever you say, and there are like 99% entries in this array are basically null. Okay, see, the page table is huge. That's fine. But why it is huge? You are just storing null. I mean, most of the time. Okay, you are just storing null. So I hope you're getting the problem. See, the problem is that there are too many entries which are null, right? There are too many null entries in page table. Hence you can say, hence we end up storing too many nulls in memory. Okay, so this is the problem. So we end up storing too many nulls in memory, and obviously, right, and obviously we don't want to do it, right? Is this fine to everyone? So, and obviously we don't want to store so many nulls, right? So this is a problem. So can you tell me the solution? See, just think about it and let me know what is the solution that is coming to your mind. That we want to store the page table, obviously, right? We want to know that where this page 0, where this page 1, and at the same time we don't want to store these nulls. So what is the solution? See, whatever solution you suggest me, okay, whatever solution you suggest me, it should be scalable in the sense that the moment, let's suppose this heap grows or this stack grows, okay, the moment, let's suppose this heap is growing, this will become valid, right? And then it will start pointing to that particular page. So basically, the moment heap keep on growing, like let's suppose heap is growing, so these entry will keep on becoming valid, right? So your solution, whatever you suggest me, it should be scalable in the sense that if a heap or a stack grows, then you can make the invalid entries as valid. Okay, and then it should be so smooth. So just think about the solution that should be so smooth, and it should be very good solution. What do you think could be the solution? So the solution name is actually multi-level paging. Okay, so this is the solution that we are going to implement: multi-level paging. Okay, how it is solving, I will just come to the part. But all I can say is that it is very clever idea, which can make the whole thing very smooth and very scalable. So I can say it's very nice idea, right? Very clever idea to store page tables such that such that you don't have to store too many nulls. Okay, it is very clever idea such that you don't have to store too many nulls. But what is the idea? How this works? Let me just tell you. The idea is basically, it says that divide the page table itself. Okay, it says divide the page table itself into multiple parts and store each part independently of each other, right? So basically you can say, and store each part, you can call it part or you can call it, let's suppose, chunk or each smaller page table, whatever you like to say. Okay, so basically it is saying that what you do, you just divide into multiple parts and store each part independently. So basically it is saying that you divide the page table into multiple parts and we will be storing each part independently. Then how it will help? How it will help? Just think about it. So basically it is saying, or in other words, basically you can say you divide the page table itself into multiple parts and and not store, let me write in this way, not store the parts or the chunks which have only invalid entries. Okay, this is the idea here. So which means what we are going to do, this is the page table, we will be dividing this page table into multiple parts. So what we will do, we will say, let me just divide this into multiple parts. Okay, so the page table itself will be divided, right? That's why the name is multi-level paging. So now once you divide the page table, then it will look like this. I mean, this is one of the parts. See, it is just the same page table which is like this. Okay, the same page table where I'm just saying that let me just divide this page table into multiple parts. Okay, so this like this, right? Now what will I do? I will say that since I have divided into multiple parts and I can store each part independently, so I will not store this at all. I will not store this at all. This is the idea. So I will not store the parts which are having only invalid entries. Okay, so I will not store the part which are having basically invalid entries. That's the idea. Okay, and now since we are dividing and we are independently storing, that's why we have to maintain one more level of accounting, which means we should be doing that where I'm storing this, where I'm storing this, like this, right? So we should be having one more level of accounting. Okay, and that is why the name is saying that it is multi-level paging, which means I will divide the page table also, right? What is the reason? Because the moment I do this, I don't have to store all of this. Okay, these are too many. Okay, these are too many. So basically I will say this is basically telling me where I'm going to store this particular part or this particular chunk, or you can also call it page table. See, these are the smaller page tables. Okay, I mean, these are also the page tables, but these are the smaller page tables. It is just like that. See, suppose you have one eraser. Okay, eraser. Now if you just divide this eraser, then this is also eraser, right? I mean, this is also eraser, this is also eraser, this is also eraser. So these are erasers only, right? But these are just small erasers, you can say like this, right? So these are you can call them page tables. Okay, there is no problem, you can call directly page tables, right? Page tables, these are page tables. Okay, so sometimes I call them page tables. Page tables is a very correct and very accurate name, no problem. But sometimes I call them like parts of the page table or chunks. Okay, something like that, right? I will make sure that you get things very clearly. Don't worry. So the idea is clear to everyone that we are going to divide the page table itself into multiple chunks, okay, or multiple parts or multiple page tables, right? And then I'm going to store them independently. And I will say let's not store this at all, and since I'm not storing this at all, that is why I will say that okay, let's suppose this is pointing here, and since I'm not storing this at all, so I will say this entry is invalid, right? This is invalid, invalid or null. Okay, because I'm not storing this whole thing. This entry is also invalid because I'm not storing this thing. Okay, and then let's suppose this is pointing here, and similarly there are many other entries which are invalid. So what is happening, don't worry, I will just make sure that everything is clear. So basically what is happening here, that I will store these, I will store this, and definitely I have to store the outermost. At outermost there is always, okay, always there is no division. At outermost there is no division. I mean, if you want, you can divide it. Okay, if you want, you can divide this also, and then you can have one more level of page table, but this is not then outermost, right? Then outermost will be this one, right? I mean, whatever is outermost, there will be only one page table at that outermost level. So you can even write it that at outermost level there is only one page table, right? Okay. So I hope you are little bit getting that what we are trying to say. So we are saying that that we are dividing the page table into multiple parts, and we are going to store them independently, right? See, for a moment, let's not worry about the valid, invalid, and these things. Just assume that you have this kind of setup. You have this page table. Now, suppose just aptitude or just a simple question I'm going to ask you. Suppose there is a memory or there is some data that is basically, let's suppose, I think these were, if I remember correctly, this was 10 and this was 22, right? So okay, these are 2 power 22 entries. Okay, so suppose these are 2 power 22 entries. Now suppose I divide into chunks or smaller page tables, and I call these smaller page table. Let's suppose this is each smaller page table is having 2 power 10 entries. Now can you tell me the number of such smaller page tables or number of chunks? Can you tell me? Easy question, right? 2 power 22 entries total, each is having 2 power 10, so that's why 2 power 12 chunks. Okay, or 2 power 12 smaller page tables. Okay, I mean, technically, you directly call them page tables. I'm calling it a smaller, just to make sure that you don't get confused. Okay, I mean, a smaller page table means after the division. Okay, you can definitely call directly page table. I mean, a smaller and greater, these are just relative terms, right? A smaller with respect to what or something, right? So a smaller, I'm just saying it casually. I mean, it is not any official term. Okay, official term is page table only. A smaller page table is just some unofficial term, or just to make sure that you understand what I mean to say. Okay, so how many such smaller page tables or how many such page tables will be there? There will be 2 power 12 such smaller page tables, or let's just call them chunks or whatever, right? So these many page tables will be there. I hope that's fine, right? So if I divide, let's not worry about this invalid and all. Okay, just assume that you don't know that whether there are invalid, valid, you don't know about it, and suppose you don't care. Like I just mean to ask that if you divide, then in that case, do you think that there will be any difference at this level? I mean, are you magically disappearing some page tables or some chunks? No, right? I mean, there is no disturbance you are doing at this level. You are just having one more level. Okay, so there is kind of no disturbance you are doing here. Okay, there is kind of no disturbance you are doing here. You are just creating one more level. I hope that's fine, right? It is just that we will choose not to store them. We will choose not to store them. Okay. So, like, things are very simple here. We are just saying that it was like here, it was initially one page table. Let me just divide into multiple page tables. And then once I divide, I will store them independently, and I will not store which is having only invalid entries. Then how does this whole setup work? I mean, how it is scalable? Let me just tell you. So basically, the moment this heap grows, okay, let's suppose it is growing further, then this will be valid. Okay, this is valid. The moment one of this valid, okay, the moment, let's suppose it is growing by one page, okay, the moment it is growing by one page, then it will be valid, right? The moment it is valid, then this will also be valid, and I will say it is pointing here. Okay, then let's suppose it is now growing one more page, then this is valid, then this is valid, and if it is keep on growing, if it is growing too much, then this will also be valid, and in that case this entry will be valid, right? I mean, if at least one of this is valid, then immediately it will be valid. That's how it is scalable in the sense that you can
There is no restriction with respect to the memory you can use. You can use as much as memory you want from this logical memory. Okay, it will be just like that. I just need to mark valid or invalid. Okay, the moment I mark valid, then I will be storing this in the main memory. I don't have to store all the page tables at the same time in the main memory. These things will come later, but yeah, the thing is that you can mark this valid, which means that now it is basically pointing to, this page, okay, wherever it is stored, okay, in the physical address. So hope you are getting the point. See, the whole idea here is that I don't want to store these invalids. Now, one thing that might come to your mind, that I don't want to store this invalid, but ultimately I am having the invalids here also, right? See, that this is true. I mean, we are not completely getting rid of the invalids, but we are reducing the number of invalids a lot. Like for example, like these are, you can say these are, I mean, let's suppose that each of this is 2 power 10 entries, right? So these are 2 power 10 invalids, right? Because 2 power 10 entries in each. Okay. And instead of storing these 2 power 10 entries, I'm just storing, or instead of storing these 2 power 10 invalids, I'm just storing one invalid. One invalid. Okay. Which means I'm kind of having the, I'm kind of saving the storage, or I'm kind of saving the page table size by the factor of 2 power 10. Which means roughly speaking, I'm just roughly speaking, okay, we will be calculating the exact size which has been reduced using these page tables. In fact, in gate there has been many times they have asked this question, that how much size is reduced using a multi-level page table. In gate 2014, very recently, they've asked minimum and maximum number of pages and all, so which are basically, I mean, related to this concept only, like how much saving we are doing, right? How much saving we are doing with respect to multi-level paging. That's how, I mean, these kind of questions they have asked many times on gate. I can say 7 8 times they have asked. Okay, that how much saving we are doing. We will be doing the calculation very accurately, but currently I'm just roughly speaking that in this case, by the we are saving by the factor of 2 power 10, or 2 power 10 is basically 1024. So I can say we are saving by the factor of 1000, right? We are saving by the factor of 2 power 10. Okay, or in other words, you can even say that earlier it was 4 MB. Earlier means basically single level page table or flat page table, right? Flat page table. So you can say earlier it was 4 MB. Now, which is like two level page table, right? I mean, you have two levels here. Okay, so two level page table. Now it is like page table, it is kind of, okay, I mean, not exactly I'm calculating, it is just just to give you the bit idea. I'm just saying that I'm basically having 4 MB is basically 2 power 20, by 2 power 10, by the factor of 2 power 10 I'm saving. So it is 4 into 2 power 10, which is like 4 KB, right? Okay. So earlier it was 4 MB, now it is just in KBs. Yes, I mean, there will be some like 4 KB size of this, or some size of this. So basically maybe 8 KB, or like if you add this also. But yeah, it will be actually in KBs, right? Earlier it was in MBs, now it is in KBs. So how much we are reducing? We are reducing with a factor of 2 power 10, which is a huge reduction, I can say. Have you understood what I'm trying to say? So basically, we will not be storing them, and instead of storing each 2 power 10 entries here, I will just say invalid here. Just one invalid, right? And the moment it is valid, yes, I will make this valid, right? I mean, it is scalable also. There is no problem in this. But I don't want to store these many invalids unnecessarily, right? Okay, hope you understood the concept, a little bit concept, like why we are doing the multi-level page table, multi-level paging, right? So basically, let me just write it, that why we are doing multi-level paging. So just try to write down by your own, instead of me writing it. Like obviously I will be writing it, but instead of me writing it, just take a pause. Okay, pause this video and try to write down what by your own, that why we need multi-level paging. So basically, the idea here is that we don't want to store, you can say, nulls, right? We won't want to store nulls, hence we can divide flat page table into smaller page tables, and we choose not to store smaller page tables which are having only nulls, right? Smaller page tables which are having only nulls, right? That is why we need multi-level paging. Is this okay to everyone? I hope that's fine, right? Now there is one more reason, like I will come to that, but before that, I will just reveal one of the major, I can say, misconception. Okay, misconception that a student has. Okay, so one of the major misconception that a student has. This is basically, I can say, that in whole gate preparation, in whole gate computer science preparation, this is one of the very popular misconception that students has. I mean, they do not know this is misconception, but they think that this is actually a concept. Okay, the misconception here is that, suppose there's a page table which turn out to be 4 MB in this case. Okay, so page table which turned out to be 4 MB in my example. Okay, and then let's suppose there is a physical memory or the main memory, right? Let's suppose this is main memory, right? Suppose you want to fit. Okay, the misconception is that, suppose you want to load or you want to store this page table into the main memory. Let's suppose this is a 4 GB. Okay, then the misconception says that we cannot store this page table directly. Okay, which means we have to divide this. Okay, I mean, this is kind of misconception. First tell me, is this true? Is this true? See, the misconception is that, let me first explain the misconception. Misconception says that if you want to store this page table into the main memory, okay, even though the main memory size is too big than page table, then still we cannot divide, and we cannot, I mean, load, or we cannot basically store this page table into the main memory, right? And they think it because the reason behind it is that, because you have already divided the main memory into 4 KB each size of frame. Okay, since you have already divided the main memory into 4 KB size of frame, then how can you fit some bigger than 4 KB into the main memory? Okay, so according to them, that anything that you want to store in the main memory should be either equal to 4 KB. I mean, ideally should be equal to 4 KB, or it is lesser than 4 KB. I mean, you cannot store something bigger than 4 KB directly. So this is what they think. Do you really think this is true? No, right? I mean, in reality, so basically you can say, in reality we can definitely do it, right? We can definitely. So this is the misconception, but let me write the reality. So in reality, definitely we can store, right? We can store page table of size 4 MB directly. I mean, it is our choice basically. We, if we want, we can store directly. If we want, we can divide it. If we don't want, we don't divide it. I mean, it is just like a choice of two people. I mean, this is the page table, this is the memory. Where is the frame is coming into the picture, right? I mean, the where is this 4 KB is coming into the picture? You just want to store some data into the main memory. I mean, you just want to load the space table into the main memory, and you can definitely do it. I mean, where is this 4 KB frame is coming into the picture, right? That is just for the address alignment. I mean, in reality, what happens, as you already know, right, that we just divide. I mean, for the purpose of address alignment, which means that we should be basically storing at such location where each of the locations should be divisible by this size, which is 4 MB. Which means, in other words, or simply saying that you can divide. Okay, so divide into 4 MB each size, and there are many slots and just fit into one of the slot, right? So basically you can directly fit into one of the slot. I mean, if you want, if you don't want, you want to divide, then you can divide also. I'm not saying you cannot divide, but if you want, then we can directly fit, right? So we can directly directly uh, fit, or we can directly store in one of the slot, right? Which is 4 MB each size, divided into 4 MB each size slot, right? So we can directly load into one such slot, right? So this is the reality. But students think, many students think that we have already divided into 4 KB each size, then how you can load such bigger page tables? So that is why you have to, okay, you cannot store directly. So the misconception is that you have to divide page table, and that is why the multi-level paging, they think that multi-level paging is kind of forced. Okay, so the misconception here is that they think that multi-level paging is kind of forced. I mean, there is no choice but you have to do multi-level paging, because we cannot store directly. Is this forced? Tell me. No, right? Multi-level paging is not forced. It is our choice. So they think that multi-level paging is forced, which is wrong. I mean, they think, let me write it, they think. Okay, so then they think that multi-level paging is forced. Is this the case? Obviously no, right? I mean, it is our choice whether we want to divide it or we don't want to divide it. Okay, so we can directly store, for sure we can store. So the misconception here is say that we cannot store a large page table directly into the memory if we have already divided into the frames. The reality, we can store it easily and directly without dividing into smaller chunks. This is the reality. So let's just solve this question, okay, which is related to this misconception, and tell me what is the answer. So the question says a process has a page table of size 4 MB. The frame size is 4 KB. Which of the following statement is correct? So they are saying that page table size is 4 MB, frame size is 4 KB. Okay. It is not possible. It is not possible to store such a large page table directly. It is definitely possible, right? I mean, it is definitely possible. I mean, this is basically kind of false. It is not possible, so it is false. It must be stored. It must be stored contiguously. Contiguously means like without dividing, right? Without dividing. It must be stored without dividing. No, this is also false, right? This is also false. I mean, you can, if the answer is like you can, okay, you can store without dividing, then this is true. But it should be divided, then it is false. It can be stored easily by dividing. Yes, I mean, it can be stored easily by dividing. It can be stored without dividing. I mean, it is your choice whether how you want to store. Okay, it can be stored. Yes, this is true. The frame size must be increased to store. No, the frame size actually has no matter, no business, right? I mean, this is just to confuse you. Okay, now you cannot just increase the frame size. I mean, it is not necessary that you are increasing the frame size. Frame size is with respect to the original page, like I mean the data pages, like logical address you have divided into pages. So that is with respect to that. Frame size is with respect to that. Okay, so here you can say C is the answer. So basically the whole point is that you can store this page table into the main memory uh, in a way you want it, right? I mean, you want to divide it into smaller chunks, then you can divide it. You don't want to divide it into smaller chunks, then it is up to you, right? So how you want to store this page table into the main memory, it is completely up to you. Which means in fact you can say that you want to store it directly, you can. If you want to divide, then in fact you can say that we can divide in our choice of chunks. It is not necessary of 4 KB each. Okay, this is also another misconception. I mean, the same misconception, actually, not another, that they think that it has to be divided. First of all, they think, and the size of each division should be 4 KB. No, right? So we can store directly. Is this true? Yes, obviously we can store directly. We can divide and store. Yes, right? We can divide and store. Yes. This is also true. And we can divide into any size. If you want, we can divide into 4 kb, yes. If you want, we can divide into 8 kb each, yes. If you want, you can divide into 1 MB each, right? If you want, you can divide into 2 MB each. I mean, it is up to you how you are dividing. Okay, you can divide into any size. Is this fine to everyone? Okay, you can divide into any size. So this is also the misconception that students think that you need to divide into frame size only. I mean, the same misconception that they think that you have to divide and you have to divide into the frame size only. Actually, this frame size division is very popular. That is the reason of misconception. See, there must be some reason of misconception, right? The popularity doesn't mean it is the way you are doing it, right? I mean, it is the force way. No, it is not the force way, right? It is just popular that you are dividing into the frame size, but it is not mandatory. You can divide into any size. Okay, so see, the same misconception, basically they say that a 4 MB page table, I mean, this is just an example, 4 MB and 4 kb. So basically a page table must be divided into frame size. 4 MB, here the page table size is 4 MB, so 4 MB page table must be divided into 4 kb pages. Okay, so this is the misconception. Students often think that page tables must follow the same page size as data pages. In reality, OS can split the page table into chunk of any convenient size. It may be 1 MB, maybe 2 MB, maybe 10, sorry, maybe 8 kb, maybe 4 kb, like that, right? These chunks can be mapped separately. So basically, you will be dividing into a smaller page table, and those smaller page tables can be mapped separately. It doesn't have to match the data pages sizes, but it is just popular. So basically you can say by default, okay, if nothing is given in the question, if the question does not specify how the page table is divided, then by default assume that page table is divided into pages of same size as data pages, which means the page size. Is it just a default thing if nothing is mentioned, if they do not specify anything? But it is not the mandatory thing. They can definitely give you, okay, any division. For example, this is 10 and 22. Now they can divide this 2 power 22 entries into any division. I mean, they can put any number of lines, by the way, here, which means, let's suppose this is 5 5 5 6 7, anything. Okay, so 5 6 7 4, okay, anything. Basically this total has to be 22. Like these things will be covered later, but you can divide into any size actually. Okay, need not to be in the same size as page size. But if they do not give you anything, then in that case assume that they have divided into the page sizes. Okay, this is something. If they do not specify anything, then only you need to assume this. Understood? So let's solve this question. What they are saying: a 4 MB page table exists in a system with 4 kb pages. Which of the following is or are incorrect? So basically, it is MSQ question. They are asking incorrect. Okay, the 4 MB page table can be divided into 4 kb parts. They are saying incorrect. So basically, this is correct. I mean, you can divide, you cannot divide. It is up to you. The OS can divide into 1 MB or 2 MB. Yes, it is also correct. It must always be divided into exactly into 4 kb pages. No, this is incorrect, right? This is incorrect. Each portion of the page table must fit into a frame. This is the same thing like above. C and D are almost the same option. This is also incorrect. Okay, C and D are the same kind of options. I mean, they are saying that you must be divided into the 4 kb size. Okay, see these numbers, please don't worry about these numbers, 4 kb and 4 MB. This is just to explain the multi-level paging idea, motivation. Okay, whenever I'm saying 4 MB, it means I'm talking about the default example I have taken. 4 kb, I mean, these sizes may vary. Okay, these sizes may definitely vary, right? These questions, I've just wrote this question based on the example that we have, typical example that we have started with the, okay, for the motivation purpose. So now you have understood that why we want to do multi-level paging, right? I mean, the complete thing is obvious to you that we want to do it because we don't want to store the invalids, or we don't want to store the null, right? So why to store the entries corresponding to pages which are empty, which means invalid entries. So I can say this is primary reason, but there is one, I can say, side region, or one of the complementary region, or one of the small region is, I mean, there is one more region which you can say the second region. Okay, the second region. So there is one more region uh, which is not concerning about the invalid entries. I mean, even if all the entries are valid, then also the region is basically, you can say, there. I mean, it is not related to invalid entries. So you can say it is not related to invalid entries. So for this, like, let's, even if you assume that all are valid entries in the flat table page table, I mean the process is using too much of the space, then also it makes sense to divide. Okay, can you think about it, like why we still want to divide? Okay, apart from saving the space is one of the major reason, but can you even think about it, like what could be the other reason? See, we want to store this page table, right? So into the main memory. So basically, let me write the second region here. So I'm only writing the second region. The first region is obvious to everyone, which is to save the space. So second region. Okay. So see, the first region is clear to everyone. Now I'm just focusing on the second region. So second region is not related to invalid entries. It is just saying that suppose you want to store directly. Okay, then what is the small problem that you might be facing if you want to store directly? The problem is that we have to find out 4 MB space, which is contiguous in the main memory. I mean 4 MB empty space, right? Empty contiguous space. So if we directly want to store, so you can say if we directly want to store, then we have to find out 4 MB contiguous space, right? I mean 4 MB means page table size contiguous space. 4 MB contiguous space, which is empty, right? 4 MB contiguous empty space, you can say, right? 4 MB contiguous empty space in main memory. Okay. So this region is basically not related to invalid entity. It is just saying that we don't want to restrict ourselves for this. Okay, we don't want to restrict ourselves in finding the 4 MB contiguous space. Okay, so we don't want to restrict ourselves in finding 4 MB contiguous space. Okay, so that is the reason, like they are saying let's just divide it, and let's just divide it into smaller parts, and each store each smaller part independently, so that you don't have to restrict yourself to have the 4 MB contiguous empty space in the main memory. So what is the second reason? This is the second reason, which is saying it is not related to invalid entries. It doesn't care about invalid or valid entries. It is just saying that we may not find, okay, the contiguous space to store page table in the main memory. So I hope both the reasons are clear to everyone, that why we want to do multi-level paging. The first reason, which is primary, to save the space, and second reason, that we don't want to find out the 4 MB contiguous space. Even if we want to, if we don't care about the invalid entries, then also we don't want to restrict ourselves in finding the 4 MB contiguous space in the main memory, or we don't want to do it. So this is the motivation behind that why we want to do multi-level paging. So the why part is clear, I hope, to everyone, right? But obviously the mechanical part, like how to do it, is still left, and which is the major part. I mean, like how we are going to do multi-level paging. So let's now discuss the how part, that how we are going to do this multi-level paging. See, why we need it, I hope the motivation is clear to everyone. Now let's just see that how we are going to perform this multi-level paging. Okay, so just assume that see, this is, by the way, just kind of aptitude, so you will find it very easy once you understand it, so don't worry much about it. Let's go step by step. Let's assume you have some logical address space of 2 power 10 bytes. So suppose this is your logical address space of 2 power 10 bytes, right? So in single level paging, I was saying that you can do one thing, you can just divide. Okay, you can just divide this into pages, right? Okay, so let's just divide this first into pages. You can choose size of any page to be size of pages to be anything. So suppose here I'm saying a page size is 8 bytes. Okay, page size, suppose I'm saying it is 8 bytes. Now if you divide each into 8 bytes, then what's going to happen? You will be maintaining one page table. Okay, 8 bytes means like 2 power 3 bytes. So you will be maintaining one page table, and then you will get to know the number of pages will be 2 power 7. So in this page table, there will be 2 power 7 entries, isn't it? So this is a page table that you have corresponding to it. And now you know in this page table there are 2 power 7 entries. And that was the whole story of flat level page table or the single level page table. Now, for some reason, let's not worry about the reason, but for some reason, we wanted to go for the multi-level page table, right? So let's just see that how we can do this, or how we can implement the multi-level page table. So which means multi-level page table means that I have this piece of thing with me, okay, piece of block with me, and I want to divide this page table further into smaller, page tables or smaller chunks, right? So I will be dividing this, right? Now interestingly, this is very important, as I told previously also. Interestingly, uh, whatever size you are going to choose here, like, I mean, you can divide this page table into whatever size you like, which means that, see, the page size is 2 power 3 bytes, which is perfectly fine. But here the each chunk, so you can call it page table, but I'm calling it chunk, okay? Because sometimes the students get confused that we were calling the whole thing as page table, then this is small is also page table, and also they get confused that whenever I'm saying page table, I'm talking about the whole page table or the smaller page table or like that. So that is the reason I will be calling these smaller parts as chunks, okay? So I will call this a chunk, right? So here at this particular level, or at any level actually, like whenever you are dividing this logical address space also, we can call this as, instead of page, we can also call it a chunk. So at any level you can choose the chunk size to be anything, right? So let's suppose this is currently having 2 power 7 entries, and suppose I'm choosing chunk size to be, let's suppose, 2 power 4 entries. Okay, now notice here that I will be talking in the whenever I talk about the chunk size, I will be talking in terms of the size, in terms of the entries, okay? Because it will make things very easy to implement, or very easy to understand. See, I will not say the unit is bytes here, or I will not say the unit is MB, KB, or something like this. I will just say entries, okay? Just go with me and you will get to understand everything very clearly. So suppose I want to divide this page table further, such that each into chunks, such that each chunk size is 2 power 4 entries. Now, can you tell me, the very simple question I want to ask here is that, can you tell me how many entries will be there in the next level? Which means what I mean to ask, let me just repeat the question also. See, what I'm saying here is that you have, okay, so let's not worry about this text. So let me just remove this text. So you have a page table or some block, let's just call it page table, a page table of 2 power 7 entries. Now you want to divide this into chunks, each chunk, such that each chunk is 2 power 4 entries. So can you first tell me how many chunks will be there? Okay, so number of chunks or chunks means a smaller page table, but I will be calling it chunks. So it is 2 power 7 entries you have here, divided by 2 power 4, which means 2 power 3, which means 8 such chunks will be there. 1, 2, 3, like this, right? 8 such chunks will be there. So that is why you will be having in the next level, you will be having 8 entries, each will be pointing to one chunk. So here there will be 8 entries, or 2 power 3 entries here you will be having. Okay, so 2 power 3 entries, and that's how you are doing the multi-level page table. See, just understand this very carefully, that at this level I'm not disturbing anything. At this level things are as it is. I'm just saying that that there is one more, okay, there is one more level of accounting I'm doing, and that is maintaining the pointer to, like, I mean, I can store this into the physical memory, so that is maintaining the pointer to this smaller chunks, and that is all I'm doing. I mean, I'm not decreasing anything here, okay? So which means that if I just ask you that how many entries are here after the division, I mean at this level, then you will say still 2 power 7 entries. It is just that I'm dividing. Okay, I'm not doing any disturbance here. So just see here that I'm not doing any disturbance here. Disturbing. Okay, I'm not disturbing this. So I hope that is fine to everyone. Now if I choose the chunk size as 2 power 4 entries, then I can say that there will be 2 power 3 chunks, so there will be 2 power 3 entries in the next level. Now let's just do one more example. Okay, I will not call it question because I'm not asking you much things here. Let's just do one more example for the division. So I can say this is another example that how we are dividing, right? And then everything will make sense in a while. So another example how we are dividing. So suppose this time let me take it little larger. Probably let's suppose this is logical address space. Let's suppose it is 2 power 20 bytes. Okay, then you can divide into smaller chunks again. Okay, at this level we call the chunk as page, but that's fine. So I will be calling chunk. Okay, you can divide this into smaller chunks. Okay, so basically we call at this level we call it page. So let's suppose page size here, it could be anything. Again, let's suppose 2 power 3, 2 power 4. Let's suppose it is 2 power 4. Okay, or 2 power 5. Okay, suppose it is 2 power 5 bytes, right? See here at this level you can call it byte or you can call it entry, which means each entry just contain one byte, right? So see here you can say that okay, this is one entry or one byte, this is one entry or one byte, this is one entry or one byte. So it doesn't matter, right? And at the next level here, the each entry will be containing multiple bytes, so I'm just calling it entry, and the unit will be again entries. Okay, so anyway, so now you will be having a page table here for this particular division. Just tell me how many entries will be there in this page table. How many entries? So this is the page table that you have with number of entries equal to number of entries equal to 2 power 20, 2 power 20 divided by 2 power 5, right? Which is 2 power 15. So 2 power 15 entries you have here. Now you can say you have 2 power 15 entries. Is this fine to everyone? Okay, so you had your logical address space of 20 bits, right? So this whole is 20, and then because of page size this is 5, this is 15, right? That's what I'm doing. Is this fine to everyone? See, that's very easy. The first step one is to choose the chunk size or the page size. We call it page here. And then once you have it, you can just divide it. And then number of entries, there will be 2 power 15 entries. That's all, right? Till now, you already know the things. Now, let's just go to the next level, which means let's just divide this further. Okay, let's just divide this thing further. Now, suppose I want to divide this page table further, right? Now, you can choose any chunk size. Okay, I want to divide this into smaller chunks, suppose. Okay, smaller chunks. So, you can choose any chunk size, right? So let's suppose at this level I'm choosing chunk size to be, let's suppose you can choose anything, but let's suppose I'm choosing 2 power 6 entries. Okay, I will be writing entries. Okay, I mean you can later on convert from entries to bytes depending on what is the size of page table entry, right? You can convert this entry to byte. Later on you can do all of this thing, but currently I'm just calling it entries, right? I mean the unit should be entries so that it is very easy for us to do all the mathematics. Okay, so now you tell me, see, this is the first step. So I can say this is like step one, right? Step one is to determine, or in the question, they will be giving you the chunk size and so on. So I will also do the questions, some gate questions. Don't worry. So step one is to know what is the chunk size. Now what is the step two? Step two is that how many chunks will be there. That's very easy, right? So you can say the step two will be to figure out the number of chunks. So how many chunks will be there? Let's just figure it out. So number of chunks. Number of chunks. How many chunks will be there? 2 power 15 entries total. 2 power 6 entry in one chunk. So you can have 2 power 9 chunks. Right? Which means at this level you will be having 2 power 9 entries. Okay. So here you have 2 power 9 entries. Right? So you have divided 2 power 15 into 2 power 6, 2 power 6, such that you have 2 power 9 such chunks, which means at this level you will be having 2 power 9 entries, because each of this entry will point to one such chunk. Point to means like wherever it is going in the physical frame, it will tell you that where it is going. It will tell you this next entry will tell you that where it is going. This next entry will tell you that where it is going, and so on, right? I hope you are getting the point. So basically you are saying that this 15 has been further divided into two parts, which is like the offset or the chunk offset or the page offset. Basically this is in terms of entries. You always write 6 here only directly, okay, because it will make things very easy. So basically you will be writing 6 here, and the mathematics will work based on the number of entries, I mean the size in terms of the entries. So you can write 6 here and 9 here, okay. This was also like 2 power 5 bytes, but here or you can call it 2 power 5 entries, because each entry just containing 1 byte, okay. Here each entry might contain multiple bytes, but that's fine, okay. So if it is 2 power 6 entries, you can further divide. Earlier this was the setup, it is 15 and 5. You can further divide this into 9 and 6. Now if you want, you can even further divide it, right? So which means you can say that let me just further divide it, okay, which means first the step one is to choose that what should be the chunk size for your next division, okay. You can choose anything. See, here at this point in time I have chosen that, okay, chunk size is 2 power 6 entries. Now at this point you can choose any chunk size. It is not necessary that you have to choose the previous chunk size only, okay. So here you can choose chunk sizes 2 power 4, chunk sizes 2 power 4 entries. So that is why, can you tell me the number of chunks here? Number of chunks. It will be 2 power 9 entries divided by 2 power 4, which is 2 power 5, right? So which means there will be 2 power 5 entries here, because these many number of chunks, 2 power 5 entries, right? And each of this will be pointing to, so you are dividing this further, each of this will be pointing to one of this. And how many number of chunks? 2 power 5, right? Sorry, this is a 2 power 5. Yeah, that is fine. So basically 2 power 5 chunks are there, so each of this will be pointing to that where it is going in the physical memory. Understood? So that is how very easily you can perform the multi-level paging, which means instead of 9 you will be further dividing. Here the chunk size is basically 4, so 4 and 5, okay. That's how you can divide. We will tell everything about it in very good detail, okay. Just try to understand for next 5-10 minutes, and everything will be very smooth after 5 minutes. Great. Now let's just do one thing. Let's just try to have one more example. So this is one example, that let me just call it example 3, okay, or let me just call it just example. Suppose in this case I say that logical address space, suppose, is of 32 bits, okay. Now I want to divide this, okay. So suppose that you have 32 bits, so now let's just divide this into multiple parts. Suppose at this point in time I'm choosing, so this is 32 bits, which means 2 power 32 bytes will be the whole logical address space, okay. So size is 2 power 32 bytes, or you can also write entries, but let's just call it byte, because each entry you can logically say that just containing 1 byte, but that's fine, okay. So here at this level let's not disturb much, so we will not disturb our terminologies, okay. We are calling it page only at this level, so let's just call it page size. So page was okay, let's just change it little bit. So let's just suppose that page size is 2 power 10 bytes, which means it's very very easy, which means that we are dividing, okay. This is 10 and this is 22, we are dividing like this. That's very easy, right? Which means you will be having this 22 actually tells us that how many pages or how many page table entries. This will tell us that, okay, we will be having 2 power 22 entries here, because 2 power 22 pages will be there. So that is why here the page size, okay, in terms of the entries I'm writing, right? So page size, page table size, page table size is 2 power 22 entries, right? Now let's just do one thing. Let's just divide this again further into multiple parts. So let's suppose this time I'm dividing into multiple parts, and let me choose any chunk size. So I'm dividing into multiple chunks. So let's suppose chunk size in terms of entries, right? Chunk size, let's suppose 2 power 8 entries. So which means how many number of chunks will be there? So you can write number of chunks. It is 2 power 22 entries total, 2 power 8, which is I think 2 power 14, right? So you can say I will be having 2 power 14 such chunks, which means at the next level you will be having 2 power 14 entries, right? 2 power 14 entries. So here you have 2 power 14 entries. This is the page table size at this point. Page table size. Okay. And each of this entry will point to one such chunk. Each of this entry will point to one such chunk. Don't worry about the valid, invalid, these things. I'm just, making it very easy and making it, sure that you understand the aptitude part first. Okay. Then logically, or then basically you can relate it later on with the other things. But for now, just focus on how we are doing the division. So this 22 has been further divided into two parts. You can say that first is 9, because sorry, first is 8 and the remaining is 14, right? I hope that's fine to everyone. Now what we can do, we can even further divide it. Okay, nobody is stopping us to further divide, and each time we divide we can have any you can say we can have any size of the chunk. Okay, it is not necessary that chunk size should be equal to the page size and so on. Okay, so let's just further divide this into multiple parts. Let's suppose I divide it, and let me choose the chunk size to be anything here. So chunk size, let me choose again this to be anything, which is, let's suppose 2 power 10, 2 power 8 entries, right? 2 power 8 entries. So how many number of chunks will be there? Can you tell me? Number of chunks. Here, if you have 2 power 14 entries divided by 2 power 8, which means 2 power 6 entries. Sorry, so 2 power 6 chunks. So you will be having 2 power 6 chunks. So which means at the next level, you will be having 2 power 6 entries. This is the page table. You will be having 2 power 6 entries. Page table size is 2 power 6 entries. So basically further, you are dividing this 14 into two parts, which is like 8, because the 8 is the offset, right? 8 and 6. You're getting my point? And each of this, so here you have 2 power 6 entries, each of this will point to one such chunk. Each of this will point to one such chunk. And how many chunks are there? 2 power 8. Okay. See, don't worry, you will get to understand everything. Let me just go again with in this example. What we are doing, we had earlier this flat level page table 22 and 10. Now I'm dividing this 2 power 22 entries further into smaller chunks. So let's just choose the chunk size to be 2 power 8 entries. Then if I do it, then there will be 8 offset, and then there will be 14, which means 2 power 14 entries this side, right? And why that is the case? Because 2 power 14 chunks will be there at this level. And then you can further divide this, right? You can further divide this particular thing into 2 power 8 chunks, and chunk size to be 2 power 8, which means that there will be 2 power 6 chunks, right? There will be 2 power 6 chunks, and then you can further divide it. Okay, so basically finally you got this 6 8 8 10, this division. Now let me just make it very clear that what does this division mean. Okay, what are these numbers representing? See, this 10 is telling you that at this level, there are in each of the chunk, okay, in each chunk. So let me write what is the meaning of this. Okay, what is the meaning of this, so that you understand this very clearly. So let me write it. So basically, let's just say this is uh, chunk size, okay, at this level, chunk size. Okay. See, this 6 will always represent the chunk size. This 8 will always represent chunk size. 8 will always represent chunk size. This 10 will always represent the chunk size. Which means there could be many chunks. Currently, let's suppose we don't know. Okay. There could be many chunks at this level. But at this level, the chunk size is 2 power 6 entries. You can later on convert this entries to bytes. That's fine. But at this level, you can say there will be 2 power 6 entries. The chunk size is 2 power 6 entries. Right. Similarly, if I ask you at this level, at the next level, what is the chunk size? So basically it is like this, right? So at this level, what is the chunk size? 2 power 8 entries. At this level, what is the chunk size? 2 power 8 entries. At this level, what is the chunk size? 2 power 10 entries. Okay. See, at the last level, the entries means bytes. I mean, whenever you want to convert to the bytes, you can directly say it is bytes. I mean, each entry is just containing one byte, because at the last level, you can say each entry was containing just one byte. Okay. At this level, each entry, whenever you're converting to the bytes, it will depend on page table entry size. Okay. And also, interestingly, at any level, at every level, basically, the page table entry size also could differ. It is not necessary that page table entry size at every level should be same. It is very independent division. Okay. Everything, this 8 I have chosen very independently. Every division is very independent. So let's just understand this division very carefully. Okay. So what does this mean? It means that at outermost level there is a chunk which is having, I don't know how many chunks, but chunk size is basically 2 power 6 entries. You can easily see that at the outermost level there are 2 power 6 entries. I mean, chunk is having 2 power 6 entries, and then this is pointing to many chunks, which means 2 power 6 chunks, and each chunk is basically 2 power 8 entries again. Okay. So this each chunk is 2 power 8 entries. So basically you are getting the chunk size. This 8 is telling you the chunk size, this 8 is telling you the chunk size, which means, see, which means what is happening here, that you are having 2 power 6 entries, means here you are having, actually at the outermost we always have only one chunk, or we always have only one page table. Okay. So if I just ask you, my next question will be that number of chunks. Okay. Number of chunks or number of page tables, number of chunks. So at outermost level it is always one. See here, at outermost level it is always one. Okay. So so here at the outermost level, number of chunks will be one. I will be filling these. Okay. I will be asking more questions and I will be filling these things. But before that, let me explain you what is happening. See, we have just one chunk at the outermost level, which is having the size is 2 power 6 entries. Each of this is pointing to one such chunk of size, the next level of size 2 power 8 entries. See, this is having 2 power 8 entries. Each of this, okay, this is also pointing to something which is having 2 power 8 entries. This is also pointing to something which is having 2 power 8 entries, like that, right? So each of this is pointing to something which is having 2 power 8 entries, because at the next level the chunk size is 2 power 8. Now similarly, here also there are many chunks. See, if someone asks me number of chunks, then I can tell you number of chunks based on the number of entries in the previous level. So how many number of chunks will be there? Since this is 2 power 6 entries, so I can say 2 power 6 chunks. Okay. Now each of these chunks, so there are many chunks, or each size is 2 power 8 entries, and each of this chunk is pointing to the next level. And what is the size of next level? This is again 2 power 8, right? So basically each of this chunk is again pointing to 2 power 8 size of chunk. Each of this, okay, each of this entry. So basically there are many entries. Each of this is again pointing to the next level, which is having 2 power 8 entries, I mean size of 2 power 8 entries. And then this is again pointing to the next level, which is having 2 power 10 entries. Okay, this is 2 power 10 entries, or 2 power 10 bytes. In this case you can directly call it byte also. Okay, 2 power 10 bytes, which means finally this is basically pointing to the page, right? Oh, sorry, the frame. So basically you can say finally it is telling you that, okay, this is the frame. I mean, this is not the metadata, this is the real page. So finally, and the page size is 2 power 10 bytes, so it will be pointing to 2 power 10 bytes. Okay, so let me go step by step. What is happening here? You are going to have this setup, I mean this division, and then we are just trying to understand that what does this division mean. Okay. So you have at the outermost level, you have always one chunk. So number of chunks are very simple. At the outermost level, I can easily say it is one chunk. Now each of this chunk, so how many chunks will be here? See, each of this entry will be pointing to one chunk. Each of this entry will be pointing to one chunk. And what is the size of this chunk? Size of this chunk is 2 power 8 entries, which I just told, right? But how many chunks will be there? How many chunks will be there? Can you tell me? How many chunks will be there? This is very important to understand. It will depend on the number of entries here. So number of entries at 2 power 6 here. So that is why number of chunks here 2 power 6 chunks. If someone asks me number of chunks, I will say 2 power 6 chunks at this level. Okay, because 2 power 6 entries at this level. Now each of this is again pointing to some chunk. So how many chunks will be there? Each of this entry, right? Each of this entry. How many chunks? See, how many entries in this level? In this level, there are 2 power 8 entries, right? There are 2 power 8 entries. In this level, there are 2 power 8 entries. And each chunk is basically having 2 power 8 entries, and each entry is pointing to one chunk, right? And how many such chunks are there? 2 power 6 chunks. So in total, if I just ask you number of entries, okay, including all the chunks. So basically, if I ask you number of entries including all the chunks, you will say 2 power 6 chunks are there. 2 power 6 chunks are there, and in each chunk there are 2 power 8 entries. So 2 power 14 entries in total, and each entry is pointing to one chunk. So that is why 2 power 14 chunks. Here you are having 2 power 14 chunks, right? So there are like 2 power 14 chunks, and each size is 2 power 8 entries again. Each size is 2 power 8 entry. So that is why basically here there are 2 power 14 chunks, and each is basically 2 power 8 entries. So how many total entries will be there? The total number of entries will be 2 power 22, right? I mean, you can just multiply this 2 power 22. So that's why there will be 2 power 22 total entries here, which means 2 power 22 total chunks here, right? 2 power 22 total chunks here. And at this level, we are not calling it chunk, we can call it page. So we already knew that if you don't have all of this, then 22 and 10, so which means there are 2 power 22 pages. So little bit you might have got understood that what we are doing, right? It is very easy that each is pointing to one chunk, and each chunk will be having some entries. So let me ask you in another way, okay? Instead of number of chunks, let me ask you that if I first ask you, let's suppose that how many entries will be there, okay? Number of entries including all the chunks, right? So this is the chunk size. Now number of entries including all chunks. Okay, let's suppose. Then there will be 2 power 6 entries because there is just one chunk. So the 2 power 6 entries only, right? How many entries here? Each, see, here you have 2 power 6 entries. Now you don't worry about the chunk. So basically you have 2 power 6 entries in total. And each entry is pointing to one chunk, right? And each chunk is 2 power 8. So you can just multiply these two, which means 2 power 14 entries will be here, which means that there will be 2 power 6 chunks, and each chunk is having 2 power 8 entries. So 2 power 14 entries will be here. Now again, there are total 2 power 14 entries. Now if you ask me that how many entries will be there in the next chunk, so in the next level, so you can say each entry is basically pointing to 2 power 8 entries, right? And there are 2 power 14 such entries. So that is why 2 power 22 entries we have here. Okay. So 2 power 22 entries you have here. Now each of this is basically pointing to 2 power 10 entries. So if I ask you that how many entries will be here, so you can say 2 power 32 entries, or here in this case the entry is just bytes, and which is true, right? 2 power 32 bytes we have in total. Are you getting my point? See, it is just very aptitude kind of thing. I hope little bit you are getting. Okay. So basically let me tell you the meaning of this 6 8 8 10 mean. Suppose you have some address like this, right? Suppose you have some address like this, which means which means the division is 6. Let me copy the division. Okay. So suppose the first 6 are this. So let's just say these are the numbers. The first 6 are this, okay? Next 8 are this, and so on, okay? Next 8 are this, and so on, okay? Suppose this is your logical address space, or logical address. Basically this is your logical address, right? Now what is the meaning of these zeros and ones? We want to understand this. See this, let me write in decimal. This is actually 20, this is I think 6, this is 5, this is 8, right? Okay. So anyway, so basically let's just understand the meaning of this. What does this mean? It says that, see, in this particular label you have each chunk of 2 power 6 entries, right? So in this 2 power 6 entries, there are basically 32, oh, sorry, 64 entries, right? So which entry you are looking for? So basically this number will tell you that, okay, just go to 20, entry number 20. It will say, just go to entry number 20. Entry number 20 will point to the next chunk, because everyone is pointing to one chunk. So it will point to next chunk, right? Now in this chunk, where to go? This 6 will tell. This 6 will tell that, okay, in this chunk you go to entry number 6. Okay, this is entry number 6. In this chunk you go to entry number 6. Now it will again point to some chunk. Now where to go in this chunk? This 5 will tell you that, okay, here you just go to entry number, this 5 is saying entry number 5, go to entry number 5. Okay, then this will be again pointing to some chunk, right, which is finally a page, which is fine. Now this 8 will tell you, which is also the offset we have. I mean, actually all of these are like offset only, okay, just like the way offset has worked. So it is saying just go to entry number 8. Here the each entry is just 1 byte, or you can say offset is 8. So go to entry number 8. This 8 is telling you entry, go to entry number 8, and this entry, or in this case it is byte, this byte we are interested in. Are you getting my point? So basically, these all are the offsets only, right? This 6 bits are offset, 8 bit is offset, this is offset, this is offset. These all are the offset only, but this is the offset to the page, okay, offset to the page, and you can say this is offset in the page table, okay, this is offset in the page table. I mean, these all numbers will tell you that how much down you should be going. So if it is 6 bit, then there must be 2 power 6 entries in that particular page table, a small page table, in that particular chunk. If it is 8 bits, then there must be 2 power 8 entries in that chunk. If it is 8 bits, then there must be 2 power 8 entries in that chunk. So basically, what I'm trying to say, that these numbers will tell you what is the size of the chunk at that level. What is the size of the chunk? Okay. So if 6 means 2 power 6 entries, 2 power 8 entry, 2 power 8 entry, 2 power 8 entries. So I hope you are getting now that what does this mean, right? So basically, given this division, I'm just making sure that you understand the interpretation of this division. Okay, given this division, you can immediately say this 6 will immediately tell you that you have 2 power 6 entries in one of the chunk, right? How many chunks are there? Let's not worry about it, but immediately you tell that, okay, each chunk size, or in other words, you can say that 2 power 6 entries will be there in a chunk, right, in one of the chunk. 2 power 6, because this is offset, it will tell you in this number, the absolute number, which means, let's suppose it is 101,001, something like this, right? 1 2 3 4 5 6, right? So this will tell you that where to go out of this 64 entries, which is 2 power 6 entries. This number will tell you that where to go, right? Now this, what does this 8 tell you? See, this 8, what does this 8 tell you? This 8 is telling you immediately, it is telling you that you have 2 power 8 entries, okay, in that chunk, right? And where to go in this entry? There are 2 power 8 entries, and which entry you should be selecting, this absolute number will tell you. Let's suppose this absolute number is this, right? Then you will get to know that, okay, in this particular level, that you should be going to, out of this 2 power 8, you should be going to here. Understood? Similarly, this 8 is immediately telling you that there are 2 power 8 entries. Okay, immediately it is telling you that there are 2 power 8 entries. Okay, and there will be some absolute number. Let's suppose this is one absolute number here. Okay, this number will tell you that out of these 2 power 8 entries, where to go. Okay, so where to go out of these 2 power 8 entries? Again, this 10 is telling you immediately, it is telling you 2 power 10 entries. Okay, at the last it is actually bytes, which is fine. Okay, and this absolute number, which is, let's suppose 1100111011, okay, something like this, these are the 10 bits. So this absolute number will tell you that where to go out of this 2 power 10 entries, or 2 power 10 bytes, right? So where to go, which is also called as page offset. So the thing here is that I hope that you are convinced now that what does each of this number are representing, right? So each of this number will tell you that how many entries are there at this particular level in each of the small page table, or in each of the chunk. Okay. And ultimately, you keep on tracing, which means it is pointing to it is pointing, let's suppose, somewhere here. Then you get to know that, okay, because of this, okay, then you get to know that okay, because of this you need to go this much down, okay, and then this is pointing to some some chunk, and because of this you get to know that okay, you have to go this much down, okay, this much down, and let's suppose this is pointing to this, then because of this you will get to know that okay, you have to go this much down. So basically each of this is like offset, each of this is offset, okay, you will get to know this is this much down, and then this is the byte we are interested in. Understood? So I hope this is making little bit of sense. So what we are trying to do, we are saying that initially you have no division. You have, let's suppose, the whole idea, the whole logical address space, which is of 32 bits. Initially, suppose this is of 32 bit. Okay, this is your logical address space. Now you say that since this is too long, okay, 32 bit, which means 2 power 32 bytes, which means it is like almost like 4 GB. Let's just divide, okay, let's just divide this logical address space into number of pages. Okay, this was the idea. Let's just divide into number of pages. Now based on the page size, let's suppose page size is 2 power 10. I immediately divide here also. I will say this is 10 and remaining is 22. Is this fine to everyone? Now there will be a page table which will be having how many entries. Immediately you can tell, using this you immediately you can tell that okay, there will be 2 power 22 entries. So there are 2 power 22 entries here, right? Because of this 22 you can immediately say there are 2 power 22 entries. So let me write that here 2 power 22 entries, right? Now suppose you say that okay, I again want to divide this. That's very easy, no problem. So you can again divide this. You just have to choose the size of the chunk. Suppose this time you are saying that okay, let me divide it, but this time I am choosing it to be 2 power 8 entries, right? So basically, let's suppose divide, so size of chunk 2 power 8. So I will again divide this into 8 and this will be 14. Which means at this level now there will be 2 power 14 entries. Or in other words, here there will be 2 power 14 such chunks. Right? There will be 2 power 14 such chunks. So basically here you have 2 power 14 such chunks, right? Or don't worry about this number of chunks. I hope you got to understand that that if we are dividing, if the way we are choosing the chunk size, let's suppose this is 8, then we will be dividing this 22 into 14 and 8. Then what does this 14 represent? It will tell you the number of entries here, right? What does this 8 represent? It will tell you the number of entries here in each chunk, right? In each chunk, number of entries here in each chunk. Now, coincidentally and not coincidentally, so basically at the last level, the number of chunk or number of page table is just one. Okay, at the last level. So in each there are 2 power 14 entries. In each there are 2 power 8 entries. In each there are 2 power 10 entries, like that, right? Now suppose you further want to divide. So what you can do? You can just say that okay. Let me just choose the chunk size. So suppose you further want to divide, and again let's suppose you're dividing into 8 and then remaining is 6, right? So what does this mean? It means that at the last level you will be having 2 power 6 entries. This 6 is representing you. At the last level you have 2 power 6 entries in each chunk, but the number of chunks are anyway 1 here, which is fine. This is telling you have 2 power 8 entries in each chunk. Number of chunks you can calculate, but let's not worry about it. This 8 is telling you you are having 2 power 8 entries in each chunk. This 10 is telling you are having 2 power 10 entries in each chunk, right? And these all are like offset only. These all are just offset, which means they will tell you that how much down you should be going to get that particular entry, right? So it will point somewhere, it will point somewhere, they will keep on pointing, and finally you, once you based on this number you go some 8 down, it will tell you okay, you should be going here, and then finally you will be getting something, and there you will be going 10 down, and then you will be getting your desired byte. That is how it is happening. That's very easy multi-level paging concept, right? Okay, see this example, see this diagram. So basically this, yeah, so by the way, you are going to have outermost page table address in your base register, something called as base register. Okay, so basically you have this base register with you, which will tell you where does this outermost page table is stored. Now everything is very easy. Based on this absolute number, I will go this much down. Okay, so wherever I find it, I will go there. There are 2 power 8 entries at this level in each chunk. Now based on this number, I will get to know, okay, how much down I should be going. It will be pointing to some chunk, and based on this number 8, I will get to know, okay, how much down I should be going. And based on this number 10, again, I should be knowing that how much down I should be going, right? I mean, I will be getting to know that how much down I should be going. So that is how it is working. I hope you understood. Now, now let's just do this gate question, which has been asked in 2002, but it is, very good question, very good to practice. Okay, let's just do this gate question, which is based on the multi-level paging. We will be solving few questions, and after that, it will be very crystal clear that what this multi-level paging is doing. Let's now see this question. So in this question, they are saying that virtual address is 32-bit. Okay, and physical address is also 32-bit. This is one of the subjective question that they ask in gate 2002. At that time, there might be some subjective paper. So they are saying that you have 32-bit physical and 32-bit virtual address, right? So let's just assume that this is your virtual address, which is of 32-bit, and similarly this is your physical address, which is also of 32-bit. Okay, so virtual address space and physical address space, both are 32 bits. The physical memory is byte addressable. So byte addressable means like at every address there is a byte, right? I mean, this 32-bit if the physical address space is 32-bit, then it means there are 2 power 32 bytes. And the page size is 4 KB, which means 2 power 12. It means that 12 is offset here and 12 is offset here. So remaining is 20, which is for frame number, and remaining is 20, which is for page number, if this is single level paging, right? So by the way, there will be how many pages? 2 power 20 pages will be there. Even if it is multi-level paging, but at the innermost, it will be 2 power 20 pages. Okay. It is decided to use 2-level page tables to translate the virtual address to the physical address. So now they are saying that you are translating this virtual address to the physical address using the 2-level page table. Equal number of bits should be used for the indexing first level and the second level, which means out of this 20, they are using 10 and 10 here. Equal number of bits they are using for the first and second level, and the size of each page table entry is 4 bytes. So page table entry size is given as 4 bytes. Now what they are asking, give a diagram showing how a virtual address would be translated to physical address. So this is a nice question in the sense that they're asking for the diagram. Okay, they are not asking any numerical value, they're asking for a diagram. So let me do one thing, let me just go to the next page and let me try solving this question. So basically what will happen, CPU will generate this virtual address, right, which will be any 01 or something like this. So basically you can divide this virtual address into 10, 10 and 12. So whatever virtual address you have, you can always divide that into 10, 10 and 12. Okay, so this is the first step. Let's suppose these are the first 10 bits, these are next 10 bits, and these are last 12 bits, right? Now how you are going to get the physical address? See, this is the offset, right? This is the offset. So you will say that offset for the physical address, you will say the offset will remain as it is. Okay, I mean, which means basically you will directly copy this offset, but there, instead of these 20 bits, there will be the frame number. Okay, the final frame number. So using first 10 bits, what will you do? This is, let's suppose, outer level page table. So some people call it first level also. Okay, I mean, it will be given like whether it is the first level. Some people also call this as first, this as second. So that is why it will be very, very clear. But outer inner is actually very much clear, right? I mean, outer inner is not confusing, but some people call it first level. This is second level. Some people call it this is first level and this is second level. So they will always give you that which one is the first they are referring to, in case if they ask such question. Okay. So by the way, this first 10 bits will tell me that in the outermost page table. So how many page table will be there in the outermost level? There will be just one page table, right? So in the outermost page table, where to go? Which means, let's suppose these first 10 bits are 0, 0, 0, 1 or something like this, right? I mean, depending on the number. So suppose these are the first 10 bits. 0, 0, 1, 0, and let's suppose 0, 0, right? Then which means this is 8, which means they are saying that just go to the 8th entry, which means I mean 0, if indexing is from 0, then basically the entry which is 7, right? Or maybe in numerical terms, like starting from 1, then go to the 8th entry. Okay, so it will depend on this number. So first 10 bit will tell you that where to go here in the outermost page table. This is the outermost page table. Now once you go here, you will get to know that where to go next. I mean, this is like kind of offset. It is like kind of offset. Now you will get to know where to go next. So basically each of this is pointing to one page table, okay, of inner level. So suppose this is the inner level page table that you have, that this particular entry is pointing to. See, every entry is pointing to one page table, right? Inner level page table. Now suppose this is pointing to one of this. So let's suppose this is the inner level page table that you have here. Okay. Now, in this inner level page table, you will again have to go somewhere. I mean, these are the many entries. How many entries are there? 2 power 10, right? So this 10 is telling you that there are 2 power 10 entries here also, right? Now, based on this number, let's suppose this time this number could be anything. Let's suppose this is 0, 0, 0, 0, 0, 0, 0, 0, 1, 0. Suppose this is 2. So basically you will go 2 down. I mean, based on this entry you will go, right? So whatever these 10 bits are, based on this you will go down, right? So suppose you are going down based on these 10 bits. So let's suppose you are going here, right? I hope that is clear to everyone. Now this will be pointing to somewhere, right? This will be pointing to somewhere, which is basically having how many entries? 2 power 12. Or in other words, you can say these are the 2 power 12 bytes. I mean, at the last level you have 2 power 12 bytes, right? And this is actually pointing to the page, okay, the real page or the frame, right? So basically this is pointing to a frame. Okay, so these have 2 power 12 bytes. So now based on this 12, right? Based on this 12 bits. So these 12 bits could be anything. Suppose 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, right? Based on this these 12 bits, you will go down, which means you will get to know that what is the offset based on this 12, right? This is a offset. I mean, for the physical address, actually you don't have to do this. I mean, this is the final byte, but just to get the physical address, you can say that, okay, this is the page number, this is the frame number, right? I'm interested in. So you can I mean, in terms of the representation, you can say that just to get the physical address, I can stop here only. Okay, I can stop here only, and I can say that this is actually the frame number. Okay, frame number, or pointer to the frame, or whatever you say, right? This is the frame number in which we are interested in. So once you get this frame number, what you do, you have your offset ready with you. You already have this offset. So what you can do, you can directly copy this offset, kind of, right? You can directly copy this offset here, and then offset is same, and then you can say the frame number you can get from here, right? I mean, the frame number is this. So basically this is the frame number that you can get. And finally, this whole thing is the physical address. This whole thing is the physical address. Now, instead of physical address, suppose you actually want the byte, so you can go to the frame, and then you can go to 12 down, right? And this is the byte in which we are interested in. Okay, I mean, based on these 12 bits, you can go down, and this is the byte in which we are interested in. Okay. So I hope you understood that how we are making the diagram. See, this question might be easy, might be tough, but this should be your one of the first question to understand the multi-level paging. Okay. So I hope that this diagram is clear to everyone, because this diagram is so important. Uh, like, I mean, this diagram is so important that it is having all the foundation of multi-level paging. Okay, that how it is actually working. So what does this 10 10 12 means? Once you understand that what does this 10 10 12, or how this division is helping us to get the physical address, the multi-level paging is actually very easy. Okay. See, ultimately, the questions might be a little tricky at the first. In fact, let me be very honest that the questions that we are going to solve, okay, in this video, are actually gate PYQs, but there will be little tricky. Okay, all the gate PYQs that we are going to solve will be little tricky. But once you solve all those, you will get to understand that how this multi-level paging is working, and then you can definitely switch to test series, and then you can solve all the questions of the test series and all. Okay, so I will make sure that you understand this multi-level paging very crystal clear, in very crystal clear way. Now let's just see this B. What is the number of page table entries that can be contained in each page? So they are saying in each page how many page table entries you have. Obviously 2 power 10 entries. How many bits are available for storing the protection and other information in each page table entry? Okay, so they are asking that how many bits are available, right? I mean, to store the other information. So basically, you can say that that there will be 2 power 20 frames. So 20 bits is needed for the frame, right? 20 bits are needed for the frame, and then you already have, I think, page table entry size is 4 bytes, right? So page table entry size is 4 bytes. You already have 32 bits with you. Out of these 32, 20 bits you need. Okay, 20 needed for frame number. So that is why remaining is 32 minus 20, which is 12, right? So 12 is answer here. So let's just see the answers that on the gate overflow directly, probably. So this is the diagram that they have, and 12 is the answer, right? Okay, let us now solve this question. So this question again has asked in GATE in year 2003. So what they are saying, in a system with 32-bit virtual address and 1 KB page size. So they are saying you have 32-bit virtual address and 1 KB page size, which is 10, and this is 22, right? 1 KB means 2 power 10, right? So there will be 22 bits are remaining for the page number. Now they are saying that use of one level page table for the virtual to physical translation is not very practical. Why? Because of, so you need to select one of the option, because of the large amount of internal fragmentation external. So if you are not not have understood internal external fragmentation, if you don't know, then don't worry about A and B. Anyway, these are not the answers. So my aim in this particular video to make sure that you understand the paging, right? So or let's just see option C, the large memory overhead in maintaining page tables. So what do you think? Large computation overhead in translation. See, in translation it is very easy. I mean, you don't have to do too much. You just have to go to based on these 22 bits, you just have to go to one of the page table, and then you directly get your frame number. So translation is not tough here. But as we know that memory overhead is too much, right? So that is why C is the correct answer here. So large memory overhead is there in maintaining the page table. Understood? So C is the correct answer. We have started with this motivation only, right? That why we want to do multi-level paging. So one of the motivation was to reduce the page table size, ultimately, in the sense that we don't want to store the invalid entries. This was one of the motivation. Another thing that you can say, which was kind of side job, is that it is very difficult to find out so much of contiguous space in the main memory. If let's suppose the page table size is 4 MB, then it is little difficult to find out 4 MB contiguous space in main memory. So that is why we thought that okay, let's just divide. Okay, so this was the purpose. Okay, so basically in the gate overflow also they have written the same kind of answer, that this is 4 MB or 4 mega entries are there, so which is very large. So that is why we go for the multi-level paging. Okay. Now let's see this question. What they're saying, consider a 3-level page table on a system where each page size is 256 bytes. So you have 3-level page table, okay, which means there will be page offset, then label 1, label 2, and label 3, right? Okay. Each page size is 256 bytes, means this is offset is 8 bits. This is offset. Each page table entry is 2 bytes. Okay. Page table entry size is 2 bytes. First level page table, okay, so here actually it must be mentioned, but here I forgot to write that first level. Let's suppose this is the first level, this is the second level, this is the third level, right? First level page table contains 16 entries. So if it is containing 16 entries, then can you tell me that what should be the number here? 16 means 2 power 4, right? 16 means 2 power 4. So basically it must be 4. I mean, this number must be 4. Then only you can say that first level is containing 16 entry. Second level page tables, okay, anyway, like this is S means like there are multiple page tables. It means that automatically you can infer that they are saying that second and these are the second and third, right? Second level page tables contain to 128 entries. So basically second and third both are containing 128, which means 2 power 7, which means it must be 7, it must be 7 here, right? So if you even sum this up, this will be 7 plus 7 14, and plus 4 is 18, and then 8, okay, 18 and 8 26, right? So basically they are actually asking the virtual address space size. So you can say this is 26 bits. Okay, very easy question, but the purpose of this question is to make sure that have you understood this this division or not, right? So which means till now I have given you this, and I was just asking what does this 4 means, what does the 7 mean, what does the 7 mean. But now in this question they are basically doing some kind of reverse engineering. They are just asking you to write the 7, okay, given that okay there will be 128 entries, there are 128 entries in the second and third level and so on. So given that, can you identify the division? Okay, this was the purpose of this question. I hope you understood, right? Here this page table entry size was not relevant at all. Okay, here this page table entry size was not relevant. I mean, this was unnecessary information for this particular question. Okay, now let's go to the next question. Now let's solve this question. So in this question they are saying that basically this question is the variation of the previous question only, almost same, a little bit of change I have done. You will get to know that what is the change, right? So the 3-level page table, again the same story. Okay, so this is 1, this is 2, this is 3. Okay, so here 256 bytes, which means these are the 8-bit offset. Page table entries are 2 bytes, that's fine. Now they're saying first level page table is basically 2 power 6 bytes. So if you notice the difference, earlier I was saying first level page table was 16 entries. I mean the unit was entries, right? But now I'm giving you unit in terms of the byte. So the very first step that we must have to do, okay, to relate this thing with the division, that we always talk in terms of the entries. I mean entries are more important, okay? So 2 power 6 byte means how many entries will be there? If one of the entries of 2 bytes, then you can say 2 power 5 entries. Here 2 power 6 entries. Here 2 power 7 entries, right? So now you can quickly fill if this is 2 power 5, then this must be 5, this must be 6, this must be 7. Okay, and then you can sum this up. This will be, I think, 12 plus 8, 20 plus 6, which is 20, 26, right? So 26 bits is your answer. See, the only key step is to identify that this is given in bytes, but you have to convert to the entries to get this division. Okay, that is the only difference that I have done with respect to the previous question. Otherwise, this question is same as the previous question. Okay. Now let's solve this question. This question I have taken from one of the university. So what this question is saying, that let us assume that there are 2-level page table in your system. The virtual addresses is split like this. Okay, this is virtual page number part 1, virtual page number part 2. I mean the page number itself is divided into 2 parts, and the page offset, which is fine. Which of the following statements is or are true? So you can say that this is MSQ question. Virtual page number part 1 is used to index the physical page that contains the data. Do you directly get the physical page? No. Okay, virtual page number part 1 is used to get the base address of the first level page table. So by the way, let's suppose this is first level, this is second level, right? So they are saying that is used to get the base address of the first level page table. No, actually this used to get the base address of the second level page table, right? Okay, so this will be second level page table. It will be pointing to the second level page table. So this is false. This is also false. Page offset is used to locate a specific byte within the physical page. Yes. So page offset is basically the purpose of the page offset is that only. So you can say these two are false. This is true. Okay, this is true. What about option D? Virtual page number part 2 is used to index page table entry in the second level page table. So they are saying is used to index page table entry. So basically, do you, I mean, from here, do you get the page table entry in the second level page table? So this is the second level page table. Do you get using this, let's suppose this is 10 bits. Do you get the page table entry of the second level page table? Then answer is yes, right? Answer is yes. Yes, we get it, right? So C and D both are the answers here. This question I have taken from one of the university. Okay. Great. So hope that is clear to everyone. Now let's just move to the next question. So let's just see what this question is saying. A process has 32-bit virtual address space. The system uses a page size of 4 KB, which means 2 power 12 bytes. Page table entry is 4 bytes. The process is using only 2 power 16 bytes of the memory. Okay, so basically this is interesting. They are saying that total that can be used, I mean the leverage that we are providing is 2 power 32 bytes, right? Which is almost like 4 GB, right? Almost like 4 GB. And they are then in the next line they are saying that you can use 4 GB, but in the next line they are saying that you are only using 2 power 16 bytes. See, do you know that if this is the total address is 2 power 32 bytes, I mean this much you can use, then do you know how much is the difference between these two? Okay, the common mistake that we generally do is we think that okay, this is double, I mean this and this are double of each other, I mean and this is, I mean multiply by 2 you will be getting this, or divide by 2 you will be getting this, I mean this and this are related to the factor of each other, right? Factor of 2. But it's not a factor of 2, it's a factor of 2 power 16, right? It's a factor of 2 power 16. This is very common mistake, and every year, I can say every year, there are at least one or two top 100 rankers, at least one or two top 100 rankers, I can say, they make these kind of silly mistakes. Okay, so they, I mean since we interact with so many students, so they later reveal that okay, this kind of mistake I have done. So don't do this mistake. Okay, if you do these kind of mistakes, then let us know in the comments that you also do these kind of mistakes. Okay, so what I'm saying, that these two are not a factor of 2, these two are factor of 2 power 16. So which means 2 power 16 is actually very small, which is 2 power 6 into 2 power 10, which is basically you can say 64 KB, right? 64 KB and 4 GB. You just imagine, right? Just imagine how much difference it is. 64 KB, this is just 64 KB, and this is 4 GB that you can use. Anyway, so now let's just come to the question directly. So they are saying that see, this is one of the unique question, unique in the sense that we have not solved this kind of question till now. Okay, till now we have not solved, but now we will be solving, and we will be making sure that you solve these kind of questions very easily also. Okay, this is the aim. So the idea here is that you have the logical address space of 2 power 32. Okay, 2 power 32 bytes. Now they are saying, see, as we know that most of this is empty, right? Mostly empty. So they are saying that you only use some KBs, which is 2 power 16 bytes you use, right? And which is basically combined size of upper and lower regions of the address space. I mean combinedly, this and this combinedly you are using only 2 power 16. 2 power 16 bytes you are using combinedly. Calculate the amount of memory required to store the page tables for this process in the following cases. So they are saying single level, if you use a single level page table, then how much memory you will require for this particular setup. If you use a 2 level page table, then how much memory you will be requiring for this particular setup. So both the questions they are asking. Let's just first solve the single level page table. Single level, right? So in single level, actually doesn't matter that how much the process is using. I mean, how many invalid entries are there. So basically, it just say that okay, if this is single level and this is basically the page size is 12 here. So total is 32. So that's why 20 will remain. So 2 power 20 entries in page table will be there. Entries in page table, right? Multiplied by page table entry size. This is the size of a complete page table, you can say, right? This is size of page table. So if you solve this, you will be getting your answer. Okay. So like 2 power 20 multiplied by page table entry size, which is 4 bytes, right? So you can say it is 2 power 20 into 4 bytes, which is basically this is mega, right? So you can say this is 4 MB. Okay, 4 megabytes. So this is the answer for the single level page table. Actually, it doesn't matter that how much process is using. So this is the core, you can say the drawback of the single level page table, that doesn't care that how much process is using. Now let's just see that how multi-level page table or the two-level page table in this case can help us to reduce the size of the page table. So let's suppose this is multi or the two-level page table. Okay. So now see here, it was 12. It was 12. Now we need to decide that, I mean, not decide, basically we need to see in the question if they have given us the hint that how to divide. I mean, what should be these numbers, right? Let's just see. So the remaining is 20. Now let's just see if we can figure out from the question itself. So the question actually directly saying that assume that inner level page table contains 2 power 10 entries, right? So basically inner level page table contains 2 power 10 entries. So this means this is inner level. So 2 power 10 means this must be 10 and our remaining is 10. So basically this is the division that we have. Okay, this is the division that we have of 32. Now let's see the size of page table combinedly. So you just tell me the number of page tables that we have. See, number of page tables at this level, we have only one page table, right? We have only one page table here. Now this question is little tricky at the first sight, but once you understand, it will be very easy, right? Not very easy, but it will be actually approachable. Okay, but if you do enough practice, it will be easy only. See what they are saying, that you are using 2 power 16 bytes. So using, I can say, usable space or usable, the portion of address space that you're using is basically 2 power 16 bytes. The very first step, okay, I can say this is like kind of we will be solving actually this type of questions, four five of these type of questions. And in fact in gate they have asked two three times they have asked these type of questions. Very recently also they have asked these type of questions. So just pay a little bit of attention here. See, the very first step is that step 1, that first calculate that if these many bytes are being used, then how many pages are being used, right? So number of pages that being used. Number of pages that being used out of 2 power 16. I mean, if these are 2 power 16 bytes and size of the page, one page is 2 power 12. So you can say you are using 2 power 4 pages, which is 16 pages you are using. This is the very first step, that you first get to know that how many pages you are using, right? So you are using 16 pages. Okay, so let me just make some space here. So this is the step number 1, that how many pages you are using. So this is very important to know that how many pages we are using. So ultimately I can say that we are using 16 pages. Now some pages will be here, some pages will be here, right? Now what will happen, that if you look at the single level page table, okay, if you look at the single level page table, then it will be basically containing how many entries? It will be containing 2 power 20 entries, right? I mean, we are not going to store all of these 2 power 20 entries, but yes, this will be containing 2 power 20 entries, and further we are dividing into 2 power 10, 2 power 10, 2 power 10, right? Further we are dividing into 2 power 10, 2 power 10, 2 power 10, but ultimately these are 2 power 20 entries, okay? Now see here that one of this entry will point to one page, right? Second entry will point to second page, and so on, right? Here the entries are pointing to the pages which are here, right? So basically, you can say if 16 pages are being used, then indirectly or directly you can say that here 16 entries are useful, right? 16 entries are useful, isn't it? Is this fine to everyone? Let me know. Okay. So here 16 entries are useful. Okay. And then if the 16 entries are useful, see at the outermost you always know that there is only one page table, okay? Only one page table. That is fine, right? So here you have 16 entries useful. Now in each of the page table you have 2 power 10 entries. I mean you can accommodate 2 power 10 entries. Okay. So basically you can say one page table of one chunk will be useful here. See, first you have to identify how many pages are useful. Using that you can immediately infer that how many entries are useful in the inner level page table. So in the inner level page table 16 entries are useful. I hope that is fine to everyone, right? So till now things are clear that 16 entries are useful in the inner level page table. Now the second step is to know that how many pages or how many tables are useful here. So you can say that 16 in each of this page table you can have 2 power 10 entries. So just one page table here, because I mean even if all of these 16 are here doesn't matter to us, but some of the, out of these 16, just to make the explanation little easier or little clear, let's suppose that 5 entries are useful here. Okay. I mean, it doesn't matter how you divide the 16, because 16 is very small number compared to 2 power 10. But just for the sake of explanation, let's suppose 5 entries are useful here and 11 entries are useful here. Okay. So you just tell me that how many page tables are useful here. See, one page table above and another page table below, because in one page table you can have 2 power 10 entries. Okay. So that is why 2 page tables are useful here. Understood? So I can say 2 page tables are useful here. Okay. One is here and one is here. So ultimately actually I just need to know that how many page tables are useful and the question is done. So basically you can say that here you have 2 page tables useful. Okay. So this is the step 2, that get to know that how many page tables are useful in the inner level. Okay. Number of page tables useful in inner level. How many page tables are useful? You can say that 2 page tables only. Okay. Or 2 chunks. Basically 2 chunks. These 2 chunks are useful. Right? And here obviously you have to maintain this one. So basically you can say that one page table here. I mean, if someone asks you that how many total page tables, or I mean you can convert to the bytes. This will be kind of a step 3. But if in terms of the number of page tables, you can say one here, and one here. Total 3 page tables are useful. Okay. So you can say that 2 page tables are useful here. Now let me just go to the next page and let me finally basically tell you that how many bytes will be needed to store the page tables. So you can say that here at this level 2 page tables are useful. I mean useful means you have to maintain. Tables are useful. At this level you can say one page table basically will be needed, right? One table. Okay. Or one page table. Understood? And here 2 page tables are useful. So each page table size here will be how much? In terms of the entries, you can immediately tell me that okay, these are like 2 power 10 entries in one page table. So this is I mean this is size here in terms of the entries, right? This is size here, again it is 10 also here, so that is fine, which is like 2 power 10, and in terms of the entries, this is the size. Each page table entry size is also given here. If you see the question, then you can say page table entry size is 4 bytes, right? So from here you can say that in terms of the bytes, 2 power 10 into 4, which is like these many bytes will be needed here. 2 power 10 into 2 into 2 power 2 bytes will be needed here, which is like if you sum both of this, then you will get to know. Basically, I mean, you can sum here before converting, or maybe you can sum here. Basically 2 power 10 you can take common, or 2 power 10 into 2 you can take common. This is 3 into 2 power 10 into 2 power 2. Okay, so which is like this is k, this is 3 into 4 is 12. So basically this is 12 kb, right? 12 kb. Basically this is 8 kb, this is 4 kb. Okay, this is 4 kb, this is 8 kb, so total 12 kb will be needed. Now you see the difference. See, earlier in the single level page table we needed 4 MB, which is huge, right? And now using just two level page table you reduce the size to 12 kb, isn't it? So I hope you understood that how we are solving this question. So basically we are just saying that how many page tables will be useful. That is the only key point we want to find out at this level, how many page tables will be needed. Okay, so here one anyway needed, right? And here you just need to find out how many page tables will be needed, and that's how you can solve this question, right? So how many pages are useful? 16 pages are, I mean, the process is using total 16 pages. I mean, sometimes they can just skip the step one. They can directly tell you that okay, 16 pages are needed or 16 pages are using. Okay, I mean, the process is using 16 pages. They can directly tell you in terms of the pages. Actually in gate 2024 they asked the question and they directly told that okay, to 16 pages or like some number of pages, these many pages are used. Okay, so they are just skipping this step one, which is fine. I mean, you first have to find out that how many pages are useful. Using that you can find out okay, how many entries are useful here, right? And based on that, let's suppose this is 5, 11, it doesn't matter actually, whatever distribution you have, 1, and this is, let's suppose, 15, right? Then also since one of the page table can contain 2 power 10 entries, so it doesn't matter whatever distribution you have here, right? So basically one page table you will definitely need here, one page table you will definitely need here. That is how you can solve this question. Now let's solve a slight variation of this question. So see, the answer of this question is 12 kb, right? So here 4 kb and here 4 kb. So 4 kb and 4 here 8 kb. So total 12 kb is your answer. Okay. Now let's have a slight variation to the previous question. So the variation here is that earlier, I mean, this is the exact same question. Just this line is changed. Earlier they said that 2 power 16 bytes of memory. Okay, till this point everything is fine, right? 2 power 16 bytes of memory, which means it was 16 pages. We have calculated how many pages. It was 16 pages. Now earlier they said like these 16 pages are divided into upper and lower half. Okay. Now they are saying that all of these 16 pages or all of this memory that we are using is from this address. I mean, lower or upper doesn't matter. I mean, this is basically 0. Okay, so generally we call it lower address. So basically you are starting all of your 16 pages which are useful is from this area only. Earlier it was divided, now they are saying it is not divided. Okay, I mean, if you start 0 from here, it will be from this area. If you start 0 from here, it will be from this area. Okay, doesn't matter, it is just a nomenclature. So single level page table we have already calculated, this was 4 MB. Now for the next two level page table, let me just tell you, very easy question again. So see here, this is 10, 10 and 12. And now here I know that total 16 pages are useful, right? So basically you know that here this area is useful 16 pages, right? Which means this is the single level page table. Okay, in single level page table how many entries are useful? Sorry, this is not single level, this is level 1 or maybe inner, let me just call it inner page table. Here how many entries are useful? If the 16 pages are useful here, then obviously 16 entries from here are useful. So you can say 16 entries useful. 16 entries are useful here. And anyway, see, the outermost, don't worry, at outermost you anyway need one page table, right? One page table. So if 16 entries are useful, which means how many page tables will be needed? See, each can contain 2 power 10 entries. So that is why you can say that just one page table. Earlier, actually, since it was divided into two regions, so that's why one and one here. But here, just one needed. One page table is fine, or one chunk or one small page table is fine, right? Page table is fine here. Okay. Now, which means one page table can contain 2 power 10 entries, or in other words, 2 power 10 into 4, which is basically in terms of byte, it is 4 KB, right? So 4 KB here, 4 KB here. So total 4 plus 4, 8. Okay. So 4 KB outer, because 2 power 10 entries here also, and each entry size is 2 power 10 into 4 bytes, so which is basically 4 KB. 4 KB here also, and one of this will be needed only. So 4 KB inner also. So 8 KB only, right? 8 KB only. So basically, you just need, in this case, okay, in this case, you just need 8 KB. Earlier it was 12 KB, right? Because we needed total three, right? At inner level, we needed two. So that is why total was three earlier. Now let's solve this question. This question has been asked in GATE 2003. Okay. So in this question, basically it's seeming to be, little, I can say, scary, which is fine. But yes, it was the tough question indeed. Okay, you can easily guess from the number of boards that it has. But here some of the information is not relevant for the multi-level paging. So I mean, not relevant for this discussion. So that is why I will just remove this. This is TLB information. Basically this question had two parts, and I'm just solving one of the part which is relevant to this video. Okay. And also this physical address cache and virtual address cache, these are not in syllabus, so you can even skip. Okay, this is the second part, you can even skip. Okay, don't worry about the second part. So this information is actually not relevant, so I will just remove this information. Okay, so this is just a removal of this information which is not relevant. So now let's just solve this question. Okay. Now this is little lengthy to read, so I'm in the same question, I'm just writing it here. Okay, just a small version. I mean, you can read it out. It is basically having some unnecessarily wordings like for virtual to physical transformation, 10 significant bits are needed and so on. So I'm just writing like, okay, 10 12 division it is given. So this is how this question looks like. So let's solve this question. This question is GATE CSE 2003 question. I can say this was one of the hard question, or one of the hardest question among multi-level paging. Okay, but you will get to understand for sure. Okay, so the first idea is that you should be understanding that what this question is asking. Okay, and then you can basically you can have your more understanding of the multi-level paging after we solve this question. So what they're saying that you have two level page table, and this is how it is divided. Suppose, see, earlier questions we said like there are like 16 pages are useful. Okay, one of the question was saying 16 pages, some pages from top, some pages from down. Another question was saying all the pages from top. Now in this question they are saying that you are using 5 pages. Okay, number of pages are given to you. You are using 5 pages. Okay, two contiguous pages from here. So basically number of useful pages are given to you, are 5 pages. But here, instead of saying that okay, all are from upper region, all are from down region, or divided only upper and down, instead of saying this, they are saying they are basically divided like this. I mean, some pages are starting from this lower address. Okay, see, this is 10 10 12 by the way. So which means that this last 12 bits are offset. So little bit, okay, little bit, you can guess that okay, this is the starting address, or this is the lowest address. And this is the basically these 12 bits are offset, which means that page offset, which means that if you do all of these ones, this will be the highest address, right? I mean, this is touching the highest boundary. Okay, so basically let me just go to the next page. They are saying that we have 10 10 12 division. Okay, and we are using some pages from the top, 2 pages from the top. So they are saying 2 pages from the top or lower address. So basically 2 pages from here, They are saying one page from the lowest, highest address. Okay, so which means starting from this address is 0xff, and the hexadecimal they have given. Okay, so 000, and this will be 0xfff. FFFFFFFFF. Okay, everything is F. I mean, this is one page only. Okay, this is one page only, because if you do all of these one, and then this will be the ending of the page, because this is just offset. So don't worry about this last three hexa numbers, right? Last three hex numbers, don't worry about it. So basically, this is your hexadecimal address. I hope now you are a little bit able to understand that what is the lower address, upper address. So basically just trying to find out some meaning here, right? This is one of the address, maybe somewhere in between. Okay, somewhere in between they are saying two pages are useful, somewhere in between. Okay, so two pages here, one page here. So basically total 5 pages they are using. So tell me number of entries which will be useful. 5 entries obviously, right? So you can say this is inner level page table, inner level. So 5 entries useful, right? And obviously at the outermost level you just have one. At outermost level you just have one page table. I mean, here you don't have to do anything, right? Just one page table. Now all here we have to find out is that out of these five, see, the 5 entries are useful. Okay, 2 entries at the bottom, 2 entries at the top, 1 entry in the between. All we have to find out that how many page tables are useful. Definitely I can say that one page table at the bottom, one page table from the top, and one page table, I mean, from the between. I mean, like this is kind of, I can say, initial intuition, right? Which is actually true. I mean, there won't be any surprises. Okay, so this is true that one page table is needed here. One page table will be needed here, because just because of one entry I need one page table. I can't do anything. Okay, just because of one entry, right? I really wish that these 3 entries, or in fact I really wish that these 5 entries could be contiguous. If these 5 entries are contiguous, then definitely you just need one page table, right? Just because these 5 entries are distributed such that we can't help but we have to use more than one, and we cannot just settle for two. We have to use three, right? So one here, one here, and one here. So 3 page inner level page table you need, and page table entry size is also given, right? 4 bytes. So just like 10 2 power 10 entries in each. So basically it's just like 4 kb. Okay, 4 kb. So 3 you need here, which means 4 plus 4 plus 4, so 12 kb you need here, and obviously 4 kb here definitely. So 16 kb you will be needing. So what is the answer? 16 should be the answer. Just a second. So let me just show you on the gate overflow. So 16 should be the answer, right? So this is the question, and if you see the answer, see, this question has got many upvotes, right? And it has got 32,000 views, and if you see the answer, 16 kb is the answer, right? Okay, so answer is 16 kb, which is which is the same answer that we were also calculating. So let me write down our answer also. So 16 kb is the answer. I hope you understood the question. But here just a bit of thing that I haven't basically till revealed, or I can say I haven't calculated, which is that probably like we just you know skipped the calculation, that probably what if these 3 entries, okay, the above 3 entries are just needing one page table instead of individually one, instead of these one, what if, because one can contain 2 power 10 entries, right? So what if these three are in just one? So we have to be careful in this. Okay, so here actually I just guessed it. Okay, so 16 kb is answer, or probably the 12 kb could also be the answer if these are in the just one. And if you see the options, 12 is also the option. Okay, 12 and 16, one of this is answer, but I just guessed probably 16 is answer. But we have to be careful in this. Let's just see that how to be 100% sure that whether 16 is answer or 12 is answer. So see, we just need to know that, okay, from here to here, I mean, this entry, the third entry, wherever it is starting, okay, this, if these are 2 power 10 entries, I mean, this entry is just after 2 power 10 entries, then there is a separate table needed. Otherwise, there is no separate table needed, right? So I just need to check this. So let's just go to the next page and let's just try to check whether, so basically what I'm trying to say here is that I just need to check whether this third entry is coming after 2 power 16 entries on, or 2 power 10 entries or not, right? So let me write what I want to say, that we need to check whether this third entry is coming after 2 power 10 entries or not. That is a simple thing that we need to check. Okay, it's not very hard to check. It is also, doable and easily doable. We will just see that how you can do it. Okay, so we need to check if the third entry is after 2 power 10 entries or not. After 2 power 10 entries, after means from uh, starting, right? I mean, or from address 0 or something like this, right? So if the third entry is after 2 power 10 entries or not. So which means what? If the third entry, right? If the third entry is after, like there are multiple ways to check it, but or multiple ways to say this, but you can say after 2 power 10 entries should be there, or maybe you can say that in terms of the absolute address. Okay, if you don't look at this division and all, okay, there are like multiple ways to actually check it. So in terms of the absolute address, you just need to check. See, if there are like 2 power 10 entries, then basically there must be, here at this level there must be 2 power 10 pages, because each entry is pointing to one of the page, right? So you just need to check from the starting. Okay, so from the starting, so 2 power 10 pages, after 2 power 10 pages, this particular segment, or this particular, these two pages are starting or not. Okay, so basically these two pages are after 2 power 10 pages or not. Or in other words, okay, in terms of the absolute address, you can say 2 power 10 pages, or or 2 power 10 into what is the size of each page. Size of each page is 2 power 20, right? Sorry, 2 power 12. So 2 power 12, which is these many bytes. So if you have, this much difference from the first and second, if you have this much, I mean these many bytes are these many bytes difference, then you can say it is very safe to say that these two pages are starting after, after this particular page table. So basically what I mean to say, let me just make it very simple. Okay, don't worry about it. That, let's just go, step by step. Let's just do one thing. Let's just first not go with the absolute address, because it is not even needed. We can do this also, but it's not much needed. We can directly figure out using the pages only. Okay, whether this page is starting after 2 power 10 pages or not. Okay, this is kind of one of the way. Okay, whether this page is starting after 2 power 10 pages or not. So basically, how we can check it, let me do one thing. Let me, this address, whatever these addresses are, let me basically divide this into 10 10 12. Okay, 10 10 12, right? So these are the last 12 which are actually useless. I mean, this will be anyway 0. I mean, the offset will always be 0. The starting page offset will always be 0. So this is, I mean, for now it is useless. I just need to check whether in these two are we having 2 power 10 pages, right? See, this is page number 0, right? I mean, this is kind of page number 0. And if you have, instead of 0, if you have 1, this will be page number 1. And if you have, okay, if you have 2 here, it will be page number 2. If you have 3 here, it will be page number 3. In the hexadecimal only I'm talking about, right? And then if you have F here, it will be basically page number 15 or something like this, right? So basically what I mean to say, that here this is telling you the page number, right? I just need to check whether there are 2 power 10 pages in between or not. So in between 2 power 10 pages or not. Which means if you add 2 power 10 means 1 followed by 10 zeros, right? 1 followed by 10 zeros. If you add 2 power, I mean 1 followed by 10 zeros, then what will you get here? If you add 1 followed by 10 zeros, see these are the 10 zeros and 1 followed by 10 zeros. So basically you will immediately get it, right? You will directly get this. So which means there are exactly 2 power 10 pages. Okay, there are exactly 2 power 10 pages between these two addresses. Which means the first address and this address, okay, this address and this address, in like this address is starting immediately after 2 power 10 10 pages. Okay, so you can say this address is starting. Okay, so this is starting immediately after 2 power 10 pages. right? Why? Because see, this this, one of the way to understand this is like this. See, you can say that the first address, what is the first address here? The first address is always 0x in the hexadecimal, 0 0 0, all the zeros, right? Now the second address, what will the second address? Second address will look like 0x 0 0 0 0, all the zeros, and then 1, right? This is the second address. Third address will look like 0 0 0x 0 0 0 0 0 0 0 2. But actually I'm not very interested in that much micro level addresses, in the sense that let's not worry about the offset part of this, right? Let's just directly, instead of counting the bytes, right? See, if I keep on counting the bytes, then after since the page offset is 2 power 12, so after this f 3f, right? This address, basically you can say this address is one page. Till this address, this is one page. Okay, but let's not unnecessarily go byte level kind of addresses. We already have very beautiful division, so let's just use that, right? So this is you can say one page, but the next page will get started from this, right? So 0x 0 0 0 0, I mean there will be these, in the hexadecimal, these 3 hex or 12 bits will be anyway 0, so this will be 1, right? This will be 1. This is the next page. Is this understood to everyone? This is the address, you can say address of second page. I mean, in terms of the number, I mean the page number is 1. Okay, page number is 1, but the address of the second page, right? Or you can say the address of page number 1. Okay, so address of page 1 is this, I mean starting address of page 1. Is this okay to everyone? Okay, so how many addresses are above it? Basically, how many pages are above it? There is just one page above it, right? Now if I'm adding one, see, if I'm adding one, so just don't worry about these offset bits. Okay, so just see here, if I'm adding one, just let me just copy this. Okay, see here that what I'm saying, that if I'm adding, just don't worry about it. Okay, this offset part. Now coming to this page number, if I add one here, this will the I mean one page later. If I add two here, then it will be two pages. After this, there will be two pages, right? Like that. If I add in this particular thing, okay, if I add, or you can say directly this. Okay, in this whole thing, if I add 2 power 10, then there will be 2 power 10, I mean this address, if you add 2 power 10, then this address, whatever address you get, you will be getting basically something like this. uh, you will be getting 1 here, right? So let me just add 2 power 10 here. So if you add 2 power 10, you will be getting something like this. See, don't worry. In Gate, they don't ask difficult questions all the time. This is one of the difficult question, I can say. Okay, in terms, see, it was easy if you don't have to figure out that whether the third entry is within those 2 power 10 span or it is outside the 2 power 10 span. Okay, it was easy if you don't have to do it. If the third entry is if this is this, if this is not at all present, let's suppose, okay, they are saying something from upper, something from down, then this question have been very easy, right? But they made it tricky by giving something in the between, and they even made it more tricky by giving you this address. Okay, and then they left you to figure out that whether you can figure out that these two are basically in this 2 power 10 span, or this is outside 2 power 10. Actually it is easy only, but initially it will be definitely hard. Okay, so if you are finding it hard, then don't worry. Okay, because it is, because for the beginning it will be hard. Okay, so if you add plus 2 power 10, okay, if you add 2 power 10, then you will be getting this, right? This, which means what? Which means what? This is basically the start of next segment. Start of, they are saying data. They are saying data is starting from, your code is starting from this, data is starting from this. This is the start of data. Okay, so basically from starting there are 2 power 10 pages, and this is the next page immediately after 2 power 10 pages. That is the point. Understood? So the third entry is outside our region. Okay, the third entry is outside our region. So basically you can say Okay, this is not the like, okay, at the last they're just using one, actually it doesn't matter. So here they're third and fourth. Okay, here they're third and fourth. Okay, the third entry is outside basically our 2 power 10 region, so that is why we have to use one more page table here. Okay, because third and fourth entries are outside our region. So this was one of the way to check, right? But the easiest way is by using these 10 bits. See what I did, I was using kind of like I was just basically using this inner level 10 bits, and then I was figuring out whether it is outside 2 power 10 range or within 2 power 10 range and so on, right? It is also approachable method, but there could be little bit easy method. Okay, what is that method? The last method I can say is using these, right? Is using these. See, outermost page table entry number 0 is for this region or this particular segment, and outermost page table entry number 1 is for this, and outermost page table entry number this for the last one. So basically based on the outermost, let me go based on the outermost, what this outermost is saying. Okay, so this is the outermost page table. So entry number 0 is basically pointing to some inner level page table, and which is that's fine basically. But I'm saying that this is the valid entry number, right? Here, this is the valid entry number, and outermost entry number one is also valid. This is also valid, right? Which is also pointing to one more, right? Page inner level page table. So since here one is valid, here also one is valid, and here also like here this is the outermost, which is like a last entry, right? So here one is valid. So basically you can say if these three are valid here, okay, three distinct you have here. If three distinct you have here, it means at inner level you must be using three page tables only, right? If three distinct you have here, then at the inner level you must be using three page tables only, right? Is this fine to everyone? I hope that is understood. So basically, very easily you can say that since these three distincts are there, so that's why three inner level page table are useful, because three entries are only valid at the outermost. Okay, so you can say three entries. This is the easiest method, right? Three entries are only valid at outermost. Hence three inner level page tables are useful, and hence you can say these are three plus one is this, so four are totally useful, right? That's how you can solve this question. I hope you understood this question completely. Initially, don't worry about it. This was actually a tricky question, but using the outermost page table entries, okay, you can easily figure out that okay, how many inner level are actually useful. And that's how they've written the answer for this question on the gate overflow also. Maybe I have the answer here. So this is the answer that they have written on the gate overflow. So Arjun sir has answered this question, and Arjun sir has clearly used the method, the later method, which is very easy method. So they are saying that each entry is 4 bytes, and hence that's fine. Now the process uses only three unique entries from this 1024 possible entries. So basically they are saying the three unique entries from the outermost. This is the thing that they are saying from. So I hope you understood this question. Yes, it was tricky question. Okay, indeed it was tricky question. But now hopefully this is understood. Okay. So now suppose if I give you the similar kind of question in the test series. Actually, I'm going to give you. Okay, so there is no escape. So I'm definitely going to put similar kind of question in the test series, because I've already found similar kind of question from a standard university. So I will put that question in the test series. So suppose if I give you, then will you able to solve it or not? See, you just have to figure out that how many entries in the outermost are useful, so that you can easily figure out that how many inner level page tables are useful, right? That's how you can easily figure out. Okay. Now we will be doing the similar type of question in the sense that number of page tables in the inner level, how many are useful. Based on that, we will be finding out the total size of page tables. Right? We will be doing a similar type of questions from the gate PYQs only. Let us now see this question. So in this question, they are saying that consider a 3-level page table to translate 39-bit virtual address to physical address. So we have 39-bit virtual address, which is given as like this. I mean, they have already, done the translation. Sorry, they have already done the division. The page size is given as like 12 bits, which means like these are like 4 KB. And page table entry size is also given as 8 bytes, right? Okay. A process P is currently using 2 GB. So they are saying that process is using 2 GB. So they are not giving in terms of the pages, they are giving in terms of the memory, right? 2 GB. So which means 2 GB means useful is 2 GB. 2 GB actually means 2 into 2 power 30, right? Bytes, which means that divided by 2 power 12 bytes, which is like page size. So you will be getting 2 power 19 pages. So basically you can say 2 power 19 pages are useful. So instead of saying 2 GB, you can say 2 power 19 pages are useful. 19 useful pages. Now let's just see how these pages are distributed, right? So basically they are saying in the next line, the minimum amount of memory is required for page table across all the levels. So they are not saying that how these pages are basically spread. This is up to you that how you do it. They are saying that what is the minimum amount of memory that is required here, right? So let me just explain the question. So they are saying that you have 2 power 19 pages. Yeah, 2 power 19 pages, okay, which are useful. So these pages could be useful from like some pages from here, some in between, some at the last. But they are saying you should be making the assumption in such a way that you get the minimum amount of size for the page table. See, by now you must have understood that we will be assuming that all the pages which are useful are basically contiguous. So this is innermost page table. Okay, so basically, see here, I told you, right, these all are called offset. So basically this is also offset, right? These all are called offset, and this is actually proven by this question. By the way, I have not seen this question earlier. I mean, when I have not noticed that they have actually written the offset here. Okay, just now, okay, I have noticed just now while I'm teaching, not even before that. Okay, so offset, it means that actually everything is offset. It's just that these are the page table offset, this is the page offset. Okay, anyway, so this is innermost page table. Now what we want these 2 power 19 pages which are useful. Okay, we want these to be contiguous, so that I don't have to basically use like, I mean, some of the page tables from here, like, I want all the page tables, even if it is more, right, all the page tables to be basically contiguous, so that it is least space. So I want, see, if these are 2 power 19 pages which are useful, so these there will be 2 power 19 useful page table entries, useful entries. And each entry, each page table at the innermost basically have 2 power 9 entries, right? So basically you can say 2 power 19 divided by 2 power 9, which is 2 power 10 page tables useful. If there are 2 power 10 page tables useful at this level, then at this level, okay, at L2, so at level 2, right, at level 2, there will be 2 power 10 entries useful, which is as good as saying 2 power 10 divided by, it's also actually 2 power 9. Okay, so 2 power 9, which is 2, right? So 2 page tables useful here, and at the last anyway you have to do one, right? So basically 2 power 10 page tables here, 2 page tables here, and at the last one. So you can say that the total amount of memory required will be 2 power outermost one, and its size is 2 power 9 entries, right? And at the last I will be multiplying with the page table entry size. Okay, Actually, page table entry size is fixed for all the page tables in this question, and in almost all the questions, like they tell you only one page table entry size. But it could definitely happen that they can tell you page table entry here is different, a size of page table entry here is different, a size of page table entry here could be different, just for the sake of question. In fact, there are standard university questions. I think I'm almost sure that one of such standard university question with the reference that okay, I've taken this question from this university, but the reference I have done in the class, in the original lectures in the course, and where the page table entry size was different at each level, which is fine. I mean, even if it's same or different doesn't matter. We understood the concept, right? So since it is same, so I will just multiplying with later. So here these are like this is size in terms of the entries. Okay, at the middle level, you can say two page tables are useful. So two page tables and each has 2 power 9 entries again. Plus at the last level 2 power 10 page tables are useful and each has 2 power 9 entries again. And page table entry size is basically, page table entry size is given as 8 bytes, right? So it is given as 8 bytes. So I will just multiply by 2 power 3 later, right? So basically you can say, now if you just simplify this. Okay. See, now I hope that you are finding these questions easy, right? So this question was one of the toughest question I can say on the Gate Overflow platform, but now you are finding them easy, right? Into 2 power 9 into page table entry size is basically 2 power 3. So like you can say it is 1024 1024 plus 2 1026 1027. Let me just see that they are asking in which unit, right? They're asking in kb. Okay, they're asking in kb. So basically you can say it is into, like 2 you can send here, this is k into 4, right? Into 4 kb, right? 1027 into 4 kb, so which is basically 4108, right? 4108. Okay, so let's just see the answer on the Gate Overflow itself. So what is the answer? Yeah, 4108. And by the way, this question has been answered by Deepak, okay, in 2021. So Deepak has answered this question and very beautifully he has answered. And I think he has written some remark here also. So by the way, like I'm 100% sure that you understood this question. But if there is any doubt, then you can also read this answer, okay? If there is any doubt, and these kind of questions are not very tough, to be honest. Now, I mean, earlier they might be tough, but now it is easy, right? They are just saying that minimum we want. Since we want minimum, we want all the pages that are being used to be contiguous, right? So that ultimately we get minimum. I mean, here you will be getting as many packed as entries possible, right? So that is why you will be basically saying directly that 2 power 19 entries will be useful. But let's just see the slight variation, or maybe the tough variation. Okay, so variation of this question, where they say of previous question, where they say instead of minimum we want maximum. Okay, so maximum, let's suppose they are saying maximum size of page table which are needed, right? See here, let me write it here. We had 2 power 19 pages used, right? So this is single label. Okay, this is basically at a single label you will be having many page tables. I mean, at the innermost level, obviously you have many page tables. Each is having 2 power 9 entries, and similarly here also many, and each is having 2 power 9, 2 power 9, like that, right? Okay. So if you want maximum, then what you need to do? You want all of these 2 power 9. See, there are how many entries in total? If you see, this is a 32, right? And 12 and 20. Okay, so if you see that at this level there will be 2 power 20, there will be 2 power 20 entries, right? At this level. So just a second, no, this is not 12. Okay, this is 39. Okay, so since this is 39, so it will be 39 minus 12, right? So it will be 39 minus 12, which is 7, and then 2 27, right? So you can say at this level there are 2 power 27 entries, right? At this level, innermost level, there are 2 power 27 entries, and then you have basically how many such you can say chunks or such page tables. So each is having 2 power 9 entries. So 2 power 27 divided by 2 power 9. So you are having 27 minus 7 is 20, and then minus 2. So basically you are having 2 power 18, 2 power 18 page tables or chunks, right? Page tables at this innermost level, at innermost level. Is this fine to everyone? Right. Now, if we want maximum, then we want all of these 2 power 18 to be used somehow, okay, without any hesitation, without any, and like without any, practically, I mean, without any, basically, I can say, the practical or the conventional way. I mean, in the conventional way, we are basically growing like this, right? But it is definitely possible that heap or stack may take the memories from anywhere, right? I mean as an implementation we do like this, we are growing like this, but it is definitely possible that we can start picking memory from anywhere. So let's not worry about it. Like, we just want the worst to worst case, okay? We should not be assuming that heap and stack or growing, or like, or maybe, like, in other words, like, we should not be worrying about the implementation part. We just want these page tables to be used as much as possible. So I want an each page table in each, see, there are 2 power 18 page tables, and I want in each page table I just want one entry, okay, for maximum. I just want one valid entry for maximum in each page table. So you can say, at innermost level, see, such question has already been asked in gate, okay. This is the variation of the previous gate question, but minimum and maximum, they both have been asked in gate. In fact, that have been asked in gate 2024, very very recently. I will solve that question also, okay. But let me just take the variation of this question. So at innermost, you can say, at innermost level, there are 2 power 18 page tables, right? At innermost level there are 2 power 18 page tables. We want we want each page table to hold just one valid entry. Each page table to hold just one valid entry. And since there are 2 power 19 valid entries we have to hold, so basically you can say that there must be page tables which are having more than one valid entry, because otherwise you can't accommodate this 2 power 19, because this number is more. Like, simple, you can say, simple pigeonhole principle, right? I have 2 power 18 such boxes, and if I just put 111 everywhere, then there will be, many remaining, right? So 2 power 19 minus 2 power 18, these many will be remaining actually, all right? So basically we have to fill maybe more than one, but at least I want one, right? I want that all of these page tables to be occupied. So 2 power 19 page tables are useful here. And then at this level also, if there are 2 power 19 page tables useful, then here also, like, there will be 2 power 19 entries which will be useful, right? Sorry, here 2 power 18 page tables are useful, so here also 2 power 18 entries which will be useful. Now again I want those 2 power 18 entries to be, I can say, to be taking as much as page tables as possible. So I want the number of page tables occupy here as much as possible. So basically what I'm trying to say, that at innermost level I want, see, this is, I think, little tricky variation, but that's fine. See, by the way, let me just write one thing here, so that it will be useful for the later part of the question. Let me write, see, number of page tables. Let me already write it, so that you don't get confused again and again. Number of page tables at each level. Size you already know, right? Size is basically 2 power 9 of each page table, each small page table, but number of page tables. So obviously one at outermost. And if there are 2 power 9 entries, then there will be 2 power 9 page tables here, right? If there are 2 power 9 page tables, and like, number of entries, if you count, and each page table is basically having 2 power 9 entries again, then 2 power 18 page tables here, right? So basically one page table, 2 power 9 page table, 2 power 18 page tables. I hope that is fine to everyone, right? So there are, like, these are number of page tables. Now for the maximum, I want maximum page tables to be used. So at this level, see, I have 2 power 19 pages which are useful, right? So that is why I want this all to be all page tables to be used. So 2 power 18 used page tables here. Now, since 2 power 18 page tables are used here, so 2 power 18 entries must be used here, right? So I want these 2 power entries to be spread such that all of these page tables are used here, right? So I want this 2 power 9, all of these 2 power 9 to be used, right? I mean, here since this is very huge, so that is why, like, I can say that, okay, since like 2 power 18 can be used here, 2 power 9 can be used here, because 2 power 18 entries could be used. And if each entry, I want each entry to go into individual page tables, right? So 2 power 9, or and here it is just 1. So you can say that 1 plus 2 power 9 plus 2 power 18 page tables, and one page table size, because each page table size is same, into 2 power 9 entries, and then page table entry size is, I think, 4 bytes, right? This will be the answer. This will be the answer if you solve for the maximum, right? So number of this is number of maximum page tables used. Basically basically you can say that, if you allow your memory to be taken very arbitrarily, right? I mean, you don't assume that, okay, heap stack grow like this, okay? For the minimum, you assume that all are contiguous. For maximum, you assume that, okay, all are in such a way that you can basically use as maximum page tables as possible, right? All are in such a way. Let's suppose if it is 2 power 10 only, then can you use 2 power 18 page tables? Obviously no, right? If there are 2 power only 10 entries, 2 power 10 entries are only useful, then how you can spread 2 power 10 entries into 2 power 18, right? So automatically it will come down to be 2 power 10 in that case. But here, since 2 power 19 pages useful, so 2 power 18, so 2 power 19 entries useful, that is why I can basically take all of these page tables in the worst case, right? Okay, so I hope you understood this little bit, that what we are doing. But you will get more clarity with more questions. So that is why we are going to solve all of these questions. Okay, we are going to solve all of these questions. Now let's solve this GATE 2024 question, which is basically interesting question in the sense that they are asking minimum and maximum both. They are saying let x denote the minimum, and by denote the maximum, right? Maximum number of pages. Okay, across two level page table. So basically, yeah, this is the same question. This is the same question, just I'm writing in this short, okay, so that I don't have to read all of this. So basically they are saying that you have 32-bit system and 4 byte page table entry, two label you are using. Okay, they are only using two label. So basically you have this setup. Here you have to write 4 KB, so you have to write 12, right? Here this is single, I mean, this is two level. So basically, let me just read it out. Okay, so basically they have not given this division. If they do not give this division, then always assume that a smallest page table, or the smaller page table, or the chunks in which we are dividing, okay, chunk size in which we divide, or the smaller page table size is same as page size. Okay, this is the assumption that we do if they do not give these entries. I mean, if they do not tell you that, okay, what should be the division, how you are dividing the page table, the single level page table, if you want to divide. So if they do not give, then in what size you should be dividing, then you can assume that they are dividing in the page size. Now page size is how much? 4 KB. So each 4 KB, but how many entry will come in 4 KB? 4 KB divided by 4 bytes, which means 1K, which means 2 power 10 entries, right? So 2 power 10 entries will come in one of the page table. So 10 here, and remaining is automatically 10, right? Okay, so basically this is a division. Have you understood this, what we are doing? So if they do not give you that what is this exact division, in that case you assume, only in that case, right? Otherwise you don't assume. Only in that case you assume that this is 10 and this is 10. I mean, basically the chunk size is actually equal to page size, if they do not give you that what is the division. Okay, great. So now they are saying that you are dividing into 10, 10, 12. Now they are saying that you use 200 unique pages, or 2000 unique pages. Okay, so you have 10, 10, 12. So pages useful is equal to 2000. Pages useful equal to 2000, right? Now Now this is the division that we have. Okay. Now they want x to be minimum number of page tables, right? Minimum number of pages of page tables basically used by the two level page table, and minimum and maximum they're asking. Okay. Minimum is very easy, so let's just do first minimum. Okay. Minimum is very easy. So if we are using 2000 pages here, right? If you are using 2000, let's just assume all of these 2000 are contiguous, which means let's just assume that at a single level, so there are two levels. At this level, 2000 entries are useful. Entries are useful, which is same as if one can contain 2 power 10 entries, so it is same as 2000 divided by 1024, right? It will be 1 point something. So basically one will be one of the page table will be completely full, and then second will be having little less, which is fine. So basically you can say this is 2, right? Which means here if 2000 entries are useful, which is same as saying 2 page tables are useful. And here anyway it is 1, right? Here anyway it is 1. So basically since size is same, right, 10 and 10 size same, so you can say total 3 page tables are useful, and each page table size is 2 power 10 entries, which is same as these many bytes. So this is 1024. So they are asking in terms of minimum maximum number of pages across the route. Okay, so they are not asking in terms of the bytes, they are just asking how many page tables. So let's not multiply. So they are just asking how many page tables. So x is the number of page tables, right? So these are the 3 page tables. Okay, so minimum you need 3 page tables. I hope that is fine. That's very easy, right? I mean 2 page tables here and 1 is here. What is the maximum? Let's just do this same question for the maximum. For the maximum, what I want? For the maximum, I want that all of these 2000 spread in such a way, okay, in such a way that that these are by the way not contiguous. All of these 2000 in such a way that these 2000 entries should be taking 2000 page tables, right? I want these 2000 entries to take 2000 page tables. By the way, how many page tables are there at this point? Here 2 power 10 entries, so you can say 2 power 10 page tables are there, right? 2 power 10 page tables. If 2000 entries are useful at this level, then and 2000 entries are useful at this level, then I want 2000 page tables to be useful. But since I don't have 2000 page tables, so I can say I want this 2 power 10 page tables to be useful, right? So at maximum I can say it will be 2 power 10, right? I mean 1 is anyway there at the outermost, but 2 power 10 here, which is 1025. Okay, have you understood? Very easy question. If it is maximum, then I think maximum is more easy, right? I thought minimum is easy, but I think maximum is also more easy, right? Because for the maximum, I want all of the page tables to be useful, right? In that case, if this is 2 power 10 page tables, then can I use all of this 2 power 10? Yes, because these are 2000 entries, so I can use, right? If this is, let's suppose, only 1000 entries, in that case I cannot use this 2 power 10. I can only use the 1000, right? I can only use 1000. So instead of 2 power 10, I will be writing 1000 if these are the 1000 entries. Okay, understood this question? Easy question. So basically you can say 1025 maximum number of the page tables, and minimum is 3, right? Minimum is 3. So x plus y is basically, you can say x plus y is this 1028, right? So this is minimum, this is maximum. See this answer or this comment I have already written on the gate overflow. So basically for minimum we want 2 inner and 1 outer. For maximum, these 2000 entries are spread as much as possible. Ideally 1 entry per inner level page table. Since inner level page tables are limited to 1024, all 1024 inner level page tables will contain at least 1 valid entry, right? So basically it is 1024 plus 1, right? Easy question. Now they are seeming to be easy actually. See, one interesting fact about this question, that this has been asked in GATE 2024, right? And we have given the exact same question. Okay, in fact, like we are saying x plus y, the words are also not changed. We have already given this exact same question 1 month before GATE. 1 month before GATE, we have asked exact same question. Okay, And this is, very proud moment, I can say, that since we, do so much of effort, we try to find out as many standard questions as possible, and finally, like, our hard work of making test series is worthwhile, right? We put gate relevant questions only, and then it many times it happens that our exact same question, you can say, which have been never asked in gate, and no test series have never asked like this type of question. No one thought about those type of questions. We put those type of questions because we strongly think those are related to gate and very much relevant to the gate, and then gate also asks these type of questions. Okay, so there has been many instances. So we have also asked this question. So by the way, you can try solving this question. This is also, very, very nice question. Here, instead of 2, we have 3 level. Okay. So the answer is on the next page. Just try it out. It is also very nice question. Okay. So answer is on the next page. You can definitely try it out. This is also very nice question. Okay. So I hope you understood this minimum and maximum concept, right? So just to basically summarize, I can say for minimum, just keep pages contiguous. For maximum, I can say that try to use as much inner level page tables as possible. Okay. By the way, we have given we have also given the reference of this question, that from which university we have taken this question under this question. Okay, if you see this question on the Gate Flow, this is under mock test 2. You can see link from which university we have taken this question. Okay, and that university also has the solution, but we have little detailed solution. They just have 1 or 2 line of solution, but yeah, we have detailed solution. There also answer is 16. Here also obviously answer is 16. Right, this is kind of summary that you can say, right? Okay, hope you understood these type of questions. So now let's just solve this question. So this question has been asked in gate 2013, and this is very much related to, page table and all, but this question also had 2 parts in year 2013. Okay, in year 2013 this question had 2 parts, and in one of the part they have asked something related to virtual index, physical tag, cache, and so on. So let's not worry about that part. I'm just writing the part which is relevant to us. So like, I'm just, trimming the part which is not relevant for this particular video. So basically, this is gate 2013 question. Let's just try to solve this. A computer uses 46-bit virtual address and 32-bit physical address. This is easy question, but let's just solve this. So basically, you are saying 46-bit virtual and 3 level page table. 1, 2, 3. And okay, so this is 46, which is virtual address space. And now similarly, you have 32 bits, which is physical address space. So this is frame number. This is, you can say, this is the offset, right? So basically, this is your 32 bits. And this is physical address space. Now, what they're asking is, they're saying that page table entry size is 4 bytes. Now, what is the size of page? That's what they're asking. Now, assume the size of page is, this easy question actually. Size of page is, let's suppose, 2 power p bytes. Okay. Suppose, assume. Now, can you solve this question? See, if this is 2 power p bytes, then obviously you will letting p here. We just have to figure out these quantities, right? And then we just need to sum up all these quantities and to 46, and then maybe probably we need to find out the p. Now, if this division is not given, then what we need to do? We need to assume one simple thing that we need to assume, and which is the very standard thing, and which is actually generally we implement this also in the modern operating system. But still, if this is not given, then only we should be assuming that. What is that? That smaller page tables, or in that case, I'm just calling it chunk. Okay, chunk size, or the smaller page tables, like whatever you like to call. smaller and this outermost, okay, both. Okay, I mean the final page table, right? I mean the final page table, after the division, basically smaller means final page table after the division, equal to the page size. What is the page size? Page is 2 power p, right? 2 power p, that's what we have assumed, bytes, right? Bytes. So the smaller page table size is also this much. But I can write p directly here because each entry is basically 1 byte, or maybe like you know that, okay, if this is 2 power, we write p here, right? 2 power p, then we write p here. What should I be writing here? Can I write p also here? No. Here I don't write the page table sizes. I write the sizes, but in terms of the entries. So you can say this is same as if this is 4 bytes. So 2 power p minus 2 entries, right? Now you can write p minus 2 here. This is same as like this. Okay. Have you understood what I'm trying to say? Basically, I cannot write p directly here. I need to write in terms of the entries only. I mean size in terms of the entries. So if this is 2 power p bytes, then 2 power p minus 2 entries. Okay. Now if you sum this up, this is 4p minus 8 equal to 46. Okay. So now you can solve for this. 4p minus 6, not 8, sorry. 4p minus 6. Okay, and then you can solve for this, which is basically coming out to be 13. And since I assume 2 power p to be page size, okay, so you can say 2 power 13 bytes are page size, which is 8 kb. I've answered this question on the Gate Flow long back, I think in 2016. Okay, long back. Okay, I hope you understood. The key point here is that whenever you have to assume the page size, okay, or something which is already the format, right? You already know that, okay, it is always in the 2 power, right? So don't assume it to be x. Don't assume page size to be x, because your calculations will be unnecessarily lengthy, complicated, right? Just assume it 2 power x, 2 power p, because this will make the calculation easy. That's the key point. Okay, assuming that page size is 2 power p, this is the, I can say, the key point to avoid lengthy calculation. Okay, now I hope this is over and this is understood. So by the way, have you understood the part which I just told you, that if they do not give you the smaller page table sizes, then just assume that to be page sizes. Okay, this is a standard assumption that we do, because that's how in many operating systems it has been implemented. Let's solve this question. So this is not a gate question, but this is very nice question, I can say. And this question is basically, this question will make sure that you understand concepts even more clearer. Okay, and based on this question, there has been very popular question that has been asked in gate. So let me just tell you that this question, which has been asked in gate 2008, and this is one of the most popular question among all the subjects and among all the everything on the gate flow and in the gate CSE, I can say, right? This question has got these many aboard. This has got 98,000 views, and it is extremely, I can say, popular question in terms of difficulty, or in terms of like appreciation. And we will be solving this question, but before that I want to make sure that you understand concept very clearly, so that is why I'm solving this question first. Okay, so let's see what this question is asking. They are saying that there is a processor which is having 11-bit physical address and 16-bit virtual address, and virtual address is divided like this, right, using two level page table. Now they are saying that virtual address is divided, so virtual address space is basically has been divided like this, which is 538, right? So this is 5, this is 3, this is 8. And now they are saying this is basically L1, this is L2. Okay, now they are saying that each page table entry is 2 byte in size and has the following format. I mean, page table entry has this format. Basically this is the general format that we have, the control bits, like dirty bits and other bits. So basically we have valid, invalid bits, something like this, right? So basically you have something called as page physical page number, and then there are control bits that you have. Okay, now basically they're asking something interesting. They're saying determine which of the following L1 and L2 ppn values cannot be possible. Okay, See, let me tell you that what does this mean and what they are asking. Okay, so I have framed this question. So just to make sure that you understand few things which should be clear to you. Now, so this is L2 and this is L1. Can you tell me, with respect to L1, can you, or with respect to L2 or whatever, right? Okay, can you tell me what is the size of each individual, small page table here, or chunk size or a small page table size? I don't need to write the small. You can directly write page table, right? Page table size at L2. At L2, what will be this? 2 power 3 entries, but each entry is of 2 bytes, so I can say these many bytes, right? So which is 2 power 4 bytes. Okay, and they have also given page size or the frame size as 8 bit, 2 power 8, which is basically, you can say, frame size is equal to 2 power 8 bytes. Okay, see, what they're asking is that here here what will you be doing? You will be basically finding out using these 5 bits. Okay, using these 5 bits, you will finding out what is the offset. This is just offset, right? Where to go, right? I mean, within 2 power 5 entries, where to go. And each of this entry is of this form. So basically it will be having some frame number, physical page number, physical frame number, and then some control bits, right? Each of this entry will be in this form. So they're asking that what are the possible values for this particular thing. So basically they are saying that that using this 5, okay, using this 5, you will go to one of the entry. Okay, let's suppose you are going to this entry. Okay, using these 5 bits, you will be going to one of the entry, and each entry here is basically will be containing some physical page number, something, and some control bits like this, right? So they're asking what are the possible values, okay, of this in L1 and in L2 both, right? So this is, let's suppose, L1, this is L2. See, let me solve this question directly, okay, without explaining the question much, because the more I explain, probably you will get more confused. So let me first tell you the solution, then you will automatically get to understand. Okay, using these 3 bits, you will be going to, by the way, one of the place, and you know that here also page table entry will be something like this, some frame number and some control bit, something like this, right? and and this basically will the frame number which will be pointing to one of the frame. Okay, one of the frame. Okay, this is the one of the page, or one of the frame, basically, right? One of the frame. This will be pointing to one of the inner level page table, right? This will be pointing to one of the inner level page table. So basically you can say this will point to one of the, this is one of the inner level page table, inner level page table. Okay, and this will point to one of the real frame. Is this fine to everyone? Great. Now tell me, if the physical address space is of 11 bits, I think this is 11 bits, right? Yes, 11 bit physical address space. Suppose the physical address space is having 11 bits, then can you tell me that how many such frames are there if frame size is 2 power 8, or frame size, you can say, in terms of the bits I'm just writing. I will not be writing size, I will say the number of bits required, right? It's basically 8 bits. So can you tell me how many such frames can exist? So basically it is 11 total. So 8 is here, 8 is here, and then how much is remaining? 3 is remaining, right? So 2 power 3 such frames could exist, which means 8 frames could exist. So if I have to tell the frame number here, then this will be ranging from 0 to 7, isn't it? Is this fine to everyone? I hope till now it is fine, because there are 8 frames possible. Because there are 8 frames possible, that is why this can range from 0 to 7, right? Now, more interesting is this part actually. Okay, see, this is telling you one of the inner level page table. Okay, so what does this mean actually? What does this mean? See, this which is outer, right? This is outer, is pointing to, this is pointing to one of the inner level page table, and this one of the inner level page table, it is pointing to one of the frame, right? That's what you know. This is one of the frame, which is having 2 power 8 bytes in size. And how many such frames are possible? So you can say 2 power 3 frames are possible. Okay, 2 power 3 or equal to 8 frames are possible. And that is why this can range, right? So I can say this can range, this value will be from 0 to 7, right? Now this is okay to everyone. Now let's just see that what is the possible value of this, right? What are the possible values of this? Can you tell me the size of inner level page table? So this is the inner level page table. The size is basically 2 power 2 power 3, and which is basically in terms of the bytes it was 2 power 4 bytes. Okay, so the size here is, okay, size is 2 power 4 bytes, right? This is the size. Is this fine to everyone? Now comes the interesting part. Okay, the interesting part is saying that, see, physical address space is basically physical address space of 2 power 11 bytes, right? Now if I have to store this, okay, like doesn't matter, okay, don't worry about the paging, okay, doesn't matter, this is paging, this is what, right? Doesn't matter. But if I have to store some piece of this which is having 2 power 4 bytes, then first I have to divide into 2 power 4 chunks. Is this fine to everyone? First, I have to divide this each of 2 power 4 chunk. I mean, this is just to make the address alignment, which means that the starting address, wherever I store this, okay, ultimately I have to store in the physical memory, okay. So wherever I store this, it must be multiple of 4. Or in other words, last 4 bits must be 0, okay. Just to make sure this, we can understand simply that we are dividing the physical address space into 2 power 4, 2 power 2, 2 power 4 each. So in other words, you can also say that this is 11. Then basically this is 4. Then how much is remaining? 7 is remaining. Which means 2 power 7 such slots. Okay, I mean either you do like this, okay, or you do like this. It doesn't matter. So I'm just saying that 2 power 7 such slots are available. So basically this will go and fit in one of such slot. So which means 2 power 7 means 128, which means this number will be 128. I mean it cannot be more than 128 or something like that, right? I mean since it is just telling you that in which slot you are, okay, can it be more than 128? So just think about it. It is just telling you in which slot you are. Can it be more than 128? No, right? So basically it will be 0 to 127, because here I was telling you the frame number. Okay, I mean the frame, or here also you can say the slot, doesn't matter. So basically if you want to fit one page, okay, with respect to this page, you can assume that main memory is divided into 2 power 8 each. Okay, so basically what I'm saying, whenever I needed to fit this frame, okay, it is just a memory view that we have, because ultimately I want the address alignment. This is important. Okay, so whenever you can say that I wanted to fit this frame, okay, then you can say that this 11 has been divided into 8 and 3. Okay, 8 and 3, which means 3 bits can tell you that, okay, I mean this will not be needing more than 3 bits. Basically this will be the range of possible values are 0 to 7. This will not be needing more than 3 bits, because it can just tell you that, okay, that this is basically loaded into which frame or which slot, right? So this page is loaded into which frame. Okay, so it doesn't need more than 3 bits, or in other words, it just need 0 to 7 possible values. Okay, but suppose the page, the or this, yes, this page size is, let's suppose, 2 power 10. 2 power 10, suppose the page size is 2 power 10. Okay, so in that case, if you assume that page size is 2 power 10, in that case what will happen? In that case you will say this will be 10. Okay, this is just 1, right? This is just 1. So which means there could be only 2 such slots possible. right? So this is basically just one bit you need. So basically you can say this will either contain 0 or 1 or 1, right? Here this is just a small variation where I say that a page size, suppose, okay, page size is assume 2 power 10 bytes. In that case I will say that, okay, this is either 0 or 1. Are you getting my point? The thing here is this, that whatever I want to store in the physical memory, I will just say that memory is divided with respect to that, which means if I want to store the real page, okay, then it doesn't matter I have to have these many pages, okay. I'm just saying memory is divided into that, and I will be basically seeing that how many such slots it is, just containing the slot number or the frame number, right? So 2 power 3 such slots are possible, so that's why 2 power 3. Now if I basically, if I have to, you know, if I have to store this thing which is of 2 power 4 bytes, so I will assume that main memory is divided like this, okay. So which is 4, and out of 11 this will be 7, which means that here I can just have a number which is 0 to 2 power 7 minus 1, okay. So the possible range here will be 0 to 2 power 7 minus 1, or in other words 0 to, this is 128, so 127, okay. This is the possible range here. Why I am saying so? Because you will be going to store this, and there are 128 such slots possible where you can store this, right? It will be going to one of such slot. Get my point? Similarly, if you want to store this, then you can say there are, okay, it's the same physical memory. You can say there are basically 8 such slots are possible, and this will be going to one such slot. So that is why this will be 0 to 7, okay. If you are going to store this, then you can say there are basically 2 power 7 such slots are possible. That's why here you will be writing 0 to 2 power 7 minus 1, or 0 to 127. Are you getting my point? So it is just a view of memory. If you want to store this, right, then it will be this number basically will telling you that, okay, which in which slot your page is, right? This number will be telling in which slot your this thing is, right? So how many such slots are possible? That's what we need to find out. Okay. So that's why here it is 0 to 7, here it is 0 to 127. Okay. Here it is 0 to 127. Why that is the case? Because it will depend on size of this, size of what it is pointing to. If it is pointing to this, and this size is basically let's suppose 2 power 4 bytes, then if you divide into 2 power 4 2 power 4 2 power 4, then there are 2 power 7 such slots are possible. It will be just maintaining one such slot number. If this is 2 power 8 bytes, and then if you divide the physical memory into 2 power 8 2 power 2 2 power 8 2 power 8 like that, then there are 2 power 3 such slots are possible, and it will be maintaining one such slot number. Okay, this is little counterintuitive, but I hope you are getting the point. So so like, let's just see the options. Basically, which of this is not possible? They are asking cannot be possible, right? They're asking cannot be possible. So let me just paste the options here. So which cannot be possible? I think L to ppn value is equal to 15. This is not possible. Why? Because this can be 0 to 7 only. Okay, this can be 0 to 7 only, and this can be 0 to 127 only. So this is always 0 to 127 in all the given option. But in this option D, option D, this is not 0 to 7. Are you getting my point? Okay, so basically the thing here is that the conclusion that I want to make, okay, the conclusion that I want to make is that this is your physical memory, right? This is the whole universe. I mean, this is the reality. Okay, this is your physical memory. Now this is just a contiguous memory. This is not generally divided, or you can say it is main memory. Now if you want to even store one integer here which is of 4 bytes, then basically you assume that it has been divided into 4 4 4 4 4. Why we are doing so? Because this is just a way of understanding, okay? Because this is how we are understanding the address alignment. We are saying that wherever you are going to store, so initial 4 bits is 0 to 3, next is like 4 to 7, something like this. Wherever you are going to store the initial address, which is like 4 or which is 8, like this, right? The initial address must be divisible by 4. To understand this thing, we are saying let's just divide into 4 4 4 4 4 4, and so that wherever you store, it will get stored into one of the slot. Similarly, whatever you want to store here, you assume, okay, the main memory has been divided into that size, okay? And how many such slots are available based on that? Let's suppose this is let's suppose this is 2 power p bytes, okay? And this is 2 power uh, n, okay, n bytes of memory. Then tell me how many bits are needed to store the address of this block. Okay, let's suppose this is B, not okay. Let's just call it block. Okay, let's suppose this is some block B. So how many bits are needed needed to address one on not one such block? You can say to address B, right? How many bits are needed to to address B? If they ask you this question, then what will you say? So this is a question, just try to solve this, right? You will say that, okay, assume mem memory has been divided into 2 power p size each, right? Which means there are 2 power n minus p slots available. Slots or frames, whatever you want to call it, right? These many slots are available. So this will go, okay, so you can say this will go and fit in one such slot, right? So so let me write it here, that you can say this will go and sit in one such slot. Okay, this will go and sit in one such slot. So which means if there are 2 power n minus p slots are available, hence n minus p bits are required. N minus p bits are required to uh, to address B. Is this fine to everyone? So answer is n minus p here. Okay. Based on the same concept, they have asked the most popular question of this gate CSE history. The most popular question based on this concept. Right? See, whatever the idea is simple. Whatever you want to store in the main memory, assume that main memory has been divided into such into size, like into slots of that size. Okay. So, for example, if you want to store this block, which is 2 power p, then assume that main memory has been divided into 2 power p, 2 power p, 2 power p, and this will go and sit in one such block, right? You don't have to fill main memory with all of this, okay? It's not like you have to have many of this so that main memory is completely filled with this. No, it's not like that, okay? Even if you have just one such b, assume that it has been divided like this and you are going to store it, right? Now let's just solve this most popular gate question, okay? So what they are saying, let's just see. So basically they are saying that you have 36 bit physical address and 32 bit virtual address, okay? And you are using 3 level, right? So basically 0 to 11, I mean this last, which is basically 12 bits, right? 12 bits are used for the page offset, and then these are the 9 bits which are used as a third level, they are calling it L3. Okay, and then these are 29 minus or 21, which is 8 plus 1 9. So this 9 is L2 they are calling, and then these are 2 bits, 30 and 31, right? 31 and 30, these 2 bits they are calling it L1. So basically they are calling the division is like this, okay? Now they are saying page table entry size is 4 bytes, okay? The number of bits required for addressing the next level page table or the page frame in the page table entry of the first, second, and third level. So basically, just tell me that how many how many bits will you will be requiring to address the next level, which is the frame. It will depend on the frame size. What is the frame size? See, the physical memory is of 36 bits, right? The frame size is 12, so you can say you are dividing into 12, 12, 2 power 12, 2 power 12, 2 power 12, or instead of that you can do like this. So basically this is 24. So here at this level, how many bits you will be needing? You will need 24 bits. Why that is the case? See what I am trying to say. Let me go to the next page. I'm saying that if you want to fill this particular frame, okay, which is of 12 2 power 12 bytes, so you assume that physical memory has been divided into 2 power 12, 2 power 2 power 12. How many such slots are possible? 2 power 36 is total size, 2 power 12, so that's why 2 power 24 such slots are possible. So you need 24 bits here, okay, to address this next level. So you need 24 bits here, or you can directly do like this, right? You need 24 bits here, so 24 here. Now, tell me what is the size of this L3? See, in terms of the entries, you can say 2 power 9. Okay, 2 power 9 entries, which is basically 2 power 9 into 2 power 2, because each entry is of 4 bytes, right? So you can say 2 power 11 bytes, right? So this is the size. Now, this L2, this one of this L2 will point to the L3, right? I mean, see here, this is L1, okay, L1, one of the, this is, I mean, this is only, yeah, one, I mean, L1 is only one, so L1 is pointing to one of the L2, okay, one of the L2, okay, so this is one of the L2, and L2 is pointing to one of the L3, one of the L3, and L3 is pointing to one of the frame, one of the frame. But interestingly, either it is L1, it is L2, L3 frame, whatever it is, okay, whatever it is, ultimately they have to get stored into physical memory, okay. Ultimately they will get stored into physical memory. So what is the size of this frame? 2 power 12 bytes. What is the size of this? 2 power 11 bytes. What is the size of this? Again 2 power 11 bytes. What is the size of this? This is 2 power 2 into 2 power 2, which is 2 power 4 bytes, right? These are the size. And ultimately all of this has to be stored into the physical memory. So how many bits are needed here? If you are it depends on what you are storing. See, will it depend on this previous? No, right? Will it depend on itself, which means that how many bits are needed here? Will it depend on size of L3? No. Okay, it will only depend on the size of next level, which is like what you are storing. I mean, what it is pointing, it is pointing a frame, right? So how many such slots are available if you want to basically store one such page? So you can say that out of 36, this is 36, 36 minus 12, which is 24. I mean, 24 bits will be needed here to address this. Now, how many bits will be needed here to address next level? So next level size is 2 power 11. So basically you can say 36 minus 11, which is 25 bits will be needed here. 25 bits will be needed here to point this, right? How many bits are needed here? How many bits are needed here? Tell me. Again, it will depend on the size of L2. So basically you can say here you will be requiring 36 minus, what is the size? 2 power 11, so 11, so which is 25 bits will be needed here to point to the next level, right? Now suppose there is a page table base register, okay. How many bits will be needed here to point to L1? How many bits will be needed? So L1 size is basically, you can say L1 size is how much? 2 power 4 bytes. So there are many such slots are possible. So you can say that 36 minus 4, which is 32, right? 32 bits. So anyway, this has not been asked in question. They're just asking this. So 25, 25, 24 is the answer. 25, 25, 24, right? So D is the correct answer. Okay, I hope you understood this question. This was one of the very popular question. Okay, so some people get confused that each will be 20 24. Okay, each of this will be 24 because ultimately okay, sorry, just wait. So each of this will be 24. Okay, because ultimately like we are having the frame number. No, we are not having the frame number everywhere. I mean the definition of frame keep on changing. I mean basically here you are storing this, here you are storing this. Okay, so it's not like that always we will be having the frame number bits. Okay, some people are having 24, 24, 24 as an answer, and that's why this is the misconception, and that's why many of the people marked B as an answer. Okay, the frame number will be requiring 24 bits, so that's why B is answer. And then they later read the explanation, they later realized that B is not the answer, D is the answer. Okay, this is one of the most popular question.